Hello out there, you are welcome to Dave Tutor Academy, where we are devoted to building excellence in students in the STEM subject. For the grade 12 student out there who is preparing for the physics exam, we know that you have quite a lot to cover for the physics syllabus, talking about mechanics, heat and temperature, waves and optics, electricity and magnetism, modern physics, astrophysics, introductory electronics, and so much more. So we have compiled a bank of questions, over 200 questions within this 10-hour period, and you are going to find them useful in preparing for exam. Talk about WAEC, NECO, GCE, GED, GCSE, and even JAMB UTME. And we are doing this because we want you to actually be the best that God has created you to be. And acing your exam is actually a big step towards that direction. We just want you to get your writing materials, get yourself set, get ready. Let's walk along. It is as you walk along that you get to build proficiency in this source. And if you really like what we're doing, we'll appreciate your support so that you can also be encouraged to keep on doing more, not only for you, even for students that are coming after you. So you can support us by giving us a super thanks from YouTube. You can head over to Buy Me a Coffee and can offer your voluntary donation. We know it will really encourage us to do more. So our video is set for us. Let's just go ahead and delve into our work as you aim for that excellence. All right. In this question of mechanics, we are told that the slope of the straight line displacement time graph indicates what? So if you are looking at the displacement time graph, you have something like this. This is the displacement, and on the horizontal axis, this is the time. Okay. So no matter the direction in which the graph is going, let's say it's something going like this. Now, if you are looking at the slope of that graph, normally the slope will be the change in the vertical axis over the change in the horizontal axis. But here, our vertical axis is actually displacement and our horizontal axis is time. So we have displacement here and we have change in time here. So normally, if you are getting slope, we know it's the change in the vertical axis over change in the horizontal axis. So you have change in displacement over change in time. So if you are looking at change in displacement and change in time, what is that giving you? That is nothing but velocity. So students, you need to be careful here. If we have been asked that what is the slope of the straight line distance time graph, distance is actually a scalar quantity, then the correct answer would have been speed. But here, since we are talking about displacement, the correct answer is actually velocity. So we are looking at uniform velocity in this particular case. Here in this question, we are being asked that a man will exert the greatest pressure when he does what? These are actions that are highlighted for him. But before we look at those options, let's look at our understanding of pressure. We know that pressure has been defined as force per unit area. Okay, so now what we are noticing is that if you are increasing the force, definitely pressure will increase. Okay, now if you are increasing the area, because it's a denominator, the larger the value, then the pressure will be decreasing. Meaning that if you are reducing the area, then the pressure will be increasing. It is an inverse proportion. Look at this, it's an inverse proportion. Okay, so increase in area will result into a decrease in pressure, and decrease in area will result into an increase in pressure. So we need to look at these options that we are given and look for the one with the least area. Okay, that will give us the area where we are going to have the maximum pressure. So when a man is lying flat on his back, of course, we have a whole lot of body contact with the floor. So that is not going to give us the greatest pressure. When he's lying on his belly, it's just the reverse of lying on his back. So it's still the same thing we're talking about here. Now, when he's standing on both feet, the 2 feet will exert some pressure. But since they are just the 2 feet, that is going to also be a bit large. But now, when we are looking at a man standing on the toes of 1 foot, meaning that the man is here and he's saying he's standing just on the toe of a foot, definitely if he's doing that, we are going to have that. If this is what he's just using on the floor, that area, you can see it is going to be a small area, and since it's small area, then in that particular case, pressure will be high. That will be high pressure. So the man will exert the greatest pressure when he stands on the toes of 1 foot. Compared to all the others, this is the least area and it will amount to the greatest pressure. Here in this question, we are being asked which of the following physical quantities are derived. Okay, so for mechanics generally, we know that the standard quantities, the basic quantities from which others are derived are the length, the time, and the mass. Okay, so if you look at all of this, already we are saying that mass is here. So mass is a fundamental quantity. It's not derived. So the answer will be area, thrust, and pressure. And looking at that, we are looking at 1, 2, and 3. So here, 1, 2, and 3 only are derived quantities. Mass is actually a fundamental quantity, and the correct answer is option B. Here in this question, we are told that a ball of mass 0.5 kilogram is moving at 10 meters per second. So we have U for that is 10 meters per second. Okay. It collides with another ball of equal mass at rest. So there's this other ball also having 0.5 kilogram, but it is at rest, means that its initial velocity is 0 meters per second. Okay. Now, after the collision, if the two balls move together after the impact, we have to find their common velocity. So afterwards, we are going to have something like this. We have one 0.5 kg and another 0.5 kg, and then they are moving with a common velocity that we are to calculate in this particular question. So by reason of the conservation of momentum, we know that the sum of the momentum before collision is equal to the sum of the momentum after collision. Before collision, we have momentum to be mass times the velocity. So for this first case, it's going to be m1 u1, and for the second case is m1 m2 u2. Okay, and then finally the bodies are going to be moving together. So we have the mass to be m1 plus m2 multiplied by the common velocity v, which we are looking for. But now, because we are told that the second body is at rest, meaning that u2 is 0, so this whole is going to be knocked out because 0 times m2 is 0. So we only have this to be, if you want to make v the subject of the formula, v will be m1 u1 over m1 plus m2. And if you had to just put in those values, m1 will go to be 0.5. The initial velocity for that first body is 10 meters per second over the m1 plus m2 will be 0.5 plus 0.5. So just want to get this, it will be 0.5. I want to still write it like that, times 10 over 2 times 0.5. Okay, because I'm having 0.5 in two places, I can just say it's times. So this 0.5 and this 0.5 can knock out, and the final velocity we are looking for will be 10 over 2, which will be 5.0 meter per second. Okay, and if you look at the options, you can see option C is corresponding to that. Here we are being told that the motion of a body is simple harmonic if D. So we are expected to fill in that statement to look at the condition for which a body will be in simple harmonic motion. Normally we can look at a simple harmonic motion just like this, okay, in which we have this particular system, right, and then we'll have this body moving towards the center and moving towards the center. Or if you want to look at the action with some spring, okay, so we can have this body also as a reason of being drawn. It can move in this direction or it can move in this direction when it's actually excited on this particular spring. So of all of these options, first, we're told the acceleration is always directed towards a fixed point. That's looking interesting. The path of the motion is a straight line. In this particular case, it's not a straight line, so that is not true. We are being told in the option C that acceleration is proportional to the square of the distance from a fixed point. No, that is also not true. Then here we are being told that acceleration is constant and directed towards a fixed point. Acceleration does not necessarily need to be constant. So of all of these options that we have, the best solution will be that the motion of a body is simple harmonic if the acceleration is always directed towards a fixed position. So it can go anywhere, but it will always tend to pass through that center. And in this case, it can also go to the positive or the negative axis, but it will still want to return to this fixed point. So the correct answer is option A. In this question, we are being asked which of the following statements is not correct about the molecules of a substance in a gaseous state. So if you look at molecules of a substance in a gaseous state, I want to look at their behavior. In the first case, we are being told that they are in a constant state of motion. That is true because all of these molecules will just be moving helter-skelter. They are never static. Okay, so that is very, very true. Then they have different speeds. That is also true because the molecules actually going to be colliding with one another, colliding with the wall of the container, and then their speed will be different. Okay, they have a temperature which is measured by the average kinetic energy. That is also true because temperature is actually measured by reason of how excited the molecules are. So if they are highly excited, they move around a lot, and then they have so much kinetic energy, and temperature can be a measure of that. So that leaves us with option D here, that the collision between the gases is perfectly inelastic. It's not inelastic, it is elastic. So the solution to this question is option D. Yeah, in this question on gas laws, we are told that a given mass of gas has a pressure, so we can have our parameters written down. Pressure of 80 Newton per meter square at a temperature of 47 degrees Celsius. When we are working with this, we need to convert to Kelvin. So we have 273 to convert to Kelvin, and that will be, it will just be that you are having 50 plus 270, that is 320 Kelvin. Okay. Then now we are told that the temperature is reduced to 27 degrees Celsius. So the temperature now, this is T1, T2 is now 27 degrees Celsius. And again, we are converted to Kelvin. That will be 300 Kelvin. And here, we have to find the new pressure. P2 is our unknown. Now, if you are looking at this, I generally advise that as a rule of thumb, you can look at the general gas equation that P1 V1 over T1 is a constant, okay? So you can just eliminate the one that is not needed to feature here. You can see that we are not dealing with volume here. So for this particular question, we are looking at pressure and temperature, and the relationship between them is that P1 T1 is equal to P2 over T2. What we are looking for is P2, so I love to say my P2 is, if I cross multiply here, okay, I will have P2 to be P1 T2 over T1, and if we are to do that, P1 we got to be 80, then T2 we got to be 300 over T1, that is 320. This can cut quite easily. 80 here 1, 80 here 4. 4 can go in 300. We can say 4 here 1, 4 in 300, 4 in 30, that is 7. 4 times 7 is 28, remaining 2. 4 in 20, that is 5. So we have 75. So our P2 is nothing but 75 Newton per meter square. And if you look at the options, you can see that the option B is giving us that solution straight and direct. In this question on heat energy, we are told that there is this 0.5 kilogram of water, okay, that is initially at 10 degrees Celsius. So we have it at 10 degrees Celsius, and it is of 0.5 kilograms. It is completely converted to ice at 0 degrees Celsius. When it is becoming ice, we are going to see it forming blocks of ice, okay? And with that block of ice, what we are having is that it's now at 0 degrees Celsius because that's the temperature for ice. And this is being done by extracting an amount of heat from it. That amount of heat that is extracted from it is 88,000 joules. And then we are giving the specific heat capacity of water to be 4,200 joules per kilogram per Kelvin. And we are asked to find the specific latent heat of fusion of ice. That is our unknown in this particular case. For us to solve this, we need to have an understanding of the processes that are taking place in this change of states, okay? Now, the amount of heat that is being extracted, which is H, will normally be first, it will take the water from 10 degrees Celsius to 0 degrees Celsius, and that energy will be accounted for by saying it is mass and the specific heat capacity of water times the change in temperature. Now, for this change in temperature, because it's a linear scale, initially we are starting from 10, we are ending at 0. So that change is 10 minus 0, which is 10 degrees Celsius. But the changes in Celsius and the changes in Kelvin, they are actually linear. So you can also call it 10 Kelvins, okay? Then we add that amount of energy to the energy that is actually taking place as a reason of the conversion of the water to ice, and that will be the mass multiplied by the latent heat of fusion of ice, which we are asked to find in this particular case. Okay, so if you want to solve this, you can just see that m is common to this left hand side, so we can just say our h over m is equal to c multiplied by change in theta plus L. So that means our L, the latent heat that we are looking for, is the heat over the mass, the amount of heat extracted over the mass, minus the specific capacity of water multiplied by the change in temperature. So we want to put in our parameters now. That H is 88,000 over the mass is 0.5. So if I'm saying I'm dividing by 0.5, it's as if I'm dividing by 1 over 2. Okay, so it's as if I'm saying times 2 over 1. Okay, then minus the specific capacity was given as 4,200. Change in temperature, we have said it is 10. Okay, so we have this as 10. So if we put in this value, this will be 176,000 minus 42,000. Okay, and that will be 134,000. So normally this is joules per kilogram. So that's what we have. But since our answers are given in kilojoules, so we just need to take our 1,000. We just move 1, 2, 3. So this is 134 kilojoules per kilogram. And if you look at our options, it is option C that is giving us that solution. In this question, we are being asked which of the following instruments may be used to measure relative humidity. If you are to look at it, hydrometer is actually used to measure the relative density. Manometer is used to measure the pressure in fluids. So if you are looking for pressure in fluid, either liquid or glass, you can make use of the manometer. But the hygrometer is actually the one that is used to measure the relative humidity, because it measures the amount of water vapor. Okay, so that is actually the one that we can use to measure relative humidity. And then hypsometer is to actually use to estimate the height above sea level, and that is not the case of what we are looking at here. So from all of these, the correct answer is option C. Hygrometer is what is used to measure the relative humidity. In this question on sound waves, we are told that a sound source produces waves in air of wavelength 1.65 meters. If the speed of sound in air is 330 meters per second, we are to get the period of vibration. Now, generally, the velocity is given as frequency multiplied by lambda, but we have the understanding that frequency itself is actually 1 over period. Okay, so we can say the frequency is the wavelength over the period. And now, since we are looking for the period, in this particular question, we can just say we want to cross multiply such that the period will be the wavelength over the velocity. And those are the two parameters that we have. We have been given the wavelength to be 1.65 meters. So 1.65 meters will be 165 over 100. Okay, so you just take the decimal and move it backwards. Then the number of zeros with which you move it backward, you divide with a 1 in front. So we have 165 over 100. Then divided by the velocity. Velocity is 330. So it's dividing 330 over 1. So this will be 165 over 100 multiplied by 1 over 330. So you can do this so that you just want to make minimal use of the calculator whenever you are working on it. If you look at this, 160 times 2 is 320. If you have this additional 5, 165 is actually half of 320. So the period we are looking for is actually 1/200. Okay, and if you want to juxtapose with the options that we have, 1/2 is 0.5. okay, 1/20 is 0.05, and 1/200 is 0.005. so this is nothing but 0.005 seconds. So I'll just use a quick fix to have my understanding that I know 1/2 is 0.5, 1/20 is 0.05, so 1/200 is 0.005, and option B here will be the correct solution that I'm looking for. Here in this question, we're told that a boy who is standing some distance from the foot of a cliff clasps his hands and is hearing his echo 0.5 seconds later. Now, if the speed of sound is 340 meters per second, we have to find how far he is from the cliff. Now, this is ideally what happens when you are sending forth a sound that is going to return with an echo. Now, the distance between the boy and the cliff, if we take that as x, okay, what normally happens is that for him to hear his echo, that means his sound wave have traveled the whole length of x and is also traveled back so that he can hear that echo. So inherently what we are looking at as the total distance for this phenomena is 2x, not just x. Then by reason of understanding of speed, we know that speed is actually distance over time, and in this case we are looking for how far is it, the distance that is covered, which we are getting to see that it is 2x. So that distance is actually the speed multiplied by time, but it is 2 multiplied by that distance that we're actually seeing. So that means what we have is that 2x is equal to the speed, which is 340, multiplied by the time, 0.5. 0.5 is the same as 1/2. So here I can cut that 2 here is 170. Therefore, 2x, 2 times that distance is actually 170. And for us to find x, we can divide both sides by 2, such that we can say our x is, here, these 2 will cut out these 2. Then 170/2, 2 in 17 is 8. Okay, remaining 1, 2 in 10 is 5. So we have this as 85 meters. And looking at the options, we can see the option D is 85 meters. And that is the correct solution here. So then don't make the mistake of using just distance over time and you forget that the echo is actually taking 2 times the distance between the boy and the cliff. Okay, in this question we have to get which of the following quantities is not a vector quantity. Look at that, not a vector quantity. Okay, so let's take them piecewise. Momentum, we know that momentum is actually the mass times velocity, and velocity itself is actually a vector quantity because it's displacement over time. So momentum is not the answer. Force is mass times acceleration. Acceleration is a vector quantity, is even velocity over time, okay? But temperature, temperature is actually the one that is not a vector quantity, and that answer will be option C. Displacement itself is a movement in a specified direction, okay? It's distance covered in a specified direction. So displacement is also a vector quantity. And the correct answer here is that temperature is the one that is not a vector quantity. In this question, we have to find the amount of heat that will vaporize some 50 grams of water, which is initially at 20 degrees Celsius, and the capacity, the specific capacity of water we are given as 4.23 joules per gram per Kelvin, and then the specific vaporization of water is 2,260 joules per gram. Student, first thing to note, look at the unit you are given. Here, the specific heat of vaporization is given in joules per grams. Here, the specific capacity of water is given in joules per gram per Kelvin, and the mass of the water was also given in grams, 50 grams. That means already this particular question, they are flattened out the unit so that you don't need to bother converting to kilogram. Already we are using, you know that this is not actually 4.23, it's 4,200 joules per kilogram per Kelvin. So they factor that in already, so you don't need to convert to kilogram. Just work with the grammage because you need to know the consistency here so that you can continue your work in that order. Okay, so that's the very first thing to note. So we have these 50 grams of water and we need to vaporize it. So let's say we have some heat that is being applied to this, okay? So we want to vaporize it and get that out. So we need the amount of heat energy that we need to vaporize it. What we need to understand is that what is happening here is also twofold. First, that amount of heat will take this water from this particular temperature of 20 degrees Celsius to 100 degrees Celsius, and it is still at water. It will take it to the boiling point. Then at boiling point, that same mass of water we need to multiply by the specific heat of vaporization of water, okay? So it is these two set of processes that will constitute the amount of energy that is required to vaporize. Before you can vaporize, you need to get it first to the boiling point. At that constant temperature of 100 degrees Celsius, you now continue to supply that heat energy that will turn the liquid into vapor. So this is what we have here. And if you want to just input everything, we will know that our change in temperature for the body initially at 20 degrees Celsius and later getting to 100 degrees Celsius, change in temperature is going to be the difference of the two, and that is 80 degrees Celsius. But ideally we are working in Kelvin, but for the change in temperature, the change in Celsius and the change in Kelvin is linear. So 80 degree change in Celsius is also 80 Kelvin change, okay? So I can say my H, if I'm to supply the parameters, the mass is 50 multiplied by the change in temperature, that is 80, okay? Multiplied by the specific capacity of water, here we have it as 4.23, okay? Plus, again, the mass, that's 50 grams, multiplied by the specific heat of vaporization of water, that is 2260 as given. So for this, let me just use my calculator straight. I have 50 times 80 times 4.23. That's 16,920. That's 16,920 plus a 50 multiplied by 2260. So 50 multiplied by 2260. That's 113,000. So plus 113,123. So if I'm to add these two together, I'm going to have 113,000 plus 16920. 129,920 joules. Okay, is that in our answer? Okay, that's not in our answer. We have seen this 130 joules, which is the approximate value of this particular expression that we have here. So we can say our H is approximately equal to 130,000 joules, and that makes option D our answer in this particular case. This question is actually a test of our understanding of the concept behind RLC circuit at resonance. Because I've been told that in an RLC circuit, we are having the voltage across the resistor and inductors to be 30 and 40 volts respectively. So voltage across resistor and inductor, this is resistor, the voltage is 30 volts. And the one across the inductor is 40 volts, okay? So we are looking for the voltage across the capacitor, okay? Now, you don't need to calculate anything here because at resonance, that is the keyword that we are having here. At resonance, what we normally know is that the inductive reactance and the capacitive reactance, they are equal, okay? If they are equal, that means that the same current is actually passing through this circuit, okay? And that same current passing through the circuit will mean that the same voltage drop will be observed across the inductor as well as across the capacitor. So what we are going to have is that since we are talking about at resonance, the voltage of the inductor is also going to be the voltage across the capacitor, and already we have been given as 40 volts. So looking at our options, the voltage across the capacitor is also going to be the voltage across the inductor, and that is option B. So it's our understanding of that can help us look at this question on the fly. within 10 seconds, we'll pick our answer, we'll save time, and we'll move on to solve more questions. Here, we have been told that if frequency of an emitted X-ray is 1.6 exponent 16 Hertz, we have to find the value of its accelerating potential. We are given E to be 1.6 exponent minus 19 joules and H to be 6.63 exponent minus 34 joules per second. Now, generally, there is the formula that we have here to actually get this accelerating potential, that HF is actually equal to EF, or that particular F, because we know that generally the speed, frequency times lambda. So frequency itself can become C over lambda, so that we can write this equation and say we have just HC over lambda is equal to EV. So either of these two, the ones that are best fitting for the parameters that we are giving, we are going to make use of. In this particular case, we are given F already. Frequency, we are told, is 1.6 exponent 16 Hertz. Then we have E to be 1.6 exponent 19 joules, and we have Planck's constant to be 6.63 exponent minus 34 joules per second. So we are looking for the accelerating potential V, meaning that here, since we have F, we have H, we have E, we're only looking for V. Then that is quite interesting for us, because we can just say our V will be HF over E. So if you want to just carry that out, you can say V is equal to, what is H? 6.63 exponent minus 34. Our F is 1.6 exponent 16. And we are dividing by E, which is 1.6 exponent 19. Very interesting. 1.6 will cut out, and then, okay, this is good now. We have our V to be 6.63 times 10 raised to power. Let's apply the law of indices here. A single 10, we have minus 34, then we have plus 16. Because this is division, that is minus, okay? And we have minus 19. So the two minuses will multiply each other to become plus 19. So we have this to be 6.63 times 16 and 19, that will be 35. 35 minus 34, okay, that's just a single 10. So this will be 66.3 volts. So if you look at our options, we are seeing option C is 66.3 volts, and that is the answer here. In this question on half-life, we are told that if the fraction of the atoms of a radioactive material left after 120 years is 1/64, we are to find the half-life of the material. Now, generally, the half-life is given as the T over N, okay, where T is the amount of time that has been spent already. But also, we also know that the fraction left after that particular time is 1/2 raised to power n, and n is actually the number of half-lives, okay? And already we are being told here, look at this 1/64, we are being told that that is the fraction that is left, meaning that if we want to substitute, we have 1/64 is equal to 1/2 raised to power n, okay? So we can just say here that, of course, if you cross multiply, 2 raised to power n equals to 64, okay? And then we know that 64 itself is 2 raised to power 6, because it is 2 in 6 places. 2 in 3 places is 8. 8 times 8 is actually 64. So with this, we can say our n, since the bases are equal, the power should be equal. N is equal to 6, okay? And then if you find n to be 6 already, we can make use of that in T half is equal to T over N. The time we are giving is 120 years, and N we have gotten to be 6. So that means that the half-life is 120 years over 6, and that is nothing but 20 years. So if you look at the options, you can see that option B is 20 years, and that is our answer here. In this question, we are told that a certain radioactive source emits radiation that was found to be deflected by both, look at that, that's the keyword, both magnetic and electric fields. Then the radiation is which of the following? Is it beta, gamma, X-rays, or ultraviolet rays? The only radiation that will be deflected by both magnetic and electric fields in this particular set of options is option A. So as good as it gets. Once you understand that, you can just pick your answer as A and you are good and done. In this question here, we are being asked that the inner diameter of a test tube can be measured accurately using which of the following instruments? Is it a micrometer, screw gauge, a pair of dividers, meter rule, or pair of vernier calipers? Okay, so I want to show us the picture of the solution, and it's just like this. It is the vernier calipers. Generally, you can say you want to measure some spherical object with this normal scale, okay? But then, if you want to measure internal diameter, like here, we have the internal diameter of this particular beaker, which is just almost the same thing as a test tube. The test tube is just narrower. It is these other functions of the vernier calipers that can actually use to measure that, and you look at the reading and you'll be good and fine. So the solution here is option D, a pair of vernier calipers. Here in this question, we are told that two bodies have masses of ratio 3:1. So this is one body. You have masses, let's say that mass is 3, here the mass is 1. Then the experience forces which impart to them acceleration in the ratio 2:9. So a force, some force is giving an acceleration here 2. Now when they say respectively, that means the order is important. The first one they talked about is 3:1. Second one is 2:9. So 3 and 2 goes together, 1 and 9 they goes together. So that is for the first case. And in the second case, some force is also being applied that render acceleration to be of order 9. So we have to find the ratio of the forces that the masses experience. I think this is as good as it gets. In the first case, you can just say this is F1, this is F2. F1 will be mass times acceleration, and that will be 3 times 2. So we can say this is 6, okay? And F2, it will also be mass times acceleration, but now we are looking at this case, okay? And that will be 1 times 9, that is 9, okay? 6 newtons and 9 newtons. So if they are looking at the forces, now if they are looking at the ratio of the forces, the masses experienced, that will be F1 ratio F2. And F1 ratio F2 in this case will be 6 ratio 9. 3 can go in them, so we have 3 in 6 is 2, 3 in 9 is 3. 2 ratio 3 will be the correct solution here, and if you look at option C, that is there as our answer. Here we are told that the particle of mass exponent minus 2 kg is fixed to the tip of a fan blade which rotates with angular velocity of 100 radians per second. Now, if the radius of the blade is 0.2 meters, so we can have our radius here. This is 0.2 meters. That's the radius, okay? And then we have to find the centripetal force, okay? So, the mass was given to be 10 raised to the power minus 2 kilograms. And what we need to note is that we are looking for the centripetal force in this particular case. But normally we know that that force is mass times acceleration. So the onus is lying on us to find the acceleration in this particular case. And acceleration normally is velocity square over r. And for this centripetal motion, that velocity is the radius multiplied by the angular velocity. So we can have that raised to the power 2 and over r. So this will be rw square. That is the acceleration. And from the question, we've been given the angular velocity to be 100 radians per second. And we have the radius as 0.2 meters. So if we just want to put everything together, we know that our force will now be mass times the radius multiplied by the square of the angular velocity. So bringing in all the parameters that we have, this will just be exponent minus 2 times radius is 0.2 times w raised to the power 2. So we have 100 raised to the power 2. So we can just have 10 raised to the power minus 2 times 0.2 times 100 itself is 10 raised to the power 2. Then with this new power, we have 10 raised to the power 4. So this will be 0.2 times 10 raised to the power 4 minus 2 is 2. So, okay, 0.2 times 100, and 0.2 times 100 is 2 times 10. So, the force that we are looking at is actually 20 newtons, okay? So, from here, I just say 0.2 times 100. The first 0 will take care of the decimal place. So, we have 2 times 10, and that will be 20 newtons. So, option B here will be the correct answer as the solution in this case. In this question on momentum, we are told that a lead bullet of mass 0.05 kilogram is fired with a velocity of 200 meters per second into a block of mass 0.95 kilogram. So we are given that the lead block can move freely, and we are to find the final kinetic after impact. So inherently, what we are being asked is to find the kinetic energy, which you know is actually half mv square. We need to find the value of the velocity, because we are already given in the question that we are having initial velocity of the bullet ub is 200 meters per second, whereas the initial velocity of the block, let me call k, that is 0 because it is at rest. Okay, and there is a final velocity v, which we are going to use to evaluate the kinetic after the impact that we are going to be looking at. By looking at the law of conservation of momentum, we know that the mass of the bullet multiplied by the initial velocity of the bullet, that's the momentum before collision, plus the mass of the block multiplied by the initial velocity of the block, but that initial velocity, we set it is 0, and when 0 multiplies anything, that is going to be 0, okay? That is going to be after the impact. Their masses are going to combine, so we have the mass of the bullet plus the mass of the block multiplying the common velocity with which they will be moving. Okay, so that common velocity will just be, here we have mass of bullet multiplied by the initial velocity of bullet over the sum of the masses, the mass of the bullet plus the mass of the block. So if we want to put in these values, mass of the bullet is 0.05 times initial velocity, that's 200, okay, over the mass of the bullet plus the mass of the block. Okay, so yeah, I think this is 1, 0.05 plus 0.95, that is 1. So we have 0.05, that v is 0.05 is like we have 5 over 100 times 200 over 1, because this denominator is actually 1. We don't need that again. So this is just 5 times 2. So the final velocity is 10 meters per second. So we can use this formula now to find the kinetic. So that kinetic will be 1 over 2. What is the mass? It is 1. It's the mass of both the block and the bullet. And we have already gotten that here to be 1. So we have multiplied by 1. Multiplied by the square of the velocity, that is 10 raised to the power 2. So that k will be 1 over 2 times 100, and that will be 50 joules. So looking at our options, we are seeing 50 joules as option A, and that is the correct answer in this case. In this question, we are told that a ball of mass 0.1 kilogram is thrown vertically upwards with a speed of 10 meters per second from the top of a tower, which is 10 meters high. So we can neglect air resistance and find the total energy just before hitting the ground. So if we want to put in all our parameters, we have been told that the tower is 10 meters high. So this is 10 meters. So h will be 10 plus this particular distance that, okay, we are going to be looking out for. We will call that s, okay. Then we are told that the ball was thrown with an initial velocity u was 10 meters per second. When it gets to its maximum height, before it starts its journey downwards, the velocity there will be 0 meters per second. Okay? So, looking at this, for the upward journey, if you just take a consideration of the upward journey, you can use the equation of motion to try and help us solve that, because we need to find the value of s. That height is actually 10 plus s, and if we can get the h, we can use the energy is equal to mgh Okay, since there will be a conversion of the potential energy at the top to the energy downward, okay, that is actually going to be the kinetic energy with which you move downwards. So if we get that potential energy, it's also the energy just before the body will hit the ground. So we can find S and put it here and know that we have our solution. So we want to just employ the equation of motion. We can make use of the fact that V square is U square plus 2AS. Now, A in this particular case, for this, A is actually minus G. On this upward movement, A is actually minus 10 meters per second square. Why is it that? Because the body is moving upward, moving against the pull of gravity. So it's going to be negative. So if we just put in those values, final velocity is 0, initial velocity is 10 meters per second square. So we have 10 raised to the power 2 plus 2 multiplied by acceleration due to gravity is minus 10, minus because it's going upward, and then we are looking for S. This will be 100 minus 20S. So S will be 100 over 20, and that will be 5 meters. So very, very interesting. We can now say that H is 10 plus S, which is 10 plus 5, and that is 15 meters. So the energy that we are looking for, that energy is actually mgh. That will be mass. What is its mass? 0.1 times acceleration due to gravity 10 multiplied by the height h, which is 15 meters. This is nothing but 0.1 times 10 is 1, 1 times 15 is 15. So we have this as 15 joules. And looking at the options, we have 15 joules as option C to be the correct answer in this case. Here we're told that a car of mass 800 kg attains a speed of 25 meters per second in 20 seconds. Then we have to find the power developed in the engine. So we have our parameters here, that the mass is 800 kilograms. Then the speed is 25 meters per second. And the time that we have working here is 20 seconds. So we are looking for power, okay? Now we know that power itself is work done over time taken, but work is force times distance over time. So we can say force itself is also mass times acceleration. Then we'll still have distance over time here. And if we want to put that into correct perspective, we have mass. Acceleration is velocity over time. Distance is actually, this distance over time is actually velocity. So what we are having inherently is the mass multiplied by the velocity square over time that we are looking at. And those are the parameters that have been given here, okay? If we want to put them in appropriately, we can say the power towards the mass is 800 times velocity is 25. So we have it in two places, over the time is 20. 20 year 1, 20 year 40. Now 40 times 25 is 1000. 1000 times 25 is 25,000. Okay. But looking at the options, we don't have 25,000. So we need to take it into scientific notation. We can move our decimal place from here. I see we have 0.0. So we have 1, 2, 3, 4. So that would be 2.5 times 10 raised to the power 4 watts. And we can see from our options, option B is corresponding to that as the correct solution. When the brakes of a car are applied, okay, we are looking at what happens to the frictional force, looking at these options that we are given in this particular case. Okay, so let's look at what is going to be happening here. Okay, so number one, is that frictional force a disadvantage because in the direction of the motion of the car? No, it's not in the direction of the motion of the car. If the car is accelerating like this, the frictional force is actually acting backward like this. Okay, so that first one is not it. In the second case, it's a disadvantage because it's in the opposite direction of the motion of the car. Okay, yes, it is in the opposite direction, but what is our aim? Our aim is to bring the car to a stop. That's why we're applying the brake. So everything that we work to bring it to a stop, to draw it back so that it is actually standing still, is going to be an advantage. So option B is also not the correct thing. Now, C is an advantage because it is in the direction of the motion of the car. No, it's not in the direction of the motion of the car. So D, it is an advantage because it is in the opposite direction of the motion of the car. Yes, because frictional force is a force that tends to oppose motion. And so if you're applying brake and it's also opposing the motion, that means our aim of bringing the car to a stop will be achieved very, very seamlessly. It's going to contribute to that. So option D is the correct answer here. We have this question that the stress on a wire was given to be 10 raised to the power 7 Newton per meter square. Okay, and then the wire is stretched from its original length of 10 centimeters. Length originally is 10 centimeters. Okay, if you want to convert that to meters, that will be 10 over 100 meters. So that will be 0.1 meters. Okay, then it is stretched from that original length to 10.05 centimeters. So the extension is actually the difference between the two. So we have 10.05 centimeters minus 10 centimeters. That will be 0.05 centimeters. And that will be, so that will be 5 over, we move our decimal place, 1, 2, 5 over 100. That is taking this as a fraction. Now I want to convert to meters. I need to divide by 100 times 1 over 100 meters. Okay, so we are looking for the Young's modulus. The Young's modulus Y is actually stress over strain. That's the formula for the Young's modulus within the parameters that we are given here. But we have stress, we don't have strain. Strain itself we can get by saying it is the extension over the original length. And in this case, what we have is 5 over 100 times 1 over 100, which is the extension, divided by 10 over 100, which is the original length that we got as 0.1 meters. But I can just as well multiply it and take care of the division. So I have times 100 over 10. So now I can just divide like this. 100 is going here. So I can take this as 5 over, this is 10 raised to the power 2. With this 10 raised to the power 3. That is the strain. Okay. Then in that case, I can just find the Young's modulus Y to be the stress, which we are given as 10 raised to the power 7. Okay, over 1 divided by the strain, which is 5 over 10 raised to the power 3. So this will become 10 raised to the power 7 over 1 times 10 raised to the power 3 over 5. Okay, so this will be 10 raised to the power 10 over 5. And that will be, if I take 110 out, okay, it will be 2. Then the remaining will be raised to the power 9. And the unit is Newton per meter square. So this is interesting here. Look at what I did there. I have 10 raised to the power 10, okay, over 5. So if I just take a singular 10 out, I will have 10 raised to the power 9 remaining. That singular 10 that I took out divided by 5 is 2. So the correct answer here is option D. Now these are means of actually working with this in such a way that you are getting tips to resolve your question without needing to pause to go and be checking your calculator. If you can do your fractions on the fly like this, then you are going to gain speed, you are going to gain traction, you don't need distractions. You are also not going to be susceptible to mistakes when you are pressing your calculator. So just apply all this and surely you'll find them useful and you'll be good to go. We hope you are really enjoying this video, and if that is the case, don't forget to like the video and also subscribe to the channel for more videos like this that will break down your work and give you the academic excellence that you have always been looking for. Alright. A solid object weighs 10 newtons in air, 6 newtons when forcefully immersed in water, and 7 newtons when fully immersed in a liquid X. Our mandate is to find the relative density of liquid X. And in this particular case, we can take it as the loss of weight that we observe in liquid X over the loss of weight that is observed in water. And with the parameters that we are given, we can just look at that holistically to say that relative density will be, now what is the loss of weight in liquid S? When the object was in the air, it was 10 newtons. Okay, when it is in liquid X, it was found to be 7 newtons. So the loss of weight is 10 minus 7. Okay, then the loss of weight in water, of course, the weight in the air still remains 10, and then the weight in water was 6 newtons when forcefully immersed in water, so it is 6 newtons. So this is what we can use to get this relative density of the liquid X. 10 minus 7 is 3. 10 minus 6 is 4, and 3 over 4 is going to be our answer as option C in this case. When the temperature of a liquid increases, its surface tension does what? What happens to the surface tension of a particular liquid that the temperature is being increased? Okay, so you can actually get the solution out as you wish, but generally what happens is that when you are increasing the temperature, there's increase in the kinetic energy of the systems, and as a result of those increase in kinetic energy, molecules tend to be in more excitation state such that they break the coercive force that is at the edge, at the surface of the liquid. And as that is taking place, the surface tension, which is a measure of how the liquid can resist another third-party object that is being placed on it, okay, is that surface tension that we say, okay, no, we don't want you to be here, we just stay on top. They want to resist the immersion of another liquid. That surface tension, once you are increasing the temperature, that surface tension is actually going to be decreasing, okay? So the more you are increasing the temperature, the surface tension is actually reducing. And you can also achieve the same thing by putting detergent in water. So if you have a liquid and you are putting detergent there, it will also reduce the surface tension. So looking at all the options that we have here, what happens is that when temperature of the liquid increases, the surface tension decreases. Option A is your answer there. A gas at a volume V0 in a container at pressure P0 is compressed to 1/5 of its volume. So we are being asked what will be its pressure if the magnitude of its original temperature T is constant. So we are noticing that the temperature T is being kept constant here, but we are told that there is actually a set of parameters that initially this is V0, okay, and it is being considered at pressure P0. But now what we are having is that V0 had been compressed to 1/5 of its volume. So this is 1/5 V0, and we are being asked what will happen to the pressure. Okay. Normally, by reason of the gas laws that we have is understanding that we have P1 V1 over T1 is supposed to be a constant, okay? Now we are being told that temperature is being kept as a constant, so we can do away with temperature. So we just have P1 V1, which you can relate to any other P2 V2. This is a linear relationship. So if we have a decrease in volume, those are saying the whole system must be actually maintaining its consistency. If we drop the volume now by 1/5, that will actually take effect on the pressure as 5 pressure. Okay, so if we just want to look at that via calculation, like we said, we have our P1 V1 is equal to P2 V2, and here in this particular case, what is our P1? Let's say our P1 is P0, our V1 is V0, is equal to, in the second case, what is our P2? That's what we are looking for. Let's call it P. What happened to our V2? It is 1/5 multiplied by V0. So if we just cut out these that are actually equal to each other, then we have P will be 5 here, we multiply the P0 to have it as 5 P0. So inherently, if you reduce the volume by a particular parameter, that parameter will be multiplying the pressure for the system to still maintain that gas law of the pressure law. So the pressure will be multiplied by a factor of 5 if the volume has been reduced by a factor of 5. In this question, we are told that a piece of substance of specific heat capacity 450 joules per kilogram per Kelvin falls through a vertical distance of 20 meters from rest. So let's say it is coming from rest, and this is 20 meters. So this particular body is falling from here and just falling down straight here, okay? So it has some specific heat capacity. C is 450 joules per kilogram per Kelvin, and then that's 20 meters. We have to find the rise in temperature of the substance on hitting the ground when all these energies are converted into it. So that statement is very key for us, that here we are having a conversion of energy from potential energy to heat energy. Okay. So now with the parameters we are given, we are noting that the formula for potential energy is mass times acceleration due to gravity times height is equal to the formula for the heat energy, mass times the specific heat capacity multiplied by the change in temperature. Interestingly, the masses they will cut out, so that we are not giving the mass is actually that we don't need it. And we are looking for the change in temperature. That change in temperature is going to be the mass, the acceleration due to gravity multiplied by h over the specific heat capacity. So if you want to look at that, that will be 10 multiplied by h is 20 over c. What are we giving as c? 450. So you can just cut 5 here. 5 in 10 is 2. 5 in 45 is 9. So we have 4 over 9 as a change in temperature for this particular body system as stipulated. So option B will be our correct answer. Here we have these 4 statements. Our being asked that which of the above combinations are peculiarities of the boiling point of a liquid. So let's go through them one after the other. First, a liquid boil when its saturated vapor pressure is equal to the external pressure. Okay, that is true. That is true. The point at which you are having a liquid boil is the point at which its saturated vapor pressure is equal to the external pressure. So 1 is correct. In the second case, dissolved substances in pure water lead to an increase in the boiling point. That is also true because what those dissolved substances do, what they represent is as if they are having impurities. So when you have impurities in pure water, then the normal heat that the water could have taken to actually get to its boiling point will need to also be shared with that additional substance that you have added to it. So that substance will also take some of the heat. So of course the boiling point will be increased. It will not just be at the normal boiling point of water. It will not be at 100 degrees Celsius. You need to add more for that mixture. Now is a mixture, okay? Then option 3. When external pressure is increased, boiling point increases. That is also true. As you're adding pressure from the outside into a system, that means the boiling point is also going to increase. So 3 is also right. Okay. The last sentence, dissolved substance in pure water decreases the boiling point. No. That's just a negation of the option 2, the statement 2 that we just look at. So statement 4 is wrong, and then the correct answer, they say which of the combinations are peculiarities of the boiling point of a liquid. The correct answer would be A, 1, 2, and 3 only. Here we're told that the temperature gradient across a copper rod that is having thickness 0.02 meters maintain at two temperature junctions of 20 degrees Celsius and 80 degrees Celsius respectively is what? Okay, so for us to be able to solve this, we should know that that gradient, that temperature gradient that we are talking about is actually the change in temperature over the thickness of this particular copper that we are looking at. And if that is the case, we are going to say that the change in temperature is from 20 to 80. So 80 minus 20, that is 60. So that means that what we are going to have is 60 Kelvin over the thickness. The thickness is 0.02 meters. Now, why did I say Kelvin? Because it's a linear change in Celsius that we also observe in Kelvin. So instead of saying you want to convert Celsius to Kelvin, 20 to Kelvin, 80 to Kelvin, then find the difference. The difference will still be 60K. So this is the same as if you're having 60 over 1 divided by 0.02 is 2 over 100. So if you want to evaluate that, you can just say this is nothing but 60 over 1 times 100 over 2. So 2 here 1, 2 here 30. 30 times 100 will be 3000, and that will be 3 times 10 raised to the power 3 Kelvin per meter. And looking at our options, we can see that that is featured in option B as the correct solution. Okay. In this question on heat energy, we are to find the mass of ice that will melt when 2 kg of copper is quickly transferred from boiling water to a block of ice without heat loss. We are given the specific capacity of copper to be 400 joules per kilogram per Kelvin, and the latent heat of fusion of ice to be 3.3 exponent 5 joules per Kelvin. So what we need to note first and foremost is that when we are moving the 2 kg of copper, we are told that it is moving from boiling water. That means its initial temperature is 100 degrees Celsius, because that's the temperature of boiling water. So if it's coming from there, that will be its temperature. And now, what is the temperature for ice? That is 0 degrees Celsius. Okay, M is what we are looking for. So the mass for ice, we don't know. Now, what we should notice here is that what we're having is a transfer of heat energy from the hot copper to the cold water. Okay, so what we just need to do is to find the heat loss and equate it to heat gain. Okay, so we'll see that it is the copper that's actually losing it. So we can have the mass of copper multiplied by the specific heat capacity of copper multiplied by the change in temperature that the copper is going through. That's going to be the heat gain by the ice. Now that ice is not going to have a change in temperature. Why? Because it's only going to maintain that temperature of 0 degrees Celsius until it melts from ice to water. At that point, there's no change in temperature. So we can only have the mass of the ice multiplied by the latent heat of fusion of ice. So what we are looking for is the mass of the ice. So if you want to get that, you can just say the mass of ice is equal to the mass of the copper multiplied by the specific capacity of copper multiplied by the change in temperature of the copper over the latent heat of fusion of ice. So if we want to bring in all our parameters, we can just say our mass of the ice is, what's the mass of the copper? We are given as 2 kg. So this capacity of copper was 400. Change in temperature, the copper was moved from a boiling water, so it is operating at 100 degrees Celsius there, moved to this particular ice. Ice is at 0 degrees Celsius, so the change is 100 minus 0, which is 100 over the latent heat of fusion of ice. That's 3.3 times 10 raised to the power 5. Okay, so if we are to look at this will be 2 times 400 is 800. 800 times 100 will be 8,000. 80,000. 80,000 is 8 times 10 raised to the power 4 over. Now we have 3.3. We are not having anything 10 here, so we can as well express this in such a way that the 10s will cut out. So 3.3 times 10 raised to the power 5 will be like 3.3 times 10 times 10 raised to the power 4. 3.3 times 10 is 33, so this is 33 times 10 raised to the power 4. So I can cut out this 10 raised to the power 4 to say this is nothing but 8 over 33 kilograms. So where is that option? You can see option A is 8 over 33 kilograms. In this question on waves, we are told that the equation of a wave traveling along the positive x direction is given by this, okay? And then we have to determine the angular velocity of the wave motion. So your understanding of what we are talking about, the equation of the wave, is critical here, because that equation is given as y to be a sine omega t minus phi, okay? And then if you have to compare these two, you compare it with y is 0.25 exponent minus 3 sine 500 t minus 0.025x. We can see that by comparison, this is w and this is the coefficient of t. Both are the coefficient of t. So w, which is the angular velocity, is nothing but 500. What is the unit? That will be radian per second. But if you look at the option, we don't have that. We only have 5 times 10 raised to the power 2, which is the same thing, radian per second. The other thing you could have noted is that this particular equation, we could have written it as y is a sine 2 pi ft, okay, minus 2 pi over lambda x. So in this particular case, you can also do this, and of course w is actually 2 pi f, so you can also use that. Maybe sometimes you need to find frequency, or using this second parameter here, you need to find the wavelength. See, so just note that. But here, the correct answer out of these options is option C. If a sound wave goes from a colder region to a hotter region, what happens to its wavelength? Okay, so let's consider this critically. what we notice is that if you are looking at a cold air region, what happens to the air waves in that particular type of region? What you will notice is that for those regions, the molecules of air, they are densely packed, and if they are densely packed, then sound waves will generally not be able to go far, and then it will not be able to travel so much. When you get to a hot region, what you are going to have is that the air particles are not so densely packed, and because of that, your sound waves will be able to actually travel further than before. So what happens is that for this cold region and for this hot region, their peculiarity is that the sound wave, when it gets to the hot air region, so when the sound wave gets to hot region, the wavelength will just increase. It will be able to move further, it will be able to propagate better, because there is not much resistance that is going to be feeling as a reason of the atmosphere. In the cold region, the molecules are choky, they actually restrict, so they can muffle even those sound waves. But in the hot region, they can go as far as you can imagine. Okay, so the correct option is option A. The lowest note emitted by a stress string has a frequency of 40 Hz. So that means that the fundamental frequency is 40 Hz. Then we have to get how many overtones are there between 40 and 180 Hz. You can just take an iteration that for the second overtone, that will be 2 times F0, okay? So that will be 80 Hz. And then we can go on that the third will be 3 F0, and that will be 3 times 40, that will be 120 Hz. Then the fourth will be 4 F0, that will be 4 times 40, 160 Hz. And then the fifth will be 5 times F0, and that will be 5 times 40, that will be 200 Hz. So within the region that we are given, 40 and 180, we can see that all we have is these three, okay? These three are what are lying between. Now we need to note those words. They said between. So since they are saying between, we don't need to include 40 Hz. And of course, 200 is greater than the 180, that is the upper limit that we are given. So in this question, the correct option to pick will be option B. 3 is the answer. We are told that a man stands in front of a plain mirror. Okay. Let's say this is the mirror and this is the man. And then, after that, we are told that if the mirror is moved 1 meter towards the man, the distance between him and his new image, okay? If the mirror is moved 1 meter to the man, that means we are having a change in location like here. That mirror has been moved. So now the distance between the man and the mirror is 3 meters, but we are being asked the distance between him and his new image. So where will the image of a plain mirror be formed? It will be formed 3 meters behind the mirror. So the man is going to be here. Okay, that's where his image will be. So the distance between the man and his new image will be 3 plus 3, and that will be 6 meters. So 6 meters from the option is option C, and that is the correct answer here. In this question, we are told that the inside portion of part of a hollow metal surface of diameter 20 cm is polished. The polished portion will therefore form a what? Wow, so this is a very interesting question in which you need to actually understand how mirrors they are made. So we are given something like this, and we are told that this is actually a hollow metal sphere, and normally if we are to continue that diagram, we have something like this. Okay, so the inside portion of this hollow metal sphere, that means inside portion, this is inside, right? That is polished. Okay, and the diameter here, the diameter from this particular point to this point, that was given as 20 centimeters. So we want to get the polished portion. What is it forming? What type of mirror is it forming? Now, for this particular case, what you are going to notice is that because this inner region is polished, that is not going to be the region that will be acting as a mirror. It will be the other side. The side you polish will be the one that is going to reflect back. It's going to push back what is going. So it is the other side that is going to be used as the mirror. So that means what you're having inherently is that this side is where light rays can come in. Now we are told that we have the diameter there. Normally, this will be the center of curvature, and that center of curvature will be half of the diameter that we are given. So from here to that, we have that to be 10 centimeters, but this is the center of curvature. The focal length is between the center of curvature and the pole of the mirror. And if we call this F, distance from F to the pole is actually half of this 10. This is 10. So the remaining 1 here is actually 5. So already we are seeing that the focal length is going to be 5 centimeters. And the other question is that what type of a mirror is this? For heat, what we are having is that we have those rays of light returning there from the focal length. They will actually reflect back light rays just as shown. Okay, so what we are having here is nothing but a diverging mirror. Now, a diverging mirror is also known as a convex mirror. It's the other case for lens. The diverging lens is actually the diverging or the concave lens. But for mirror, you have a diverging or a convex mirror. And this is like this. So what we are going to be having is a convex mirror with focal length of 5 centimeters. The diameter was what we are giving. Half of it will be the center of curvature. Okay, but it is half of that is the focal length. So the correct option out of all this option is option C, convex mirror of focal length 5 centimeters. In this question, we are told that the velocities of light in air and in glass are 3 exponent 8 meters per second and 2 exponent 8 meters per second respectively. Now, if the angle of refraction is 30 degrees, we are to find the angle of incidence. So here, inherently, this is the angle of incidence theta. Okay, and this is the angle of refraction that we are given as 30. Already, we are told that the speed in here is 3 exponent 8 meters per second, and the speed in glass is 2 exponent 8 meters per second. So, the formula for the refractive index will really help us here. And that formula is saying that we can either have it as sine I over sine R, and that is also the speed in here over the speed in glass. Okay, so if you want to just make use of this, we already know sine R. Okay, since we have the theta for R, we are looking for sine I, and look at the question. We have to find the sine of the angle of incidence, not the angle of incidence. Then you can equate that to the speed in here and the speed in glass. If we are to do that, we are just going to say that our sine I that we are looking for is over sine R is 30. That is equal to the speed in here, 3 exponent 8 over the speed in glass, 2 exponent 8. Okay, so sine 30 is actually 1 over 2. So these two can cut, so that the sine I we are looking for is 3 over 2. This sine 30, which is 1 over 2, when it comes to that other side, I will say times 1 over 2. So this is nothing but 3 over 4. And 3 over 4, if you are to convert to a number in decimal place, that would be 0.75. So here, among the options, option D, 0.75 is the correct answer for this question. In this question, we are looking at the astronomical telescope, and we are saying that an astronomical telescope is said to be in normal adjustment when what? So for the astronomical telescope to be in normal adjustment, we'll have the lens, okay? And if you are looking at the lens like that, it's actually looking far into space. And when it's looking into space like that, what we need is a set of some things that we should be able to look at holistically. Like we are seeing some Mars and we're having some star. We can look at them all. So the telescope will be in normal adjustment, not when the eye is accommodated, no. When the focal length of an object is longer than that of the eyepiece, no. When the final image is at the near point of the eye, no. It is actually in normal adjustment when the final image is at infinity. So the final image we are looking for will have to be at infinity, and then we can have that the object focus of this lens is also landing at the eye focus of the second lens, and then the final image will be at infinity. So option D is the correct solution to this, that it will be in normal adjustment when that final image is at infinity. Alright. In this question, we are told that a 2 ohm inductor has negligible resistance and is connected to a 50/pi AC supply. So we have to find the reactance of the inductor. So how do we go about finding the reactance of the inductor? The reactance of the inductor is actually given as 2 pi F multiplied by the inductance of the inductor. And that inductance we are already given as 2 Hertz. That frequency is the frequency of operation of the AC supply. So we have to put all those in perspective. We have 2 multiplied by pi, multiplied by that frequency 50/pi, then multiplied by the inductance, which is 2 Henry. Okay, so we just cut all of this. We have pi multiplied by pi. 2 times 50 is 100. 100 times 2, that is 200 ohms. So the reactance of the inductor is nothing but 200. In this question, we're told that the load extension graph, so this is load, okay, on the vertical axis, and on the horizontal axis, this is the extension. But before we go ahead, let's just look at the unit that we're being given. Load is given in newtons, and extension is being given in centimeters. So for us not to make any mistake, we need to just know that, so that if we want to use the appropriate unit, we should convert as appropriate, okay? Now that's quite interesting that we're being asked to find the work done on stretching the material. Normally in mechanics, we know that work is a product of force times distance, okay? But in this particular case, we are looking at a graph in which at the initial starting point, the load, which is the force being exerted, is actually 0, and the extension, of course, since the load is 0, the extension is also 0. But as a reason of the fact that the load is being increased, the extension that is also produced is being increased, and that is why we have this. The shaded region is the graph that corresponds to that, because ideally, if you just want to use the product of force and distance, you can say 4 times 1, and that is 4. No, that will not be right, okay? In this case, originally it started from 0. So for the solution to this question, that work will be the area under the graph. Area under the graph is going to give us the work done for this particular load extension graph that we are given, and that will be given as, look at this, this is nothing but a triangle, so it is half multiplied by the base multiplied by the height. Or looking at what we are having here, we are losing load in newtons and extension, so we are going to have F multiplied by E. But again, what is our F? We can now go ahead to try and solve this. That F, as we have been given on the peak, it is 4, and that is 4 newtons. But the extension, look at this, the extension that we have is 1 centimeters. And you know that in using the standard unit, you cannot use centimeter, you need to convert to meters. So that is nothing but 1 times 10 raised to the power minus 2 meters. Okay, it's just as if you are dividing as 1 over 100, and that will now be in meters. But I want to write it just as 1 times 10 raised to the power minus 2, such that we can find the work done in this particular case as 1/2 force times extension, and if you want to evaluate that, that would be 1/2 multiplied by the force, that is 4 newtons, okay, multiplied by the extension, that is 1 times 10 raised to the power minus 2 meters. So these two can cut this 4, so we have to so that the work done will now be given as 2 times 10 raised to the power minus 2, and what is the unit of work? That will be joules. That's the newtons multiplied by the meters, that will be joules, and this is going to be the solution for this question. Here we're asked to name 2 artificial satellites, and we're also being given that a geostationary satellite moves in an orbit of radius 6,300 kilometers, and we have to find the speed with which it moves in the orbit. Very good and fine. In the first case, you just need to know these artificial satellites so that you'll be able to answer this. And some of them are just as listed there. You have Sputnik, GPS, Minster, GOES, and since we are just asked to name 2, any 2 will suffice. Okay. Now, in this second question, we are being told that the geostationary satellite moves in an orbit of radius 6,300 kilometers. So if you want to depict that radius, this is the Earth and this is the satellite. We have that radius that we are given there, okay, as distance from the center of the Earth to the satellite. And the parameters that we are given, if you want to make use of them, we have R to be 6,300 kilometers, but speed is gotten in meters per second. So you can say this is nothing but 6,300 kilo means multiplied by 10 raised to the power 3 meters. Okay, we have been given pi to be 22/7. Pi is 22/7. But if you have a good understanding of geostationary satellite, what it implies is that it's circling that orbit within 24 hours. So the time that we are looking at in this place is 24 hours. But again, since we are working with respect to meter per second as what is going to be our unit, we need to multiply 24 multiplied by 60, that will be in minutes. Then again, multiply by 60, that will be in seconds. So speed, which we know to be distance over time, we cannot get here. But in this particular case, what's going to be the distance that this satellite will cover in moving around here? That's going to be defined by the circumference of the orbit. And circumference is nothing but 2 pi r over t. So this is what we need to input into our calculator, that velocity is 2 pi is 22/7. R we have gotten to be 6,300 multiplied by 10 raised to the power 3, and then the time we have gotten to be 24 times 60 multiplied by 60. So we can say it is meters over seconds. So we just need to put all of this into our calculator to get the value of the velocity as appropriate, and we'll do that just now. That we have 2 times, okay, let me just put everything in bracket first. The numerator 2 times 22/7, okay, then multiply by 6,300, then multiply by 10 raised to the power 3. That's the numerator. So the denominator now divided by 24 times 60 times 60. Okay, so what's that going to give us? 1375/3, but in decimal 458.3. You know, this bar means that is a repetitive 3, so you can just say 458.3. So this is 458.3 meters per second. And with this, we've been able to answer this question holistically as expected of us. In this question on projectiles, we are told that a projectile is fired at an angle of 30 degrees to the horizontal with a velocity of 40 meters per second. We have to calculate the velocity attained after 1 second, and we can take the acceleration due to gravity g to be 10 meters per second square. So this is a pictorial view of what we have, that yes, at an angle of 30 degrees, the projectile is being fired, okay, and then its initial velocity of launch is 40 meters per second. Since it is a projectile, and if we really understand our resolution of components, we will know that since 30 degrees is to the horizontal, then the horizontal component of the velocity will be 40 cos 30, while for the vertical component, we need to be careful to get this. okay, let me just say it like this, that eventually we are going to have it that our u that we are looking for is going to be the square root of us square plus uy square. Okay, so that's what is going to give us the velocity after 1 second in this particular time. But recollect, we are giving g to be 10 meters per second and the time of concentration to be 1 second. So what's going to be our vertical component of that velocity? For that, we are going to record that normally v is u plus at, and why are we bringing u plus at here? Because for the vertical component in moving upward, acceleration due to gravity is going to act on that body. Okay, so the fact that acceleration due to gravity is acting on that body will mean that there will be a pull. So this a will actually be minus. So in that case, we can say that our uy is going to be nothing but the original component on the horizontal, which is 40 sine 30. But now, because it is a vertical component, we need to subtract 10, which is acceleration due to gravity, multiplied by the time, which is 1. Okay, so this is what we are supposed to make use of. And if we bring in our calculator, we can find ux and we can find uy. So we are going to do that to say what is 40 cos 30. Okay, so this is 20 root 3. Okay, is 34.64. So this is 34.64 meters per second. And then 40 sine 30 minus 10. 40. Okay, we don't even need calculator for this. 40 sine 30 is, I'll see we are multiplying 40 by 0.5 because sine 30 is 0.5. That will be 20. So 20 minus 10 times 1 is 10. So this is 10 meters per second, such that what we are looking for, our u, is now going to be the square root of ux, 34.64 square, plus uy, 10 square. And from our calculator, we can look at this to say this will be, okay, what we just got initially, 20 root 3 raised to power 2, okay, that's 1200. So we have square root of 1200 plus 10 raised to power 2 is 100. So we have u to be square root of 1002 plus 100 is 1300, so that the u that we are asked to find, the velocity after 1 second, will be square root of 1300. Okay, so that will be 10 root 13 or 36.055 or 36.06. So this will be 36.06 meters per second as the velocity attained after 1 second of launch. All right. Here we have the circuit diagram that is a simple rectifier circuit, and we're to use it to answer the questions that follow. So these are the questions. In the first case, we have to state the function of each of the parts labeled A. This is A and B. Okay, that is fine and good. We have to sketch the output signal produced. Let's just look at this holistically. Normally, this is a transformer. That A is a transformer, and ideally, it's a step-down transformer that is actually used to get the source voltage for this. This is a diode, just as well as this is another diode. Okay, now B is a smoothing capacitor. This B is a smoothing capacitor because it's going to smoothen the output that is going to be gotten from this circuit, and this is the load that's going to be supplied with the smoothing voltage from the circuit. So in the first case, that we're asked to actually state the functions of those devices as shown. What is transformer going to do and what is the smoothing capacitor going to do? Now, A is the one that produces the alternating current because you can see is a transformer. Normally it's a step down because it will have some other source of voltage, okay? But B is the one that smoothens, since we are talking about an alternating current, so it's going to smoothen the rectified current that is coming from that transformer. And ideally, this in blue is going to be your source voltage, okay? But that is going to be at this point A, where this voltage will be still sinusoidal. But when it gets to B, B is going to affect on it in such a way that that solid sinusoid is going to be reduced to this. And I want you to notice something. Just notice something. Here, there is a crest and there is a trough. This particular region is actually the region in which the capacitor, this smoothing capacitor, it is charging here. Okay, whereas in this particular region, this is the region where it is discharging, and that is how it actually functions as a smoother of that particular current or voltage that's going to be produced in the circuit. So that is that with respect to this question. In this question, we are to explain the wave-particle duality of light. And looking at the second question, we are given that a particle of wavelength 4.2 exponent minus 11 meters travels with a momentum of 1.6 exponent minus 23 kilogram meter per second. We are to determine the value of the Planck's constant. So, whenever we are talking about the wave-particle duality of light, is actually indicating the fact that light can act as a particle as typified by way of photon and also as waves, but it cannot act as both a particle and wave at the same time. It's either acting as a particle or is acting as wave per time. And it is attribute to act as a particle that is warranting this second question, in which we are asked to find Planck's constant given the momentum and wavelength of a particle of light. Now, the formula that we need to use is that the momentum is equal to the Planck's constant divided by the wavelength, okay? Such that if we cross multiply, the Planck's constant is going to be momentum multiplied by wavelength. So, this is the formula that we need to use. And if we want to make use of that, we just know that Planck's constant H will be, what's the momentum that we're giving here? 1.6 times 10 raised to the power minus 23 kilogram meter per second, multiplied by the wavelength that was given as 4.2 times 10 raised to the power minus 11 meters. So we can take our calculator to just multiply this out. So this is 1.6 exponent minus 23 multiplied by 4.2 exponent minus 11. Okay, so this is 6.72 exponent minus 34. So this is nothing but 6.72 exponent minus 34. And what's going to be the unit for the Planck's constant? That's going to be joules seconds. Okay, so it's just for us to know this particular formula, apply it, and in this particular question will be done and dusted, and our answer will be, this is quite close to the constant value for the Planck's constant, but no problem. Since they asked us, we are good and fine just like this. Here we are being asked to state 3 observable phenomena where a particle behave like waves. Students, I need you to be careful here. They're only asking you to state, so don't waste your time trying to define, trying to enumerate on it, because time will not be a friend. So some of those phenomena where a particle can behave like waves include the fact that it can be diffracted, it can experience interference, polarization can occur, it can be refracted, and it can be reflected. Any 3 among these 5 will be sufficient to earn your full marks in this place, and since you're only asked to state, that will be good and fine. Alright, so that means you just take this as a bonus question and you'll be good and fine. Here in this question, we are to state the scientific principle underlying the operation of fiber optics, and we are also to explain the terms core and cladding as used in fiber optics. Now, a picture is worth 1,000 words, and here the scientific principle behind the operation of fiber optics is total internal reflection, and it operates in such a way that normally the core is having a higher refractive index more than the cladding. The cladding is the protective sheet on top of the core, even though they still have some better protective layer covering both of them, but so that the rays of light that is coming into the core, that is the carrying medium, should be able to be reflected back inside and not be lost to the cladding. That is why the cladding needs to be of a lower refractive index. And of course, this is just the operation of total internal reflection. And then the core is the central part here shown in white that is acting as a light carrying portion of the fiber optics, whereas the cladding is the outer layer that surrounds the core and it has a lower refractive index. And if you can explain successfully like this, your full mark is assured and you'll be on your way to excellence. All right. So here in this question, we're asked to take Hooke's law, and as simple as it gets, Hooke's law states that the extension produced in an elastic material is directly proportional to the applied force, provided that the elastic limit is not exceeded. Once we are done with that, we are going to be applying that Hooke's law to this particular question, in which we are told that a spring has the length of 0.2 meters when a mass of 0.3 kilogram hangs on it, and the length of 0.75 meters when a mass of 1.95 kilogram hangs on it. Our mandate is to calculate the force constant of the spring and the length of the spring when it is unloaded. So we need to note that information that we're being given. It is when the spring is unloaded that we are to find the length of the spring. So this is actually a pictorial view of what we have here, that in the first case, when the mass is 0.3 kilograms, we have 0.2 meters as the length of the spring. Notice that that length will be the addition of the original length L0 plus the extension E1. I'm calling it E1 because we have two cases. So here, this will be 1, and here, this will be 2. In the second case, we are told that it has a length of 0.75 meters, which is going to be the addition of the original length plus the second extension when a mass of 1.95 kilogram hangs on it. So we have to calculate force constant of the spring and the length of the spring when it is unloaded. For us to solve this, we can make use of Hooke's law and the formula that says that force is equal to the force constant multiplied by the extension as a means of solving this question. But looking at the parameters that we have, in the first case, we are given the force mass M1 to be 0.3 kilograms, but we are talking about forces, so we can say F1 is M1 multiplied by G. So that will be 0.3 multiplied by 10 meters per second, and that will be nothing but 3 newtons. Okay. Then M2, we are given as 1.95 kilograms. And again, in the same vein, F2 will be M2, which is 1.95 multiplied by 10. So this will be 19.5 newtons. Okay. The new length we have been given in meters, so we are good and fine to use it. So if you want to employ the formula F equal to K multiplied by E, in the first case, we can say that for F1, we are going to have 3 is equal to K, which we don't know, multiplied by the extension. Now, this is where it gets tricky. What is the extension in this particular case? We know that the original length L0 plus the extension will give us the length of the spring. So the extension will be the length of the spring minus the original extension. Students, once we miss that point, you are going to get a wrong answer. But the right thing will be that this 0.2 meters is the addition of the original length L0 plus the extension, so that the extension will be 0.2 meters minus L0. So we have 0.2 minus L0. Okay, I can take this as my equation 1. And then the second case, the force is now 19.5 is equal to K into what is the length here is 0.75. Just coming from the explanation I did before, that length is the addition of the original length plus the extension. So extension will be 0.75 minus L0. So this will be minus L0 also. So this we can call equation 2. So our mandate is now to go ahead to solve this question by whatever means we think will be appropriate and get the solution above. Now, this is what you need to notice, student. First, we have to get the force constant of the spring. So we should eliminate L0 as much as possible. And okay, if you just want to do that, we can say from equation 1, from 1, you can see that 3 over K is equal to 0.2 minus L0, such that L0 will be this going to the other side, that going to the other side, 0.2 minus 3 over K. So this we can use in the other equation. We can use it in 2, that 19.5 is equal to K multiplied by 0.75 minus, instead of L0 now, we can put all of this 0.2. Let me put that in brackets because we have minus 3 over K. Okay. So if you open up that bracket, we can have 19.5 is equal to 0.75k here minus 0.2k. When this minus and this minus, when they multiply, it will become plus. K multiplied by 3 over k, the k will cancel out, so we have plus 3. So here, if we just collect like terms, we can have 19.5 minus 3 is equal to 0.75k minus 0.2k, and that's going to be 0.55k. Okay, so 19.5 minus 3, this is going to be 16.5 is equal to 0.55k. And for us to get k, we can divide both sides by 0.55. Okay, and this we can take with our calculator as 16.5 divided by 0.55. What's that going to give us? Wow, 30. So here, this is cutting out such that the first constant k is nothing but 30. Now, what is going to be the unit of k? Originally, we have been told that F is equal to ke. So k will be F over E, and that will be that the unit will be newtons per meter, because force is in Newton and E, the extension, is in meter. So this is the value of the constant. Okay. Now in the second case, we are asked to find the length of the spring when it is unloaded. Let me just move my body a bit so that I have space to work. Okay. In our first equation, we are talking about the fact that the force, which was 3 newtons, is equal to the force constant k multiplied by the length 0.2 minus the original length L0. Now, since we have been able to find the value of k, that means we can just say that 3 is equal to k is 30 multiplied by 0.2 minus that original length when the spring is not loaded. So we can just divide by 30 so that 3 over 30, that will be 1 over 10, which is 0.1, is equal to 0.2 minus L0, so that our L0 will be 0.2 minus 0.1, and that will be 0.1 meters. So for this particular question, we've been able to get the value of the force constant k to be 30 newtons per meter, and the length of the spring when it is not loaded, when there's no force acting on it, to be 0.1 meters. And is a very good application of Hooke's law, which we have been able to solve appropriately in this question. Now here in this question talking about diffusion, we are to define what diffusion is and state factors that affect the rate of diffusion of a substance, and then state the exact relationship between the rate of diffusion of a gas and its density. And just as being shown on the board, in the first case, diffusion is the intimate mixing of substances due to random motion of their molecules or particles. So when you are talking about, for example, the fact that somebody farts, okay, so what is happening is diffusion is occurring due to the random motion of the molecules or the particles. So it's just mixing with the atmosphere, and then we are getting to perceive it. Okay, then the factors that affect the rate of diffusion include the temperature of the environment, the medium of diffusion, can be liquid or gas, okay, the density of the substance, and the concentration gradient of the particular substance. And here now, in this particular third question, we're asked to state the exact relationship between the rate of diffusion of a gas and its density. The rate of diffusion of a gas is related to its density. You know, from this second one, we're already saying that the factors that affect the rate include even the density of the substance. But the particular relationship will be that the rate of diffusion is equal to 1 over the square root of the density of the gas in question. Okay, so this is the exact relationship between them. And once you're able to state that, you'll be good and fine, and your full mark will be awarded as appropriate. Here in this question on satellite, we are told that a satellite of mass m orbits the Earth, which is of mass capital M, with a velocity v at a distance r from the center of the Earth. Our mandate is to derive the relationship between the period t of orbit and the radius r as given. Now, if you want to just notice all the parameters that were given, we are told that the satellite here is of mass small m, the Earth is of mass capital M, and then there is a distance between them which is r, and then that satellite is moving with a velocity v. Okay, very good with all these parameters that were given. And for us to derive this relationship between the period of orbit t, which will be the time it will take for it to complete a circle, okay, and the radius r, which is the distance between the satellite and the center of the Earth, we need to consider the fact that the centripetal force on this satellite, which is causing it to accelerate, is going to be equal to the gravitational force on the satellite. So we can just say we are having Fc is equal to Fg. And now, what is Fc originally? Fc is giving us m multiplied by the square of v over the radius, whereas Fg is giving us the gravitational constant multiplied by the product of the masses over the square of the distance between them. So this is what will help us to actually solve this question, but we are having velocity here. Velocity itself is distance over time, and for this particular satellite that is orbiting around the Earth, the distance will be the circumference of that particular orbit, which is 2 pi r, and then the time will be the period that we are looking at, okay? So if you want to use this and put it into this particular equation, all we're going to have is that we're going to have m over r multiplied by v square will now be 2 pi r over t raised to power 2. That is equal to g multiplied by m multiplied by capital M over r raised to power 2. We can open up this bracket to say this is going to be m over r multiplied by 4 pi square r square over t square, which is equal to g multiplied by m and capital M over r square. Okay, I can see already that this r can cut here, so I have one r remaining, okay? And then if I say I will cross multiply, so here if I now say I want to cross multiply and just have a flattened solution, I can say I'm having m multiplied by 4 pi square multiplied by this r in red, then multiplied by this r square is equal to this t square multiplying the other side, t square multiplied by g multiplied by m and multiplied by capital M. And of course, m is also common to both sides. I can cut out this. Then I will have, okay, if I want to just take t as a standalone, I can have t square to be equal to this r multiplied by r square will be r3. So I have 4 pi square r raised to power 3 over this gm. Okay, so this is as good as it gets. I can take the whole of all this as a constant, okay, or I can even just express it out that this is equal to 4 pi square over gm, since I'm looking for the relationship between t and r, then multiplied by r cubed. Either I take this as a constant or not, I can say t is going to be the square root of all of that expression, 4 pi square over gm multiplied by r raised to power 3. And now, the square root of 4 is 2. The square root of pi square is pi. So I still have, okay, this is remaining r raised to power 3 over g multiplied by m. So I can immediately say this is my relationship between t and r, or I can even just actually say that all of these are constant. For t and r, I can have it that t is proportional to the root of r cubed if I'm taking every other thing as constant or proportionality. Because pi, we can get g is a constant. The mass of the Earth is also a constant. So either of the two is good and fine, and we have been able to derive the relationship between the period t of orbit and r with the case scenario that was depicted for us. Our question is going to focus on optics, and in the very first question we are asked to define the following terms as it relates to converging lens. So let's note we are talking about lens, but particularly we are even talking about the converging lens. So we want to talk about the focal length and we want to talk about the optical center. So the focal length is the distance between the optical center and principal focus. So this is the principal focus, and the optical center is just the center of this lens here, the one crossing both the broken lines and this particular black lines, which is the principal axis. The optical center itself is the geometric center of the lens, just as I'm saying now. This is the geometric center of the lens through which rays of light are going to pass undeviated. Is a point in the lens through which the principal axis here in black, it passes, and light rays also pass through it undeviated. So let's use an example to explain all this grammar that we have just talked about as regard the optical center in particular. So our definition had helped us to define this point as the optical center, and the distance between the principal focus and the optical center as the focal length. But to actually get a full picture of how this is working, let's consider this and want to try and place it on the converging lens. So there are rules that guide the construction of rays of light that will help us to get the image of such an object like this. Okay, so this is the object, and then for us to form the image of this particular object from the converging lens, normally rays of light that will be coming from the object will be drawn parallel to the principal axis. This is the principal axis in black. So rays of light will come, and then when it gets to the lens, it will be refracted through the principal focus. Okay, so since it's coming from this side, then it will be refracted through the principal focus on this particular side. And we have noted that the distance between the principal focus and the optical center is the focal length. Okay, then that being as it may be, the other rule is that the rays of light coming from the object will pass through the optical center undeviated. So from here, it will just pass through the optical center undeviated, and the intersection of those rays of light is going to inform us about where the image is going to be placed. So if you want to have a pictorial view of what I just explained, it's just here. So you can see from the object, for us to get the image, we have rays of light parallel to the principal axis, but when it gets to the lens, it will be refracted through the principal focus here, and then rays of light also coming from the object will pass through the optical center undeviated. So you can see this one is just passing through straight, it's not deviated, it's not refracted at all. And then the point where those rays of light, where they are meeting, is where we are going to have our image. The other rule is that if the rays of light is also passing through the principal focus, once it gets to the lens, it will be refracted, and then it will deviate parallel to the principal axis. So it's like the reverse of the one coming parallel to the principal axis that will be refracted through the principal focus. But even if it's coming from the principal focus, once it gets to the lens, it will be refracted to run parallel to the principal axis. So I took my time to explain this because our next question is going to actually leverage on the understanding of how these rays of light, how they emanate from the object to give the image, and we can go ahead to see that right about now. Okay, so yeah, in this question we have to draw a ray diagram to illustrate how a converging lens is used to produce a virtual image of an object. And if you want to leverage on the understanding that we just shared from the previous question, we can have our converging lens as shown. We have its principal focus, center of curvature, and co. We have the principal axis. We are looking for a position, a point where we can place an image in such a way that the object that will be formed is going to be virtual. Virtual in this case will mean that it has to be on the side where the image is also placed. Okay, so that's going to be our information on the virtuality of the image that we produce, and this is going to be what we are going to experience. And I'm going to just render some explanation here. This in solid green is our object, and this in light green is our image. And coming from the understanding of how rays of light produce the image, first we are saying that ray of light emanating from the image, which is parallel to the principal axis, this one that I'm showing with this arrow, then after passing through the lens, it will be refracted to pass through the principal focus. So we have something like this. Okay, and then the other one is that those rays of light will pass through the center of curvature undeviated. So we have a particular ray of light coming in this direction. But if you notice this is going to be ever expanding. So the image is not going to be formed on this side because those rays of light, they are not going to cross, they are not going to intercept on that particular side. So for us to get it, we need to trace back, and that is where the virtuality of the image of this object is coming in. We are tracing back, and we are saying that here at this particular point, the image is going to be formed because those rays of light are going to intercept there, and then this is a virtual image. And the other properties is that yes, it is virtual, it is erect, you can see it's erect, and then it is magnified, it is bigger than this particular object size. So if you want to look at it and want to say that okay, from this diagram, we can see that if we want to consider the image distance, the focal length, and the object distance, we can notice that from here to here, this is the image distance, u. Then from the principal focus to the center of curvature, we have this as our f. But look at here. So if we look at that and we consider it to the center of curvature, we can see that this is our v, which is the object distance. And the peculiar thing here is that the image distance is less than the focal length, which is less than the object distance. And with this, we are going to have a virtual image of the object, which is going to be magnified and erect. So as a rule of thumb, objects that are placed between the principal focus and the center of curvature of a converging lens is going to give us this type of image that is virtual, erect, and magnified. So students, as you can just get your hands dirty by practicing with placement of objects on various locations across the lens. Maybe before 2 multiplied by the focal length, before 2f, maybe around here, before 2f, you can consider how that image will be formed. You can consider at 2f where the image will be formed. You can consider between 2f and f where the image will be formed. Here, you can also consider at f, at the focal length, where will the image, where will it be formed? And here we are seeing that between the focal length and the center of curvature, the image produced will have this attribute. So if you have been able to get this, then you have answered this question correctly and dusted it appropriately. So here in this question, we're asked to name the primary colors of light, and then subsequently we are to match each primary color to its corresponding complementary color. As good as it gets in a pictorial form, these are the primary colors of light, in which we are having those primary colors to be RGB, indicating red, green, and blue. And the complementary colors for red, the complementary is cyan, the complementary for green is magenta, the complementary for blue is yellow. I want you to note just some few things here. Ideally, if you are answering your questions, first answer the first one, B1, red, green, and blue, and then B2, you rewrite red, green, and blue, and then match it that red, cyan is a complementary for red, magenta for green, and yellow for blue. I just want you to notice this particular thing. Look at this. Red is having its complementary as cyan, okay? Green is having its complementary as magenta, yellow is having its complementary as blue. And now the combination of the three is what is actually going to give us the white light. So you can use this for the additive or the subtractive guide for colors. But as regarding the question that was asked, the primary colors are RGB, the complementary colors are cyan, magenta, and yellow. All right. This is quite an interesting question that students, if you can get the hang of it, you'll be able to solve it subsequently if you come across it in your exams. We are told that the ray of light passes symmetrically through a glass prism of angle 60 degrees and refractive index of 1.5. Our mandate is to calculate the angle of incidence and the angle of minimum deviation. So we can take this as a pictorial view of the glass prism that we are looking at, and the included angles are also as shown. Okay, so here we can just try and look at how to solve this question with the information that we are given. First and foremost, we know that the refractive index n is given as sine I, the sine of the angle of incidence, over sine r, the sine of the angle of refraction. Here, refraction for the triangular prism. But look at the information that we are given. We are told that the triangular prism is of angle 60 degrees. So we can say this angles in blue is 60. But permit me to call it and tag it as A. And in other cases, I can just write that, yes, we know that our A is 60 and A is 60 here, right? But we need to find the angle of incidence just given the angle A to be 60, and we need to find the means of reflecting how the angle of incidence can be obtained from A, and then how we can also find the angle of minimum deviation. Now, let's look at the angle of minimum deviation and how we can solve that holistically. If we take this as the incidence ray, so this is the incident ray, normal to the prism, it will make an angle of incidence I, okay, and then passing through the prism, it will make an angle of refraction R. But in this special case, we are told that the light ray is passing symmetrically through the prism, meaning that the angle of refraction at one side of the prism is also going to be the exit angle at the other side of the prism, and then we can have the emergence angle here as E. Okay, so that being said, assuming that the light ray is just passing normally, it will go straight and continue with this broken line. And now if we look at the emergent ray, you can see that there's an angle that the emergent ray is making with the original incident ray, and that angle there for this particular case is the angle of minimum deviation. Minimum because it is passing symmetrically. If it's not passing symmetrically, it will just be an angle of deviation. But it is as a means of it passing through symmetrically that we're going to have minimum deviation. So we can call this dm, and our mandate is to find the angle of incidence I, this I, and the angle of minimum deviation dm. So with the parameters that we are given here, let's try and see if we can get dm and a as a reason of the angle 60 degrees of the prism that we are given. We will come to make use of our laws of geometry coming from mathematics, and that will be good and fine. If I call this M, N, O, and P, if you consider the quadrilateral MNOP, you can see that this angle here at P, this is also a right angle. At N, this is also a right angle. So we can say that angle A plus 90 degrees at N plus this angle here, okay, if I call that, let's say I can call that X, I'll just know that as X, okay, plus angle X plus the other 90 degree that is at P, call that another 90, that is equal to 360 degrees at the sum of angles of a quadrilateral, 180 into N minus 2, okay, and of course it's just four-sided, just like a rectangle. So A is the angle of the prism that we're given as 60 degrees. So X in that particular case will be 360 minus the sum of 90 and another 90 and another 60. Okay, so that X is going to give us 90 plus 90 is 180. 180 plus 60 is 240. 360 minus 240, that is 120 degrees. But this angle here, this angle in green, if I call that Y, okay, you know, initially I'm calling this X. If I call this angle in green, if I call it Y, we can see that Y and S are angles on the straight line. So X plus Y is 180 degrees because they're angles on the straight line, so that Y will be 180 minus X, and that X is 120 degrees. Okay, so Y itself is 60 degrees, which inherently is also A. So this Y, this place is also A, and that is 60 degrees. Now, I'm just trying to find a means of getting the angle of refraction here, R, and then maybe later I can also come to get the angle of incidence, I. Now, for us to get R, we can see that this A is exterior to this triangle in which you have the base angles to be R and R. And from trigonometry, we know that A is going to be the sum of the two opposite interior angles of the triangle. So A is R plus R, which is 2R. And then I can say R is A, which is 60 over 2. So the angle of refraction we are saying to be A over 2. We will note that, okay? So this is our very first postulate. On the second note, we can look at this angle I, and then if I call this angle here, if I call this theta, this angle is also theta as a reason of the symmetry of this diagram. And this angle of incidence I and this particular angle, theta plus R, they are vertically opposite angles. So I can say I is nothing but theta plus R, okay? And then, as interesting as that gets, already of course we have R to be A over 2. How do we get theta as a reason of this angle of minimum deviation? Looking at that triangle also, we are seeing that the angle of minimum deviation is exterior to these two theta, this theta and this theta. So we can say that actually dm is equal to theta plus theta, which is 2 theta, so that theta is also dm over 2. So with the value of theta as dm over 2 and r as a over 2, you can say our angle of incidence is also equal to theta is dm over 2 plus r is a over 2, so that I itself is dm plus a over 2. So we have two values here, the angle of refraction as a over 2 and the angle of incidence as dm plus a over 2. So instead of just writing n to be sine I over sine r, I can say n inherently will be sine of I, that is now dm plus A over 2 divided by R, divided by sine R, which will be sine A over 2. So this is the formula for the refractive index that will help us to solve this question holistically. Okay, we have gotten our A to be 60. Okay, so for this particular question, we are now looking for I, okay, and we are looking for dm. So these are our two unknowns. And to solve in the first question, to find the angle of incidence, we'll still come back to this formula for refractive index to say that 1.5 is equal to sine I, which we are looking for, divided by sine R. Now sine R will be sine A over 2, so we have this as sine 60 over 2. Sine 60 over 2 is sine 30, so we can say sine I is equal to 1.5 multiplied by sine 30, and sine 30 itself is 0.5. 0.5 times 1.5 is 0.75, so that I will be arc sine 0.75. And we have to check that in our calculator. We have arc sine 0.75, that is equal to 48.59. We can say 48.6. We can say I is 48.6 degrees. So our first solution is out, and that is as good as it gets. We'll now try and find a means to look for the angle of minimum deviation. All right. So in the second case, we can say that to get the angle of minimum deviation, our n, which is 1.5, we now want to use this formula holistically. Okay, is equal to the sine of that angle of minimum deviation plus A. A we have been given to be 60 over 2 divided by sine A over 2, which is sine 30. Sine 30 is 0.5. 0.5 times 1.5 is 0.75. So that means sine dm plus 60 over 2 is equal to 0.75. Or we can even say dm plus 60 over 2 will be arc sine 0.75. So let me just do that. That what we're having is dm plus 60 will be arc sine 0.75. Okay, and what is arc sine 0.75? That's the answer that we just got, 48.59. So I can say 1 over 2 of dm plus 60 is 48.6, such that dm plus 60 itself will be 2 times 48.6, and 2 times 48.6, this will be 97.2, and then dm will be 97.2 minus 60 degrees, and that will be 37.2 degrees as the angle of minimum deviation, whereas we have gotten our angle of incidence to be 48.6, and then we would have covered this question holistically, and that is the solution that is expected of us. So generally, this is the formula that students are expected to use. This is the formula that you are expected to use. I just took this time out to explain it so that even if you get to meet it subsequently in your exams, you can just make use of the formula directly, having the understanding of how it was obtained, so that you are not confused at all. It's still in line with the formula for refractive index that we have as sine I over sine R. All right. This question is outrightly focused on electricity in physics, and in the first case, we are being asked what is the root mean square of an AC, and we're also asked to define the impedance of an AC circuit. Now, a picture for me is always worth 1,000 words, and in the first case, to define the root mean square of an AC, we need to look at a DC. So this is a direct current. You can see this is denoting battery cells, okay, and then the current that we will have in a DC circuit that will produce the same heating effect as the current in an AC is what is regarded to as the root mean square current, and is defined, normally for the alternating current, the current will also be sinusoidal, just like this, and this is what we are going to have. But the root mean square is defined as the peak current here, the peak here. If this is I, the peak here, IP, okay, divided by square root of 2. That is the definition of the root mean square current in an AC, okay? Now, in the second case, when we are talking about an impedance in an alternating current circuit, Normally, we need to understand the features of an alternating current circuit. That's a circuit that has at least two of a resistor, a capacitor, and an inductor. Okay, so it will have at least two of these three devices, and then the impedance will be the total opposition to the flow of current in that particular circuit. In a normal circuit, we just have the resistance as the opposer to the flow of current, but now in an AC, we have the resistive load, the capacitive load, and the inductive load, and the combination of the three is what is tagged the impedance. So that is the example of the definition of all this. And if you want to put it in words, it's just as given here, that the root mean square is just the value of the steady or direct current, which will dissipate it at the same rate with that current in a given resistance. It is the square root of the mean value of the squares of the current or voltage, because they didn't specifically tell us current or voltage here. So it can be current or voltage, and that is taking over a whole circuit. Now, in the case of impedance, it is the total opposition to the flow of an AC by both resistive and reactive component, as I showed in the diagram the other time. So it is the total opposition of a circuit, which can consist of any two of the resistor, the inductor, or the capacitor. So that will now receive the flow of AC in the circuit. That is what constitutes the impedance. Okay. Here in this question, we are being told that an electrical device rated 120 volts and 60 watts, here as shown in the diagram, is operated on a 240 volt 50 hertz main supply, which is also as shown here. Now, the circuit has a capacitor connected in series with the electrical device and the supply. So that is why we have our capacitor as shown here, and our mandate is to calculate the capacitance of the capacitor. So let's start with the mandate before us. We are asked to find the capacitance of the capacitor. Now, looking at the particular circuit that we have here, we know that since it's a series circuit, the same current will flow in that circuit. So the current flowing across the capacitor is also going to be the value of the current flowing across the resistive load. And since that is the case, we can say that the voltage across the capacitor will be the current flowing in the circuit multiplied by the capacitive reactance. Now, if we can get the value of the current and we can get the value of the voltage across the capacitor, we can get the reactance of the capacitor, and then we know that that reactance SC is actually 1 over 2 pi FC, where pi was given as 3.142. F is the frequency of the circuit given as 50 Hz, and C is that capacitance of the capacitor that we are looking for. So we can just do a change of subject of formula to say that our SC will be 1 over 2 pi F XC. So let's just take it piecewise. Okay, first, how do we get the current flowing in this particular circuit? Since we have this as a resistive load and we are giving the voltage across this as 120 volts and the power given as 60 watts, we know that from physics, power in this particular case that we even have a resistive load is given as a product of the current multiplied by the voltage. Now we are giving the power to be 60, the voltage to be 120, then I will be the power over the voltage, and that will be amounting to 60 watts divided by 120 volts. So the current in this particular circuit, as deduced from the resistive load, is nothing but 0.5 amperes. So that is good and fine. Since we have the current now, we can proceed to try and find voltage drop across that particular capacitor. And for us to get that, we can make use of the fact that the square of the voltage flowing in the circuit is going to be the square of the voltage across the capacitor plus the square of the voltage across the resistive load. So since we now have the voltage across the capacitor as what we are looking for, we can now say that VC square is equal to V square minus VR square. So let's just put in those values there. This will now be, what is the source voltage? That is 240. So we have 240 raised to power 2 minus, what's the voltage of the resistive load? That is 120. So we have 120 over 2 raised to power 2. So if you want to use our calculator, we have 240 raised to power 2 minus 120 raised to power 2. That is 43,200. So this is 43,200, such that the voltage across the capacitor itself is going to be the square root of 43,200. Okay, so we can just say the square root of our answer 207.85. So this is 207.85 volts. So these are as interesting as it gets now. Since we have now gotten VC and we have gotten the I, from this particular formula here, we can now say that our VC over I is going to be, instead of using XC, we can use this for our XC, 1 over 2 pi F multiplied by the capacitance of that capacitor. So that's what we're going to do now, and we'll get our capacitance out and find, but I'll need to clear my board first, okay? So those are the values that we have gotten so far, but we are made to understand that here, if we want to make SC the sort of the formula, it will be VC over I is equal to SC, and SC itself is 1 over 2 pi FC, 1 over 2 pi FC. Now, I love to just make my unknown the sort of the formula, so if I cross multiply here, I can say that means that the capacitance of the capacitor is going to be I times 1, that is I, divided by 2 pi F times VC, that is 2 pi F multiplied by VC. So all I need to put in is all these parameters to say what is the current that was given as 0.5 amperes as calculated before. Then 2 times pi was given as 3.142. The frequency were given originally as 50 Hertz. Okay. And then the voltage across the capacitor we have obtained to be 207.85 volts. So our capacitance we can get by evaluating this particular function, and we can use our calculator there to say that we are having 0.5 divided by everything in bracket. So 2 times 3.142, okay, multiplied by 50 and multiplied by, now this was just the answer we got initially, so I can just multiply by my answer, and that is equal to what? This is 7.6563. Okay, let me just say 7.66. So this is 7.66 times 10 raised to power minus 6 farad. Now, 10 raised to power minus 6 will amount to micro. So this is nothing but C is equal to 7.66 microfarad as the value of the capacitance of the capacitor in this particular circuit that we are looking at. All right. And here in this question, we are told that the circuit diagram, this circuit diagram, illustrates two capacitors of capacitances C1 here. Let me just identify that C1 here and C2 that are connected in series across a 2-volt source. So our mandate first and foremost is to find the expression for the total capacitance in terms of C2. So C1 is not going to reflect in the equation. We only want to make use of C2, okay? Then we have to get the potential difference across each one of them, across each capacitor. No problem, good and fine. In the first case, for us to find an expression for the total capacitance in terms of C2, let's even leave in terms of C2 first. Let's look at in series. How do we find the total capacitance of capacitors connected in series? It's given as 1 over C total is equal to 1 over C1 plus 1 over C2. Okay, so if you want to do that, we can just say we can find the LCM that 1 over C total is going to be, that's going to be C1 C2, and then C1 C2 over C1 will remain C2, so we have C2. C1 C2 over C2 remains C1, so C1 times 1 we have C1. So here we can just say we want to cross multiply to say that the total capacitance in this case is going to be C1 divided by C2 over the sum of C1 and C2. I just took my time to get this out. Ideally, this should just be on the fly that you'll be able to get straight and direct. So this is the first thing we need to note. But we have to obtain the total capacitance in terms of C2. And then this is where it gets interesting. Look at this. We have C1 and we have the distance relating it. We have C2, we have the distance relating it. Okay? Normally, we are made to understand that the capacitance is inversely proportional to the distance between the electric plates. So in this particular case, we can say C1 is inversely proportional to 1 over 2, and then C2 is inversely proportional to 1 over 5, where 2 millimeters and 5 millimeters are the distance between the plate of the two capacitance. Okay, so Now, these two, we can just say we want to bring them together to say we have, let's say C1 over C2. That would be 1 over 2 divided by 1 over 5. So for this now, we can say we want to cross multiply such that we are going to have 1 over 2 C2 is equal to 1 over 5 C1. But we're asked to find it in terms of C2. So C1 is not going to reflect at all. So from here, we can say C1 is going to be 5 over 2 of C2. I just cross multiply the fractions in front of the 2. So 5 will go and multiply the numerator here as 5 over 2 C2. That means I cannot make use of this particular expression for C1 in this formula for C total that I've gotten initially. And then I would have been able to find an expression for the total capacitance in terms of C2. Student, I hope you understand this. You already know the concept of finding the total capacitance for a circuit in series, okay? We just brought in this idea of the fact that the capacitance is inversely proportional to the distance between the dielectric plate of a capacitor. And then, if we can do that for C1, we can also do it for C2. And since we are talking about capacitance, we can bring them as a relation to one another and find C1 in terms of C2. So we are going to just use this now in our formula for total capacitance and we'll be good and fine. All right. So this is what we have gotten so far. And we want to reflect the total capacitance only in terms of C2. We can just say, wherever we see C1, we are going to put 5 over 2 C2. So we can say our C total is going to be, in the first case, C1, that will be 5 over 2 multiplied by C2, again multiplied by another C2, over C1 again, that will be 5 over 2 C2 plus another C2, okay? Okay, so this is going to be 5 over 2 multiplied by C2 square divided by here. If I bring in, if I want to solve this, as if I can say for this second C2, I have it as 2 over 2. So 5 plus 2 is 7. 2 is the same base, so I can just have it as 7 over 2. I hope you get that, student. I'm just doing the LCM straight and trying to express it out. So this will just be 7 over 2 C2. So I can just write it straight as 7 over 2 C2. And of course, we have C2 square up and we have C2 down. This is C2 here can go on here. We have it as just C2. So our C total is going to be 5 over 2 C2 divided by 7 over 2. So this is going to be 5 over 2. Instead of divided, I can say times 2 over 7 of C2. And of course, if I am to cut, 2 here can cut 2. So this is going to be 5 over 7 C2 as the total capacitance of this particular circuit in terms of C2. All right. Now, for us to calculate the potential difference across each capacitor, we have already obtained the total capacitance to be 5 over 7 of C2. But by reason of our understanding of charges, we know that charge is the total capacitance multiplied by the voltage. So we can say that total charge Q is nothing but that total capacitance, which is 5 over 7 divided by C2, multiplied by the voltage. And the voltage here we can see was given as 2 volts, so we can say multiplied by 2. So this is nothing but 10 over 7 C2. Okay. Now, for us to get the charge across each of them, let's take, maybe we want to find, since we have C2, let's say we want to find V2, the voltage across the C2, across this particular one. That will just give us the Q, the total Q, over the capacitance of that capacitor C2. So I'm doing this because I know that that ratio will cut out so that we can have 10 over 7 C2 divided by what is our C2 already. Of course, our C2 is C2. Okay. So this is just nothing but 10 over 7 volts. Or if you want to write it in the normal voltage, you can just say 10 over 7. What is 10 over 7? 10 divided by 7. That is equal to 1.4285. I can just 1.43. So this is 1.43 volts. That is V2. But then to get the V1, we know that normally the voltage across the circuit, since it's a series circuit, the voltage 2 volts will be first the drop across V2 here plus the drop across V1. So it is the sum of these two voltages that will add up to this total voltage 2 volts. So I can just say, since that is the case, then V1 will be the V total, which is 2 volts minus V2. Okay, that is minus V2, and that will be 2 minus 1.43, and 2 minus 1.43 is nothing but 0.57 volts. And that's also consistent with the distance between the plates, that here, since it's an inverse proportion, then the larger the distance between the plates, the more the voltage that will be dropped across that particular capacitor, and the lower the distance between the plates, the lower the voltage across the capacitor. So from what we have gotten so far, we've gotten our V2 to be 1.43 volts and V1 to be 0.57 volts, and with that you've been able to solve this question holistically, and that is done and dusted. So for this question, the principal factor that determines the relative stability of a radioactive nuclide is actually the neutron to proton ratio. So we need to get the number of neutrons, we need to get the number of protons. So we need to get the number of neutrons, and we also need to get the number of protons, and find the ratio to determine the stability of the radioactive nucleus. So for the second question, in which we have the number of radionuclides, and we need to determine the stability compared to one another, this is what we are going to take. Let's just take like the first one, for instance, in which we are giving X, and we have it as 40 and 20. For this particular case, it will be good to know that this 40 is actually the atomic number, and then this 20 is the proton number. So we need to first and foremost get the neutron number. The atomic number is denoted as A and the proton number is denoted as Z. Now for us to get the proton number, generally we make use of the formula that the atomic number is actually consisting of the proton number Z plus the neutron number N, such that the neutron number can be obtained by saying it is the atomic number minus the proton number. So for each of these radionuclide, we need to get the atomic number, the proton number, and the neutron number, and then we can find the neutron to proton ratio. And if we want to do that here, let me just say we have X 40 20, we have W 92 36, and we have Y 95 42. So we want to get the atomic number for each one of them. For X, that is 40, for W is 92, for Y, that is 95. The proton number, which we can also deduce from the figure that we are given, we can see that the proton number for Z is 20, the one for W is 36, and then the one for Y is 42. Now for us to get the neutron number, we need to now subtract the proton number from the atomic number. So 40 minus 20, this is 20 here. 92 minus 36, that will be 12 minus 6 is 6, remaining 8 minus 3 is 56, and then 95 minus 42, that will be 53. So we can look at the neutron to proton ratio. In this case, it will be 20 over 20. So this is 1. That's quite stable. Okay. Then in the second case, we have 56 divided by 36. And we can use our calculator to obtain that we have 56 divided by 36. That's giving us 1.555, or we can say 1.6. All right. And then 53 divided by 42. What's that going to give us? 53 over 42. So this is 1.262, or let's just say 1.26 is 1.26. Okay. And now looking at those values, we can see that the one that is very, very stable is X. So the order, and look at that, we are saying that it is decreasing order. So the most stable one is actually X 4020, followed by the next one will be 1.2. You can see 1.6 is quite far from even both of them. So the next one will be Y, which will be 9542Y. Okay. And then the least stable one is W. And we can tag that as 9236W. So this is the order, and the justification that they are asking for is for us to show this neutron proton ratio that we have stated to be the factor that determines the relative stability of a radioactive nucleus. Yeah, we're asked to explain the term ionization potential, and ionization potential is the minimum energy that is required to remove an electron completely from an atom. Now, the next question is going to be a practical demonstration of that, so that will serve as our explanation for this definition, okay? So this question here is going to perfectly illustrate the explanation that we just made. We're told that this diagram illustrates energy levels in the hydrogen atom. So E naught is the energy of the ground state. You can see E naught corresponding to N is 1. Now, when an electron makes a transition from level N is 3 to level N is 1, it emits a photon of wavelength 1.02 exponent minus 7 meters. We have to calculate E naught. Okay, we have to calculate this E naught. And then we have to calculate the ionization potential of the hydrogen atom. We are given this number of parameters, Planck's constant, the speed, and then the conversion of 1 electron volt to joules. In the first case, the transition from state and the change in energy level is given as Hc over lambda. And here, what is the change in energy level? We are having a movement from E3 to E naught, okay, is equal to Hc over lambda. So let's just see what we can do here, and I'm going to be meticulous about the units so that you can see the appropriate conversion that we need to do. Energy level for N equals to 3 is minus 1.5 electron volts, then minus the energy level of the state that is being transitioned to is going to be H, which is Planck's constant, 6.6 times 10 raised to the power minus 34 joules seconds, multiplied by the speed, 3 times 10 raised to the power 8 meters per second, and we're using the wavelength to divide that, and that wavelength is 1.02 multiplied by 10 raised to the power minus 7 meters. Now let's cut. Here we are seeing meters, and this is also meters. They are cutting out. We are seeing second, and we are seeing per second here, so that's also cutting out. Then that means that what we are going to have on the left hand side, we have minus 1.5 electron volts minus E naught is equal to, let's calculate this with a calculator, okay? So we are going to have 6.6 exponent minus 34 multiplied by 3 exponent 8 divided by 1.02 exponent minus 7, okay? So this is 1.94 exponent minus 18, 1.94 exponent minus 18. But what is the unit? It's going to be joules, okay? Now, this is joules, but this is electron volts. We need to convert this. Either we'll convert electron volts to joules, or we'll convert joules to electron volts, okay? So I want to convert joules to electron volt. I'm comfortable with that, okay? So since 1 electron volt is 1.6 exponent minus 19 joules, I can say here, I can convert this to electron volt by dividing by 1.6 times 10 raised to the power minus 19 joules, then multiplying by 1 electron volt, okay? So this is what will render me to have this in electron volts, so that on the left hand side I can have minus 1.5 electron volts minus E naught is equal to, on the right hand side, let me obtain that with the calculator. The answer we just got divided by 1.6 exponent minus 19, okay, not 9, minus 19, that's going to give me 12.13, okay? So this is 12.13 electron volts, so that if I rearrange, take E naught to the other side, I'm going to have E naught is equal to minus 1.5 electron volts minus 12.13 electron volts, and that is going to give us minus 13.63 electron volts as the amount of energy that is on level N is equal to 1 as requested in this particular question. So since I've gotten that, now I need to know how to find the ionization potential of the hydrogen atom. And we're already saying that that ionization potential is the amount of energy that is required to remove an electron totally from the atom. So you can say in the second case, we are looking at the ionization potential of the hydrogen atom. That ionization potential, the ionization energy or the ionization potential is going to be E at infinity minus E naught And of course, we just got our E naught now, and we have our E at infinity to be 0. So that is going to give us 0 minus, what we got was minus 13.63 electron volts. Okay, so the ionization potential will be, the negative sign will multiply each other to give us plus. So we have 13.63 electron volts, and that is 13.63 electron volts as the ionization potential, the ionization energy of this particular hydrogen atom. Here we have to explain the statement. The work function of sodium is 2 electron volts, and then we are told that light of wavelength 116 nanometers is shown on the surface of a sodium metal of work function 2 electron volts. We are to determine whether photoelectrons will be emitted. So here is a pictorial view and the solution to our explanation that first and foremost, the minimum energy needed to remove an electron from the surface of sodium metal is 2.0 electron volt. That is the explanation of the statement, the work function. So inherently, we are just trying to define the work function, that the work function is the more energy needed to remove an electron from the surface of a metal. In this case, we are saying for sodium is 2 electron volts. So in our explanation, we need to say that from the surface of sodium metal is 2 electron volts. And in the second part, that we are being told that light of wavelength 116 nanometers is shown on the surface of a sodium metal. So this is the light in yellow, and the wavelength that we are given is 160 exponent minus 9 meters. Okay, this is not yet the threshold wavelength. Okay, it's just the wavelength that we are given, and we are just trying to find a means to see if that wavelength is actually the threshold wavelength or not. And if it is actually the threshold wavelength, then it will be able to allow electrons to be emitted from the surface of the metal. If not, maybe if it is higher or lower, we are going to get to that. We'll see the impact that is going to have. So fundamentally, we know that the work function, which is defined as phi, is the Planck's constant multiplied by the threshold frequency. But since we are not giving the threshold frequency here, we're not talking about frequency, we're talking about wavelength. So frequency is speed over wavelength. So we have this as hc over the threshold wavelength, okay, which we need to compare the value of this threshold wavelength to the value of this wavelength that we are giving to know if it will be sufficient to remove the electron from the surface of that sodium metal. Already we have been given the work function as 2 electron volts, okay, but for the electron volt we need to convert to joules because that will be the unit that will be consistent with our working. So we can say the work function, which is 2 electron volts multiplied by the conversion to joules, will warrant that, just like we are coming from the previous question, we multiply by 1.6 exponent minus 19 joules, okay, is equal to the Planck's constant 6.6 exponent minus 34 multiplied by the speed, which is 3 times 10 raised to the power 8, okay, and we are dividing this by the threshold wavelength, which we are looking for as lambda naught. So if you just rearrange, lambda naught here will be 6.6 exponent minus 34 multiplied by 3 times 10 raised to the power 8, and we are dividing with 2 times 1.6 times 10 raised to the power minus 19. So let's just use our calculator straight here. You have 6.6 exponent minus 34 multiplied by 3 exponent 8, then divided by, I need to put all of this in brackets so that it will reflect as the whole of my denominator, 2 times 1.6 exponent minus 19. Okay, so what's that going to give me? This is 6.1875 times 10 raised to the power minus 7, and the unit will have to be meters. Now, look at that value, but what we have inherently is that we are giving this as 160 times 10 raised to the power minus 9 meters. If you want to take this to minus 9, then we can shift our decimal place to 1, 2, so that this will become minus 9, and then we'll have it as 618. So let me just write like that. Now what we are going to have is 618.75 exponent minus 9. So that is laws of indices coming into play for us. So what we need to now do is to compare these two values. So what we have originally is that the original wavelength that we are giving was 160 nanometers. Okay, and here the wavelength that we got as the fundamental wavelength is 619 nanometers. So looking at this, we can see that the wavelength we got is actually higher than the wavelength that we are given in the question. And as that is the case, photoelectrons will be emitted from this sodium metal. It's going to cause photoemission to occur, because we can see that here the energy is actually inversely proportional to the wavelength. And if we put in these values, we will see that the higher the wavelength, the lesser the energy that is going to be supplied. And the lesser the wavelength, the higher the energy that's going to be supplied. So for us to have a case of the threshold wavelength to be 619 nanometers, we can see that our wavelength for this particular case is far lesser than that. And if it is lesser, okay, it is lesser, then the energy will be higher. So that energy will be sufficient to remove the electron from the surface of the metal. And since that is the case, you can say for this particular case scenario, there is going to be emission of photoelectron from the surface of the sodium metal. And with that, we've come to the end of this question 2. All right. Here in our very first question, we're asked to mention a device used for detecting fault in electric circuits, and then we have to mention one feature of the named device in A above. So I would love to actually mention a multimeter, or what some other people call an avometer. Okay, that is quite good. Or you can actually use a simple continuity tester. The difference is that the continuity tester will only check if there is no breakage in, let's say, a conducting wire. So you put one end of the wire here and you put the other end there. Sometimes those devices, they just give beep sound to show that there is actually no breakage on the connecting circuit. And a multimeter or an avometer can also do that, but in addition to that, it can also measure so many other things. Maybe you can get to measure your current, your voltage, your resistance value, and that's why you are seeing that there are many divisions here. So you can just switch to whichever one is suitable for what you want to measure, and that is as good as it gets. Now, some of the features, of course, it will need a connecting wire that's shown in red and black here. And here you are going to have a display. This is actually an analog display, but some do come as digital display, in which it digitize the result of whatever it is you are measuring. And then another thing you need for them is a powering cell for you to power the device as appropriate. So that is the answer to this question, and we are good and fine with it. This question is requesting us to distinguish between simple and compound microscopes. Okay, this is just a pictorial view of what this can look like. And in a simple microscope, we have only one converging lens as opposed to two converging lenses in the compound microscope. The simple microscope has low magnification, whereas the compound has a very high magnification, so you can see a bigger and an enlarged image of what you are looking at. And then in the simple microscope, the final image is erect, whereas in the compound microscope, the final image is inverted. So you can just pick a combination of two of these and you get your formats. Note that you are not requested to draw a diagram, but for us, we know a picture is worth 1,000 words. So showing you will actually engrain this more on you so that you will be able to recollect better if you are in your exam hall. All right. Here we are told that the mass of copper deposited on the cathode of a copper voltammeter is 450 grams when the current passed through it for 25 minutes. Our mandate is to calculate the current passed through the voltammeter, and we are given the electrochemical equivalent of copper to be 3.33 exponents minus 4 grams per coulomb. So here we are going to be making use of Faraday's law of electrolysis, which is estimating that the mass deposited in such a setup is proportional to the quantity of electricity that is passed through it. And for us, in this particular case, since we are having current, we can say that means that inherently the mass is proportional to the current passing through it and the product of time. So if we bring in the constant of proportionality, that's where we have our electrochemical equivalent Z multiplied by IT, such that in this particular case, what we are asked to find is the current passing through the voltmeter. Okay, current passing through the voltmeter will now be the mass divided by electrochemical equivalent multiplied by T. All right. So if we just want to do that with all the values that we have been given, we have the mass deposited as 450 grams, we have the electrochemical equivalent, and then the time was given in minutes. We need to convert that to seconds. So we can say the current in this particular case will be the mass 450 grams divided by the electrochemical equivalent, which is 3.3 times 10 to the power minus 4 grams per coulomb. Okay, multiplied by the time. The time is 25 minutes, so that is 25 minutes, but we need to convert to seconds, so we can say multiply by 60 seconds. So we just need to bring in our calculator to solve for this, that 450 divided by the product of 3.3 exponent minus 4 multiplied by 25 multiplied by 60. Okay, just ensure that you put in everything correctly, and then we can look at that. This is 10,000 over 11, but in standard form 909.09, so this is 909.09. the dash on it means that it's repetitive, and we can just say this is nothing but 909.1 amperes. That is the current that is passing through the voltmeter. Okay, in this question on friction, we are told that a wooden block was placed on an inclined plane as shown below. So this is a wooden block that is placed on this inclined plane. Okay, now if it is just about to slide, we are to show that the ratio of the sine of angle phi, this angle phi, to the cosine of angle phi, okay, is the same as the coefficient of friction. All right, now if we want to just prove that, we know that normally the coefficient of friction is the force over the reaction that is being experienced on that particular wooden block. And in this particular case, if we are to look at it, if this angle here is phi, and we are just to construct our angle something sort of this, we can see that this angle also is phi because it's corresponding to this. So this angle here and this, they are corresponding angles, and that being the case, this particular f and r, we can resolve them along this phi. In short, let me just move this so that we'll see this clearly. So in moving that, this is exactly what it's looking like, and if you want to resolve it, we know that we can get to just resolve this on the horizontal and the vertical component, and in that particular case, we'll see that the force upward to the plane will be given as mg sine alpha, okay, because alpha is the angle of inclination of that f to the horizontal, so it will have to be sine alpha. You can just recollect your SOHCAHTOA. If you just recollect SOHCAHTOA, you can easily work that out, okay. And then in the same vein, r that we are looking at will be mg cos alpha. Now, where is mg? Mg is actually the weight of the block acting downward. So if that is the case, our coefficient of friction, we can say is nothing but f, which is mg sine alpha, over r, which is mg cos alpha. Okay, so we can see that already mg will cut out, such that the coefficient of friction is nothing but the ratio of the sine of alpha to the cosine of alpha. Of course, that is tan alpha, but this is what we are asked to actually prove, and that has been shown as appropriate. In this question on projectiles, we are first asked what is the range of a projectile, and then I've been told that an athlete threw a javelin with a velocity of 12 meters per second. If the javelin hits the ground after 1.5 seconds, we have to calculate its angle of projection. Now we have to take the acceleration due to gravity g as 10 meters per second square. In the first case, the range is the horizontal distance from the point of projection of a projectile to the point where the projectile hits the projection plane. So for this particular diagram, that range will be defined here. So this is actually that range that we are being asked to define. And then in the second vein, we are to look at this particular case scenario in which the athlete is throwing a javelin with an initial velocity of 12 meters per second, and then the javelin will hit the ground 1.5 seconds later. We are to find the angle of projection. Now, for us to look holistically at this question, let's consider the upward movement of this particular projectile. Okay, for that upward movement, we know that generally time for it to reach maximum height, since we are only talking about the upward movement, we can get by making use of v is equal to u plus at. Now, since we are talking about the upward movement, we know that at the maximum height, the v is actually 0, Okay, the u, which will be the vertical component of its initial velocity, will now be u sine theta. Okay, theta is the angle of inclination, right? Then the acceleration due to gravity, because it's going upwards, that's going to act in the negative direction. So it will be minus g, not just a, it's minus g, then multiplied by our t. So from here I can say the time for it to reach maximum height is nothing but u sine theta over g. But then, since it's actually a two-way journey, it will go up, but it will also come down. Okay, that means the total time of flight t will be 2u sine theta over g. I know this is a formula that is quite popular with students. I just took my time to explain it out because it's going to help us now to try and solve our question as we are given here. Okay, so here we have already been given the time. Now we are looking at 2u sine theta over g, and what we are looking for is actually theta. So we can make sine theta the structure of the formula. So that means we can say sine theta is nothing but the total time of flight multiplied by g over 2 multiplied by u. Okay, so if you want to put in our parameters, that means we are saying that it is the total time of flight was given as 1.5, g was given as 10, 2 multiplied by the initial velocity will be 2 times 12. Okay, that means that sine theta is equal to, this will be 15 over 24, 15 over 24, and then theta itself will be arc sine 15 over 24. So this is what we need to put into our calculator to get our solution out. We want to say arc sine 15 divided by 24. Okay, so we can close our bracket. What's that going to give us? That is 38.682. So we can say theta itself is nothing but 38.682, or we can just say 38.68 degrees as our solution. So if you know the formula for the total time that it takes for the projectile, you can actually rearrange to get your sine theta and then find the arc sine to pick your final answer. But I just love working from the ground up, so that's why I just took my time to explain this. But eventually our final answer will be 38.68. All right. In this question, we are being asked to mention two bodies possessing kinetic energy, and then we are told that a waterfall is 108 meters high. We have to calculate the difference in temperature of the water above and below the waterfall. We have to take acceleration due to gravity as 10 meters per second square. Now, for the very first question, you need to know that for you to actually answer this question, you just need to consider any object that is moving at all. So talk about a moving car, a fruit falling from the tree, a stone that is thrown, a bullet that is fired. Any one of these is going to possess kinetic energy. The velocity is what is accounting for that. And if you are able to mention two, you are good and fine. In the second case, that we are looking at a waterfall which is 108 meters high, and that is being shown in this diagram here. Now we have to calculate the difference in temperature of the water above and below the waterfall. Now this is what they are trying to ask us, that here we can have conservation of energy from the potential energy to heat energy. Once we are able to actually get this, the question will be easy for us. And we know that the formula for potential energy, in this case for this waterfall, is the mass and acceleration due to gravity times the height which the water is actually going through, and then the heat energy is given as mass multiplied by the specific capacity of water multiplied by the change in temperature. That change in temperature is the difference between the theta 1 at the top of the waterfall and theta 2 at the base of the waterfall. Okay, so we can just call that change in theta. You can see from this formula that the mass is going to cut out, and then we have GH is equal to C multiplied by the change in theta. So we have GH is C multiplied by the change in theta. So that the difference that we are asking us, the change in theta, we can obtain by saying we are using GH divided by C. And what are the parameters that we are giving? We are giving G as 10 meters per second square. We are giving H as 108 meters. We are not giving C, so you can just leave it as C. Okay, I think C is about 4,200 joules per kilogram per Kelvin. But since we are not giving, just leave it at that, and you can finally state that the change in temperature for this particular waterfall is 10 times 108 is 1080 over C. But then you do have to mention the unit, so it is degree Kelvin, or you can say degree centigrade. Is a change, so anyone will do and they'll be fine and good. Okay, in this question we are being asked what vaporization is, and we have to state one effect of the increase in heat for a temperature range of 50 degrees Celsius to 100 degrees Celsius on first on plastic and then on iron. Okay, very good. If you want to define vaporization, you can state that it is the process in which a substance changes from its liquid state to gaseous state at constant temperature. Student, I cannot emphasize this enough that it has to be at constant temperature. Okay, that is what will earn you your formula. You don't just say it's a process in which substance changes from liquid to gaseous. That constant temperature just has to come in place. That is what will earn you your formula. And then, looking at the second question, what we are being asked inherently is to consider what will happen to this particular material. Is it going to melt, or is it going to just have some changes in its properties as a reason of the increase in temperature from 50 degrees Celsius to 100 degrees Celsius? Of course, for plastic, the plastic is going to melt because that is way above its melting point. So for the plastic, it's going to melt and then there will be change in its density. However, for iron, because that temperature is not going to be up to its melting point, it's only going to expand. And because it is also functioning as a reason of electrical resistance, it's also going to affect some changes in its electrical resistance. It will also have some changes in its density. So with this, we've been able to look at this question perfectly. This is a question on waves, and our mandate is to explain how stationary waves are produced, and then to look at this question and calculate the wavelength of this waveform that is shown in the diagram. Okay, very good and very fine. If you want to have a look at that, for the way in which stationary waves are produced, it's just by the superposition of two progressive waves that are having first the same frequency and then the same amplitude, but they are moving in the opposite direction. So like in this particular case, you are saying that this wave, this is moving in this direction and this is moving in this direction. Both of them, they are going to, they are having the same amplitude, they are having the same frequency, and then they will produce a stationary wave. And if you want to look at the waveform, now this is the amplitude and this is the time or the frequency, you can see that as one is actually going on the thick, the other is going on the broken line, and the cumulative effect of the two at any instant in time will be that they will cancel out each other. So a stationary wave will be produced. So that is the answer to the first question. In the second question, you are to look at the waveform and we are to get the wavelength. Normally, wavelength is the time it takes to complete one cycle. So here, if we are looking at this, when are we going to have a complete cycle? We are going to see that from this particular origin, this is half of a cycle and this is actually a full cycle. Okay, again we have another half here, and here we have another full cycle, and then here we have another half. So what we are looking at here is that we are having 4 meters to be synonymous to, this is one complete cycle, another complete cycle, and a half is synonymous to 2.5 cycles. Okay, so our question is asking us what is going to be the value of the wavelength that will correspond to one cycle. So this is what we have, and we can just say we want to cross multiply that. In this case, we have 2.5x is equal to 4 times 1, and if we divide both sides by 2.5, this is also by 2.5, we can see that here the 2.5 here will cut, then 4 divided by 2.5, what's that going to give us? 4 divided by 2.5, that's what? 8/5, which is 1.6. So x, which is the wavelength, is nothing but 1.6 meters for this particular waveform. So we just know that it is going to take a wavelength to complete a circle, but here we're having 2.5 circle, so which is 4 meters. 4 meters corresponding to 2.5 circle. We can find the length that will correspond to a single circle, and we just got that to be 1.6 meters. Okay, let's ask ourselves this question. Why is it that sound does not travel through vacuum? Okay, so that's our first question here. And then we're also being asked that when is the critical angle said to be subtended by an incident ray of light, or also to state one of the conditions for total internal reflection of an incident to occur. Okay, all right. For the solution to these questions, in the first case, sound does not travel through vacuum because sound needs a material medium for its propagation. So since vacuum is not a medium, it cannot travel through a vacuum. Okay, so that takes care of the very first question. Now, when is critical angle set to be surrounded by an incident ray of light? It is when the ray is reflected along the boundary of a media. So here, the ray is coming initially and then is refracted along that boundary of the media. Then in that case, we are saying that the critical angle is subtended by that incident ray of light. Okay, and then one of the conditions for total internal reflection to occur, there are just actually two of them, this and this. In the first case, the ray must be traveling from a denser medium to a less dense medium. So the original source of the ray will be more dense, meaning that it's going to restrict the movement of that ray of light as compared to the other medium that light is traveling to. And then the second condition is that the angle of incidence in the denser medium will be greater than the critical angle of the medium. So once that angle of incidence is greater than the critical angle, then total internal reflection will definitely occur. All right. Here we are looking at a question in electricity. We are being asked what is lost volt and to state two advantages of secondary cell over primary cell. So this is just as good as it gets. In the first case, looking at lost volt, it is the voltage drop due to the internal resistance of a cell. So here you can see we have this particular cell. Okay, that is actually supposed to be producing the voltage V in this particular circuit, but that cell itself is having an internal resistance R. So what we are going to have is that, of course, and the same current will flow in a series circuit. So the V that we are having is going to be nothing but the current multiplied by this small internal resistance of the cell itself, then plus the current multiplied by the load, the resistive load that is applied on the circuit. So what we are looking at when we are talking about lost volt is the product of the current multiplied by this internal resistance of the cell. So this is what is regarded to as the lost volt. Okay, and then in the second question, the secondary cells, actually the advantage it has over the primary cell is that first, it produces current for a longer time. You can use it for quite a longer time as compared to the primary cell. Then of course it can be recharged. So you use it, it's depleted, you charge it, then you can use it again, charge it, use it again. But for the primary cells, once you use them, that is all. You just need to discard them, or even need to discard them properly. Okay, so that is that with respect to this question. We are still continuing with our questions on electricity, and here we are to state the condition under which resonance occurs in an AC circuit. And then furthermore, we are being told that a series circuit of 5 ohm resistor, 2.3 millihenry inductor, and 0.03 microfarad capacitor is connected in series to an AC source. Our mandate is to find the resonance frequency given that pi is 3.14. Okay, so that is good and fine. Here, this is going to be the solution to our question. In the first case, resonance will occur when the inductive reactance is equal to the capacitive reactance in an AC circuit. So this second question is actually a very typical case scenario of when we have resonance, because they are asking us to find the resonance frequency. So what is happening is that at resonance frequency, SC is actually equals to XL. And what's the formula for XC? What's the formula for SL? That means we are saying that XC is 1 over 2 pi FC, okay, is equal to XL is 2 pi FL. So this, if you actually cross multiply and rearrange, we are going to get that the frequency, which is the resonance frequency, is nothing but 1 over 2 pi multiplied by square root of LC. Students, you can actually lay your hands on this and try to get the formula out. But starting from where we are coming from, the resonance frequency is actually given as this. And for this question, that's exactly what we are going to be using to say that here, what is our L? Our L is 2.3 millihenry. That is 2.3 milli means times 10 raised to the power minus 3 Henry. Okay. And what is our capacitance? Okay, that is 0.03 microfarad. That is 0.03. Micro means times 10 raised to the power minus 6 farad. So if we want to use these parameters, we can say our F is nothing but 1 over 2 pi. Pi will have been given as 3.14. Then multiplied by the square root of L, that is 2.3 times 10 raised to the power minus 3, multiplied by C, 0.03 times 10 raised to the power minus 6. So you just need to capture this correctly so that you don't make any mistakes, students. with this we can now find our resonant frequency by bringing our calculator to say we want to look at 1 divided by, I want to put everything in brackets, 2 times 3.14 multiplied by the square root of now I want to put this everything together in brackets so that I don't miss out that square root. So I have 2.3 exponent minus 3, okay, times 0.03 exponent minus 6. So I can close that bracket, come out of that and check to see that I'm actually on the right track, and then I can press the equal to sign. So this is 19169.72, 19169.72, okay. You can just say I want to approximate this, and if I bring this decimal 1, 2, 3, 4, okay, 4 places, I can say this is 1.92. I'm rounding up this 6 to 1 and adding to this 1, then times 10 raised to power 4. I've moved the decimal place in 4 places, and then the unit for frequency is hertz. So that is going to be the resonant frequency for this particular circuit as given in this question. In this question, we are to mention 2 types of unit cells of a cubic crystal other than the face-centered cubic, and then we are to calculate the half-life of a reactive element of decay constant 0.0385 per second. Okay, good and fine. The other unit cells apart from the face-centered cubic is simple cubic crystal as typified in sodium chloride crystal, and then the body-centered cubic crystal. So if you just mention these two, you are good and fine with question number A. Okay, and then in question number B, we are being given that the decay constant lambda is given as 0.0385 per second. Our mandate is to find the half-life. Now, half-life in this particular case is given as 0.693 divided by lambda, and since that lambda, the decay constant, was given as 0.0385, we can just put in the value to say this is 0.693 over 0.0385 per second. So we just want to put that value there. We can make use of our calculator. 0.693 divided by 0.0385. This is 18. Okay, so this is 18, and now it's as if we are reversing this, so it will be 18 seconds as a half-life of this radioactive element. Here in this question, we are being mandated to draw a label diagram of a photocell and also mention 2 applications of a photocell. So no problem. If you want to draw a photocell, I'll just do a simple diagram here. You can have this, and typically we are going to have an anode, okay, that is going to be collecting rays of light, and then a cathode that's going to be receiving electrons from there. So I can link this to a microammeter, and then I can have, let's say, battery source, and just finish up like this. Okay, so normally the operation of the photocell will be that rays of light will be coming in incident on the anode. Okay, so this here is the anode, this is the anode, and then here this is the cathode. And then with those rays of light coming in, what we are going to be having is that electrons will be ionized and they will move to the cathode from the anode, and then that will complete the circle such that we can have electricity flowing in this particular case. So this is just a typical example of what we have. And here, critical things to note is that here we are going to have vacuum. This is actually vacuum, and of course this is an evacuated glass tube, so that's why inside it we are going to have vacuum. So this is just a very simple diagram of a photocell. When you are drawing, you can just represent the anode as a single line, represent the cathode as a single line. Maybe you just draw your evacuated glass tube, just do something like this, and you are good and fine. Okay, so you don't need to be too artistic if you are drawing. I just want to give a good representation for you. If you can do this, fine and good and no problem, you also be awarded your full mark. That is not a problem. So let me just straighten this up a little, okay? And then I can just include this as a glass tube, okay, which is evacuated. That's why we have vacuum in that particular. So if you can label all of this and just get it like that, you are good and you are fine. And then to look at the applications, this photo cell actually finds applications in burglar alarm, automatic door, TV camera, detection of light, measurement of light intensity. So that is that with respect to this particular question. Here we're asked to explain fundamental quantity and to measure two quantities which have the same unit as energy. As a reason of definition, fundamental quantity is any physical quantity that is not dependent on other quantities. It's a standalone quantity. It's any of the quantities from which other quantities are derived. So that's why we call it fundamental. Okay. Now, in the second question, we are being told that we are to look at two other quantities that have the same unit as energy. Okay, let's say we want to look at potential energy. Okay, we know that potential energy mathematically is given as mass translation due to gravity times h. And if that is the case, we want to break this down. We can say this is inherently mass. We can't break down to any other quantity again. Acceleration due to gravity is velocity over time. Velocity itself is, maybe you can say, displacement over time, then multiplied by 1 over t. So it's velocity over time. That is acceleration due to gravity. Then height, that is just distance, so I can call that d. So what we have here is we have m, a single m, d we have in two places, then t at the denominator, that is t raised to the power minus 2. And we want to put it as the base fundamental unit. We can say this is nothing but, for the mass we have m, for distance that is l raised to the power 2, and then for time that is capital T raised to the power minus 2. So what we are looking for inherently are two other quantities whose dimensions is going to be ml squared t minus 2. Okay, so if you want to look at that, I know that work and moment are going to give us that exact dimensions. And what is work? Work is actually force times distance. Okay, force itself is mass times acceleration. Okay, then we still have distance there. So if you want to look at the breakdown of this, you can say mass, this is just m. Okay, acceleration is velocity over time, that distance over time, which is velocity, then over time 1 over t, then multiplied by distance. I have that as d. And you can see that is corresponding to what we have here exactly, that we have it as md squared and t minus 2, which inherently will still land out as ml squared t raised to the power minus 2. So that is quite on track. Work is having the same unit as energy. We did this breakdown of the dimension for us to get that. In the same way, we can look at moment. Moment is actually a turning force. So it is force multiplied by distance moving in the perpendicular direction. Like for example, you have we have a wrench. If you have a wrench that you're actually using, and then you are turning it, maybe you apply a force like this, and this is the perpendicular distance, and this is F. Moment is the product of that force multiplied by the particular distance. So eventually it will just give us something like this again, that we're having force and distance, which is MAD, and eventually MAD. And then that will also give us MD squared t raised to the power minus 2, whose dimension will also be ML squared t raised to the power minus 2. So we can see that energy, in this case, we even use potential energy as a case study. You can use kinetic energy. Students, you can just try your hand on that. Use kinetic energy, okay, half mv squared, and then you could see that you also arrive at the same thing here, and we have found that work is also having the same, moment is also having the same. So work and moment, they have the same unit as energy. All right. Yeah, in this question, I'm being told to sketch a velocity time graph of the motion of a pendulum bob which is swinging from one end to another, okay? So if you want to look at that, this is what the movement of that pendulum bob is going to be like. So maybe you can see here, it's just fixed, okay, and then the bob is swinging from left to right, left to right, left to right. Now, this is what we notice. If you actually take this particular, let's say this is point A, this is point B, and this point C. What you notice is that at every point in time, the pendulum bob is tending to return to point B. Okay, so even if you are starting from B and you are going to C, you discover that it will get to a point, it will revert back to B. Then it will go to A. Once it gets to A, it will also what? Revert back to B. So generally, since the acceleration is directed to the center, to B, then that means that your velocity time graph will take a shape and look like this. From here, which you can say is A, it will come here, it will peak at B, and then it will go back to C, and then it will just repeat that circle again and again. So I can call this point A, just as a reason of explaining what I have over there. I can call this point B, and I call it point C. So this is going to be the velocity time graph. The velocity will increase anytime it's pointed towards the center, towards B, okay? And once it's going away from B, the velocity will decrease. So this is actually how the velocity time graph will look like. And once we'll be able to sketch this, we are good with the question. So here we are told that a meter rule of mass 15 grams pivoted at the 30 centimeter mark, balanced horizontally when a load of 25 grams was hung at the 18 centimeter mark. First, we have to sketch the setup, and then if the position is moved to the 33 centimeter mark, by how much we need to be careful there. By how much must the load be reduced to maintain the horizontal balance of rule? Let's first take this first scenario, okay? Because if we are moving it, that means we need to draw another diagram. So let's just first and foremost try and sketch the setup. So we are told that the meter rule is having mass 15 grams. Then we will take the assumption that it is a uniform meter rule, okay? So it being uniform means that the weight will act in the middle, okay? So this will be the weight of it, and that is 15 grams, okay? Then it's pivoted at the 30 centimeter mark. So 30 centimeter, maybe something here. It's pivoted there. It balanced horizontally when a load of 25 grams was hung at the 18 centimeter mark. So 18 centimeter, if this is 30, maybe middle will be here. So 18, middle here, 18 will be somewhere here. So this is a load of 25 grams. Okay. So for that setup, I would just like to just depict my distances to say, yeah, this is 18 centimeters. So I will have 18 centimeters. Okay. And then here we are told that the pivot is at 30 centimeters. If we've taken 18 out, that means this will be 12 centimeters. Okay. And then that is an addition of 30. This will now be 20 centimeters. So that the 3 addition will be 50. And then again, I will have the other 50 centimeters at the other end of the round. So what we are asked to draw is just as shown here. In the first case, this is the solution that they're expecting us to do. Now, for the second question, that they are told that we are being told that the position is moved. Then we also need to move the position. Okay, so you have this diagram first. Okay, and then you draw a. Sure, let me just draw again, so that we would not just be confused. We will just know that yes, this is the way to go about it. So still the weight we have at the middle. So this is 15 grams, but now the pivot is moved to 33 centimeters. Let me say this is my 33 centimeters. So this is 33 centimeters. Then the load was initially at 18 centimeters. So we still have this load here at 18. So this is, we don't know it now. We don't know the new weight because they say that by how much must the load be reduced. But we just know that from here to here, this is 18 centimeters. Okay. So know this is 18 centimeters. Okay. And then since from the edge of the meter rule to the center is 50, 33 being out means that this remaining one will be 50 minus 33, and that will be 17 centimeters. Okay. For the body to be in equilibrium, we know that the sum of the clockwise moments and the sum of the counterclockwise moment must be equal, and here we only have 1. So here, if you are taking moment about this fulcrum here, then we can see that this x gram will be a counterclockwise moment, and this 15 gram, the weight of the meter rule itself, will be a clockwise moment. And since we are saying that the sum of the clockwise moment must be equal to the sum of the counterclockwise moment, and that moment is 4 times perpendicular distance. So here 33 is from the edge of the meter rule to the fulcrum. 18 is out of it already, so this will be 33 minus 18. So this is 15 centimeters. Okay, let me just clarify that so that there will be no confusion there. Okay, so taking moment about the fulcrum, we can say this particular force, x multiplied by 15, we can say that 15x is equal to this particular 15 multiplied by its own distance 2, and that is 15 multiplied by 17. Okay, so we are using the product of the mass, the weight, times the perpendicular distance at right angle to it. So that's why we are getting this, that the sum of moments counterclockwise is equal to the sum of the moments in the clockwise direction. So this is what is warranting us to get this. And of course, we can see that this 15 can cancel this 15, so that S itself is actually 17 grams. But nobody asked us to find S. They said by how much must the load be reduced. So since initial load was given as 25 grams, now the new load we just got to be 17 grams. Then the reduction, this is where it gets interesting, and this is where you need to actually read your question one, will be 25 minus 17, and that will be 25 minus 17 is 8 grams. So 8 grams must be reduced from the initial load for us to have this particular meter rule still in equilibrium, for it to be balanced. All right. Now in this question, we are asked to distinguish between elastic and inelastic collisions, and for us to just take it on a light note, this is a pictorial view and a table list of what we are being asked. In the first case, for the elastic collision, kinetic energy is not conserved, and then the final velocity after collision is not the same. So this is u1, this is u2. If they collide, you can see that v1 and v2, they are not the same. They are still moving in some different direction as typified in this diagram. Okay, so the bodies also do not stick together after collision. You can see they are going their different ways. But in inelastic collision, kinetic energy is not conserved at all in this case. And then if they are initially moving with initial velocity u1 and u2, after the collision, the final velocity after the collision is the same. They have a common v, okay, and then the bodies, they stick together after the collision. So the prospect is that, just as noted by Cartoon Guide to Physics here, so if it is in elastic collision, then they're supposed to stick together, move on, and in that case kinetic energy is not conserved. But if it is elastic, the major issue is that kinetic energy is conserved, and then their final velocity is not the same. So here in this question on heat, we are told that a calorimeter containing 65 grams of ice at minus 10 degrees Celsius is heated uniformly until it boils after 180 seconds. Our mandate is to sketch a labeled graph to illustrate the variation of temperature of the ice with respect to time. So we have our graph here, and what inherently we are being asked is that what is going to be the stages that the ice at minus 10 degrees Celsius is going to pass through from the state in which it is ice to the state in which it boils and vaporizes at 180 seconds. So if we are to look at that, this is just a very good denotation of what we can get, and I've just noted a number of points here. Now from minus 10 to 0, taking its temperature from minus 10 degrees Celsius to 0 degrees Celsius, initially it was ice, but now it's being converted, is melting, okay? And now when it gets to 0 degrees Celsius, what is going to happen is that at that constant temperature, some time is going to elapse in which that particular ice is going to be liquefied. And then once it has turned completely to water, it will increase in temperature until it gets to the boiling point of water, which is 100 degrees Celsius. Then after then, it's just going to be maintaining that 100 degrees Celsius, but vaporization is going to be occurring. So this is actually the graph that we are asked to construct. In this question, we are told that a 40 Celsius thermometer reads 5 degrees Celsius at the melting point of pure ice and 95 degrees Celsius at the boiling point of water at normal pressure. So that's quite interesting. Both the upper and lower readings are quite wrong. Our mandate is to calculate the correct temperature reading when it reads 40 degrees Celsius, and then we're also to check the temperature at which its reading will be exactly the same as the correct temperature reading. Okay, no problem. So if we are to look at something like our thermometer here, and with information that we are given that is reading 5 degrees Celsius at melting point, we know that melting point originally is 0 degrees Celsius. So we can denote it that yes, when it's reading 5 degrees Celsius, it's actually supposed to read 0 degrees Celsius. Quite good to note that. And it's also reading 95 degrees Celsius at the boiling point of water. So we know that the boiling point of water is supposed to be 100 degrees Celsius. So this is the reading of the 40 thermometer, and this is the original reading that is supposed to be reading. But we're also noting, first and foremost, they say that we have to get the correct temperature when it reads 40 degrees Celsius. So that's why we are calling that X. And what we just need to do in this particular case is just to look at a graded difference and try and cross multiply. Like here, this scale here, we'll just relate it to the scale on the right hand side. So I want to take, for me, I love taking the difference, okay, from the unknown to the base, and then from the maximum to the lowest. So I can say X minus 0 over 100 minus 0. So I'm taking this minus 0 first, then I'm saying 100 also minus 0. So the same thing I also do to the reading of the thermometer, that this is equal to the corresponding value for X will be 40 minus the lower limit now is 5 over 95, which is the upper limit, minus still that same lower limit 5. So I can say from here I just have X over 100 is equal to 40 minus 5 is 35, 95 minus 5, that is 90. So I can cross multiply in this particular case to say X is going to be 35 times 100 divided by 90. Okay, so if I bring in my calculator for that, 35 times 100 divided by 90, so this is 38.8. the bar means that is a repeated value, so I can just say we have 38.89 degrees Celsius as the value of X, which is the reading when the thermometer is reading 40 degrees Celsius. So that is the very first thing we are asked to find. In the second case, we are asked to look at the temperature at which the reading will be exactly the same as the correct temperature reading. So let me just say I'm assuming that in that case, what I'm going to have is something like a value, this is Y, and here the value is also Y. Okay, so just like I did there, I can say this particular reading minus the lower limit over 100 minus the lower limit. In this case, the same Y minus the lower limit over 95 minus the lower limit. So that's what I would just like to do now, to say here I'm looking at Y minus 0 over 100 minus 0 is equal to Y minus 5 over 95 minus 5. Okay, so I can say what that means is we have Y over 100 is equal to Y minus 5 over 95 minus 5 is 90. So easily I can say I want to cross multiply this, that 90Y is equal to 100 times Y is 100Y, 100 times minus 5 is minus 500, such that if I rearrange, I'm going to have 100Y minus 90Y is equal to 500, and that means that 100 minus 90 is 10Y is equal to 500. Then dividing both sides by 10, that means that inherently this 10 will cut this 10, and then Y that I'm looking for will be 500 over 10, which is 50 degrees Celsius. Okay, so the midpoint is still the same, and then the temperature which the thermometer will be reading and then which is also the correct temperature for this particular case is 50 degrees Celsius. All right. Here in this question, we are being asked to state Snell's law of refraction. We're also being asked that why does a musical note of the same amplitude and frequency being played on a flute, guitar, and trumpet sounds different? So for the solution to this, we'll look at to say that Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media, and that ratio is what we actually call the refractive index. Okay. On the other hand, musical notes is of different sound in different musical instruments due to the presence of notes that are various frequencies that are produced along with the fundamental frequency, or we can say that it's because of the overtones or harmonics of different, or maybe we can say higher frequencies or pitch of the higher frequencies that are being produced. Okay, so the fundamental frequencies are there, but then the overtones, the subsequent ones that will be building on it, they're actually going to be overtones, and then they will have different pitches. That's why sound will sound different in a flute, guitar, and trumpet as compared to one another. Here in this question, we're being mandated to look at similarity and differences between a camera and the human eye. So if you want to look at it, for the similarities, both of them use converging lens, and both of them are sensitive to light. And then for the formation of the image on both the eye and the camera, the formation of the images are normally inverted. Okay. And now for the differences, the camera has a fixed focal length, but the human eye can actually have varied focal length. You can actually tend to tint your eye or maybe focus more, so that will just a little bit affect the focal length that you are going to actually form eventually. Now, distance between the film and lens can be varied, but the distance between the lens and the retina is fixed. There's no way you can change it. It's there and it is as good as it comes. Then of course the camera is a mechanical device, while the human eye is actually a natural organ. All right. So here in this question, we are being told that a light ray traveled from water into the air at an angle of incidence of 30 degrees, and we are to calculate the speed of that light ray in water and the angle of refraction in the air. Okay, very good. But we need to note some peculiarities to this question. We are told that the light ray is traveling from water, so this is water. Okay, and then it's traveling to the air. So that is what we are giving, and then we have to find the speed in water. So speed in water we are looking for. We have to find the angle of refraction in the air, r in the air. That's also another thing that we are looking for. As a rule of thumb, we should know that the refractive index is actually given as the speed in air as a ratio of the speed in the medium we are considering. Here the medium is water, so refractive index of water is actually the speed of the light ray in air over the speed of the light ray in water. So since we have been given that n to be 1.33, and then we have the speed of that light ray in air to be 3 exponent 8 meters per second, we can find the speed in water to be the speed in air over that refractive index. So that will be 3 times 10 raised to the power 8 meters per second divided by 1.33. So to say I have 3 exponent 8 divided by 1.33. So this is, let me put this in standard form. Okay, so it's exponent 6. If I want to move this point in two places, I can say 1, 2. So this will be exponent 8, so it will be 2.25, but I have this 5, so it have to be rounded up to 1 and added to the initial 5. So that's 2.26 exponent 8. So this is 2.26 exponent 8 meters per second as the speed of the light ray in water. So that is the first solution that we need to get. In the second case, we are going to have to look for the angle of refraction in the air. So we can make use of sine I over sine R. But now sine I over sine R will have to be the refractive index in the air, which is generally unitary, okay, over the refractive index in water. So now we are doing like this because we are moving from water to air. That's why we need to reverse this particular refractive index. Initially, is originally that the refractive index of air over the refractive index of water. But since the refractive index of here is just 1, we are good and fine like this, such that if we cross multiply, if we are to cross multiply here, we are looking for sine r. We already have sine I. We can say sine r is equal to n sine I. So that sine r means the angle of refraction in the air that we are looking for is equal to n, which is 1.33 multiplied by sine I. Sine I is sine 30. Sine 30 is actually 0.5. So this is 0.665. Okay, so r will be the arc sine of 0.665. Okay, so we can use our calculator. Arc sine 0.665. What's that going to give us? 41.682. You can just say 41.68. This is 41.68 degrees. So our understanding of the fact that this particular ray of light is moving from water to air had helped us to holistically solve this question to find the speed in water and then the angle of refraction in the air. Here in this question, we have to state the mathematical representation of the Newton's law of gravitation. So notice what we are being asked. They are saying what they are interested in, nothing but the mathematical representation. So you just need to write out the formula for that Newton's law of gravitation, that the force of attraction between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. Now the r is the distance between those two bodies, the masses are m1 and m2, and g is the gravitational constant. So once you just write out this, that is as good as it gets. Your full mark is assured. I'm just including this as a pictorial view for you to understand what we are talking about in this case. Here in this question, we are being asked that how is the compass needle used to draw magnetic lines of force around a bar magnet? Now, student, you just need to be able to capture this effectively. In the first place, you need to place the magnet and compass on a plane sheet. So here we have the magnet, we have the plane sheet, they are placed together, okay? And then you have to adjust the position of the compass until the needle is pointing away from the magnet, and you mark the position of the head and tail of the needle. So this is what we are talking about here. So if you put the compass here initially, you can see that the pointer is pointing towards the magnet. So we don't want to start from there. We want to start in a position in which that needle will be pointing away from the magnet. And so this here is that particular position, okay? And once you get that, you are going to move the compass to another further point from the magnet. Then you also mark the needle position in that location. So that's why we're having something like this here again, okay? And then just repeat the procedure here, you repeat the procedure here, you repeat the procedure here, until you are seeing the pointer also touching the magnet in this particular last case. So after doing all of those, what is left is for you to join all those marks, all those arrows that you have actually drawn, the one shown in blue here, okay? You just join them with a line. So this is like that line we're talking about, and then we would have drawn one magnetic line of force. Then you just repeat the process, do another one, and that is how it's just being done. Now this is how it's being postulated, that whenever you see a magnet and you are seeing lines of forces drawn from the north to the south pole, is an assumption that yes, we've done this and we have gotten those magnetic lines as acting in that direction. So experimentally you can also do that, and this is what you are going to get in that case. All right, a good question for us to consider here is that we should distinguish between series and parallel combinations of resistors. So this is just a table highlighting those differences, and this is a diagram that is also depicting here in the first case the resistances in series, and here the resistances in parallel. For the resistors in series, the voltage across each resistor is different because it is current that is the same in a series circuit, okay? But voltage across each resistive load is going to be different. So we have V1 for R1 and V2 for R2. However, in a parallel setup, it's the same voltage that is flowing across loads in parallel. Resistors in parallel will carry the same voltage. So V across R2 is also equal to V across R1, okay? So for the current that is flowing, same current is going to flow across each resistor in a series circuit. However, when you are looking at a parallel circuit, the current will be different. So that's why we have I1 and I2, okay? Now, in a series circuit, the effective resistance is the sum of the individual resistances. So in this case, R total is going to be R1 plus R2 for the series setup. But in this particular case, it is the inverse. The effective resistance we are going to have here, 1 over R total is equal to 1 over R1 plus 1 over R2. So if you want to find the LCM, you can say what you are going to be having is something like 1 over R total is equal to, LCM will be R1, R2. Then if you just factor, this will be R2 plus R1, so that your R total will be the inverse of that it is R1, R2 divided by R1 plus R2. Okay, and then finally, the effective resistance in a series circuit is going to be greater than the parallel arrangement of resistors. So R total here is actually greater than this R total. Okay, so these are just the differences between series and parallel combinations of resistors, and if you are able to think 3 points, if you are able to raise them effectively, that should be good and fine to earn you your full marks as requested in this question. Here we are being told that a current of 3 amperes passes through a heating coil of length 65.2 centimeters, which has a cross-sectional area of 3.2 millimeters square. So students, first and foremost, I want you to just note insight into what you are being given. Here the length is given in centimeters, the cross-sectional area is given in millimeters square. So those are not the same, but we need to be consistent with our unit. Okay, and then this particular heating coil have a resistance of 3.5 ohms. If the current passes through the coil for 5 minutes, again, that is in minutes, we need to convert to seconds. If you are going to be using that, we have to calculate the resistivity of the coil and the energy that is dissipated by the coil. So this is a pictorial view of what we are having. And then for me, I would just like to first and foremost convert all the units. Here we have 65.2 centimeters, and that will be 65.2 times 10 raised to power minus 2 meters. So that's going to give me 0.652 meters. Okay, so this is the length of the heating coil. The cross-sectional area we are given as 3.2 millimeters square. Now you need to be careful. We are talking about millimeter, but not just millimeter. We are talking about area, so it's the square of the millimeter. So for us to convert, we need to say this is nothing but 3.2. Okay, if it is just a singular millimeter, we would have said times 10 raised to power minus 3. But because we are squaring it, so we also need to square this. So this is nothing but 3.2 times 10 raised to power minus 6 meters square. So that is what we need to note so that we don't make mistake in this particular case. So we are giving the resistance to be 3.5 ohms. That's good. And then we are giving the time in which the current is passing through it to be 5 minutes. That will be 5 times 60 seconds, which is 300 seconds. So we can now go ahead to try and find the resistivity of a coil. Generally, resistance of a conductor is given as resistivity multiplied by length over the cross-sectional area, such that from here we can find our resistivity to be the resistance multiplied by the area divided by the length of that particular conductor. So if you want to put in all the parameters, we have resistance, we have the area, we have the length. You can say our resistivity in this case is going to be, the resistance is 3.5 ohms multiplied by the area, that's 3.2 times 10 raised to power minus 6 meters square, over the length. The length is 0.652 meters. So we can just get this. We can use our calculator to evaluate this, that we have 3.5 times 3.2 exponent minus 6 divided by 0.652. So what's that going to give us? So this is 0. Okay, let me just put that in 17.18, or if I just move this again, 1.72 exponent minus 5. Okay, so this is 1.72 exponent minus 5, and what's going to be the unit? It will be ohm. Now this meter would have cut this meter to remain only 1 m here, so it is ohm meter. All right, so that is the resistivity of this particular heating coil. Okay, so in the second case, we are asked to find the energy dissipated by the coil. Energy for this particular case we can find by saying it is the product of the current multiplied by the voltage multiplied by time. And if you look at all of those, okay, we don't have the voltage, but we know that voltage is IR, so here it will just be I square r multiplied by t. So our I, it is 3, we have 3 square. Our r is 3.5, okay. Our t is 300 seconds. So you just need to find this on the calculator to say we are having 9 multiplied by 3.5 multiplied by 300. Okay, so this is 9450. So this is going to be 9450 joules as the energy dissipated, and we have gotten the resistivity of the coil initially. In this question, we are asked to define viscosity, and we are also asked to state two fundamental assumptions of the molecular theory of matter. Here is the solution to this question. The viscosity is the internal friction that exists between the layers of molecules of fluids, whether it be liquid or gas. So that is what we actually allow sometimes maybe a pond skater to actually be on the surface of the water, because there is some level of viscosity on the water surface. Okay, so that is that about that. Now, for the assumptions of the molecular theory of matter, number one, we can say that matter is made up of molecules, and those molecules are in constant rapid motion, and they also experience force of attraction. And then, of course, matters can exist in solid, liquid, and gaseous state. So this holistically will help us to answer this question, and that will be done with that. Here we are being told that the kinetic energy of electrons that is emitted from a metal surface when light of frequency f falls on it is 4 exponent minus 19 joules. Now, if h is the Planck's constant, we are to express the threshold frequency of the metal in terms of the given parameters here in the equation. So this is quite interesting. You can notice that we are not giving any value of the constant, like we are not giving h to be a particular value, and we are not giving c to be any particular value. That's why they are saying that we should express the threshold, okay, threshold frequency in terms of the given parameter. So that's what we'll try to do in this particular case. But this pictorial view is helping us to explain it, that okay, there is this light of frequency f, and of course the amount of that energy that's coming from the light is hf. Okay, when it is incidence on this metal, there is a kinetic energy with which electron will be emitted, and of course the metal itself has inherently a work function, and what we normally work with is that the energy hf is actually equal to the work function plus the kinetic energy in this particular case. All right, so if that is what we have, hf is the photon energy, f is what we are given as just ordinary f. We are not giving its value, but we are given that the kinetic energy that is emitted is 4 exponent minus 19 joules. So in this particular question, we can say hf, which we still have, is the work function. Now the work function itself is the product of the Planck's constant and the threshold frequency f naught. So we have it that this is hf naught plus, since we are giving the kinetic energy, we don't need to write k already. We just need to write it is 4 exponent minus 19 joules. So since we are asked to express the threshold frequency in terms of the terms, then we should make f naught the subject of the formula in this particular case. So here, if we are to rearrange, we can say hf naught is going to be, when this 4 moves to the other side, we have hf minus 4 exponent minus 19, and then f naught itself is going to be hf minus 4 exponent minus 19 divided by the Planck's constant h. Okay, and if we want to break it into its constituent terms, we can say is that f naught equals to hf over h is actually f, then minus, we still have 4 exponent minus 19 divided by h. I just broke this into its two terms, hf over h, then 4 times exponent minus 19 over h, and this is what we are going to have, and the unit is going to be at. So this is the expression for the threshold frequency of this metal in terms of the given parameters for this particular question. Here in this question, we are told that light of frequency 6.62 exponent 14 Hz is incident on the metal surface with work function 2.08 exponent minus 19 joules. Our mandate is to calculate the wavelength of the light and the energy of the light. So here in this question, we are given the Planck's constant h, and we are given the speed of light. And a typical example of what this scenario is looking like is this. We have some photon of light that is of some particular energy incident on this metal. We are looking for the wavelength, and we are looking for that energy, but we are given f. So we are given the frequency that it is 6.62 exponent 14 Hz. Okay, And then we're also given the speed of light to be 3 exponent 8 meters per second. Generally, we know that the velocity of light is given as frequency multiplied by lambda. That velocity here is c. So let me just put that what we are actually having inherently is c. Now this is c is equal to frequency multiplied by lambda. So the wavelength lambda will be the speed of light over the frequency. And since we have the speed of light and frequency, we can say lambda in this case is going to be 3 times 10 raised to the power 8 over the frequency 6.62 exponent 14. So we can bring in our calculator to say 3 exponent 8 divided by 6.62 exponent 14. So this is going to give us 453 exponent minus 9. But if I move it 2 places back, if I move the decimal point 2 places back, that will be 4.53 exponent minus 7. So that's expressive enough. 4.53 exponent minus 7. And what's going to be the unit for the wavelength? It is meters. Okay, so that is as good as it gets. So this is question number 1. In question number 2, we are asked to find the energy of the light, and already we have defined that energy is actually the Planck's constant multiplied by the frequency. Do we have the frequency? Yes. Do we have the Planck's constant? Yes, we are given. So that energy is going to be nothing but the Planck's constant h 6.6 exponent minus 34 and the frequency 6.62 exponent 14 at. Okay, so again our calculator will be of help to us here. We have 6.6 exponent minus 34 multiplied by 6.62 exponent 14. So please just ensure that there's no mistake. You can check and check again that you put the values correctly, and you can solve for that. That's 4.3692 exponent minus 19, or I can say 4.37. so this is 4.37 exponent minus 19. And what's going to be our unit for energy? That is joules. So this is just how we go about solving this question, and will be good and fine. Here in this question, we are asked to list 4 components of a slide projector, and this is a pictorial view of the slide projector, which is an optomechanical device. You just put in your picture slides into like this slot, and then the mechanism with which is going to work and project those images that you have inserted onto a projecting screen. So some of the components include the projection lens, okay, the slide carrier that you are going to insert your slide in, a condenser, the light source that will be beamed on those particular images, a concave mirror through which the light rays will pass, and then you also need a projector screen and co. So if you are able to just list like 4 of these, then you'll be good and you'll be fine, and the question would have been answered and dusted. Here is a question asking us how electricity is being generated from a dam. Okay, so let me just use a picture to explain this. Normally, as simple as it gets, just for you to answer the question, you can say that the dammed water will pass or fall through a narrow opening of the dam, and it will rotate a turbine. The turbine in turn will rotate the dynamo which generates electricity. If you are able to state that, that is good. But for me, I used to say this: a picture is worth 1,000 words. So here, this is the reservoir. Okay, let me use ink, red ink. So this is the reservoir. Okay, and this is the dam. The water has been stopped initially. So if you want to actually start generating electricity, the water inlet will ask to pass through this penstock, and then that water, as it is flowing, it will be turning this particular turbine, and the turbine itself will just rotate the dynamo that will go ahead to generate electricity, which can now be passed through the transformer and then connected to the transmission lines and distributed to wherever it is that it is to be distributed to. So this is just as good as it gets. If you're able to just state these 2 statements, you'll be good and fine and earn your full marks. Here in this question, we are to contrast a wet Leclanché cell and a lead acid accumulator. So here is the tabulated differences. If you want to compare, maybe any 2 or 3 will be sufficient. In a wet Leclanché cell, you will notice that it is just a primary cell, whereas the accumulator cell is a secondary cell. The positive terminal of the Leclanché cell is carbon rod, but the positive terminal for the accumulator cell is lead peroxide. Okay, negative terminal of the Leclanché cell is zinc rod, but the negative terminal of the accumulator cell is lead. Now the Leclanché cell cannot be recharged, whereas the accumulator cell can be recharged and reused. And For the Lagrange cell, the current only lasts for a short time, but for the accumulator cell, since it is a secondary cell, the current will last for a long time, and then even the durability definitely will last far more longer. So you can find that as being used in your motor vehicle because it is being recharged and the current can last for a long time. And here we are being told that a load of 200 kilograms is raised through a height of 6 meters in 4 seconds. We are to calculate the time rate of energy that is used in horsepower. Okay, so if you want to have a pictorial view of what we are talking about, it's just something like this here, in which we have that load 200 kilograms as the mass. So here, this is the mass. Okay, then 6 meters, this is the height, and then the time that was taken is actually 4 seconds. We are to calculate the time rate of energy that is used in horsepower. We are giving G to be 10 meters per second square and 1 horsepower to be 746 watts. So what is the formula for the time rate of energy? Look at what they are saying. They say the time rate of energy. That means we're actually talking about power. Okay, it's power, it's not energy. So you can see that for this particular case, the power is going to be mgh over t. That's just energy over time. And since it is an object being raised through some height, so this will be good and fine. So if you want to put in those parameters, that power will be the mass, which is 200 kilograms, multiplied by the acceleration due to gravity 10, multiplied by the height, which is 6 meters, divided by the time, that is 4 seconds. So you can say 4 here 1, 4 in 20, that is 50. So we have 500 times 6. 500 times 6, that is 3000 watts. Okay, but now look at what we are giving. We are being asked to find it in horsepower. We are given that 1 horsepower is equal to 746 watts, but now we have this 3000 watts, but we are looking for the equivalent amount of horsepower. We can call that x, and with x, if we cross multiply here, we will see that x will be 3000 divided by 746. So we can use our calculator to evaluate that we have 3000 divided by 746. So what's this? This is 4.02. So this is nothing but 4.02 horsepower as the time rate of energy of this particular system. All right. So here in this question on Hooke's law, we are told that an elastic material of length 3 meters is to be stretched to produce an extension 3 times its original length. We are to calculate the force required to produce the extension if the force constant of the material is 982.3 Newton per meter. So what we have is just something like this. Let's say we have a material like this. Okay, we are told that it is 3 meters, but now we're told that a force will be applied on this particular material, a force F, and this material is stretchy, okay, so it can stretch. With the application of this force, we are told that the new length of the material has now been extended, and the extension is 3 times its original length. This is where students, you shouldn't make mistake. Initially, let's just look at this particular place, that this is its initial length, 3 meters, but now the extension that was produced from here to here as a reason of this force that is applied, if you call it E, we are told from the question that that extension is 3 times its original length. 3, if L naught is the original length, it is 3 times the original length. So that extension is 3 times 3 meters, and that is 9 meters. So we need the value of that extension. But by reason of the formula from Hooke's law, the force that produces an extension is in the material is given as a product of the force constant multiplied by the extension. Okay, and in this particular case, if you want to put in the values, that force that we are asked to find will be the force constant 982.3 Newton per meter. Okay, then multiplied by the extension. What's the extension now? It's not the 3 meters that we are given originally. It is 3 times its initial length. So that is 9 meters as we have calculated there. So it is times 9 meters. Now I want you to look at something. Look at this value. This value is per meter and this is meter. Outrightly, those two units will cancel out when they are multiplying each other. If you remember your law of indices, you have m raised to power minus 1 multiplied by m raised to power 1. So of course this will be just a single m, and you have minus 1 plus 1, which is m raised to the power 0, and any number raised to the power 0, it's 1. Okay, so that means that the formula you are even using is in line with what you are expected to do. So what we are going to have is 982.3 newtons multiplied by 9. And to evaluate this, you can just bring in a calculator. You say we want to evaluate 982.3 multiplied by 9, and that is what in decimal place 8,840.7. so this is 8,840.7 newtons. And students, I just want to emphasize this for you. Once you don't put your unit, you are going to lose some marks. So always remember to put your unit whenever you are working in any science related subject, in short, in any subject, even if it is maths. Okay, so the force that is going to produce the extension is going to be 8,840.7 newtons. In this question, we are being asked that in a solar panel for each supply, we are to state the function of each of the following parts, and we have the metal flat plate, the thermal insulator, and the tubes that can be found in a solar panel for each supply. So we need to have a look at what this is actually looking at before we can be able to define what this particular part can be used for, and it is as shown on this diagram here. In this diagram, we can see the metal flat plate on top of the roof of the house, and what it does is that it collects the rays of light coming from the sun and it absorbs the heat, okay, which is actually the energy that is trapped to ensure there is a circulation in that particular water system. Okay, so that is the function of the metal flat plate. For the thermal insulator will normally be inserted between the metal flat plate that is collecting the heat and absorbing that heat energy and the roofing material. You know, normally the roofing material and the metal flat plate, if they are coming in contact together, there will be heat exchange by conduction, but we want to reduce that. So this thermal insulator here, this particular region that I'm shading in red, okay, those ones are actually going to act as the insulator to minimize heat loss between the metal flat plate and the roofing of the house system where this system will be installed. Now the tubes are going to be conveying the heat that are absorbed, and like in this case, it's going to take it to the water container, which we actually have like an heating element. So the tube will actually trap the heat energy and bring it to the particular container where it's going to generate heat to boil the hot water. And of course, as that tube is conveying that, there is another pipe that is taking, you can see there is a pumping machine here, is actually pumping the cold water up such that the heat energy that is captured can heat up that cold water and they pass it out. In this particular case, blue is the one taking the water to the system on the roof, and red are the set of tubes that are actually bringing the water back. So this is the overview of the system, and that is how it works. So we've been able to identify what these three, what they work for, and we can just summarize that as shown here, that in the first case, the metal plate receives and absorbs solar radiation to produce heat, and then the thermal insulator minimizes heat loss as a reason of the interaction between the metal flat plate and the roofing material. And then finally in C, the tubes help to circulate the heat. You can see it's the one bringing the heat into the container where the water will be boiled and then it will be circulated back. And so this is actually the answer to this particular question. In this question on optics, we are told that in a design of an optical fiber, what type of material is most suitable for design of the core? And then we have to state one condition that is necessary to confine signals to the core of an optical fiber. Let's look at a pictorial view of what we are going to be talking about here. So this is actually like a cross-section area of the optical fiber, and this is regarded as a core, and the sheet is regarded as a cladding. Okay, that's a protective sheet that is covering the core, and the material that is mostly used for the core is actually glass, also time of plastic material, but mostly it is glass. Okay, because the rays of light that are actually coming into the core of the material needs to be restricted to the inside of the optical fiber itself. We don't want a case in which, like if you have rays of light coming into the material, say like this, you don't want it to diffuse into the cladding of the material. Okay, you want it in such a way that these rays of light will be highly maintained inside that particular cladding. So if this ray of light is coming like this and is bouncing off the edge of the core, you want it to still remain within the core and not diffusing into the cladding. And for that, then the refractive index of the glass should be higher than the refractive index of the cladding. Okay, so this angle that is coming in and this outer angle should not exceed the critical angle, such that we will now have light rays diffusing into the cladding. So the condition to confine signals to the core of the optical fiber is that the refractive index of the glass should be greater than that of the cladding. Now we can just summarize as shown here that in the first case is glass or plastics that are most suitable material for the design of the core of an optical fiber, and then in the second case, to confine signal to the core of the optical fiber, the refractive index of the core must be greater than the refractive index of the cladding. This will allow us to actually restrict the signals inside the core. It will not diffuse into the cladding, and with that, the data transmission can be done for long distances because the signal strength will not be lost. Okay, so that is the principle of the operation of optical fiber. In this question, we are told that the velocity v of a wave in a stretched string depends on the tension T, which is in the spring, and the mass per unit length mu of the spring. So we are to obtain an expression for the velocity in terms of the tension and the mass per unit length. But this is the caveat. Look at this. We have to use the method of dimension. So how do we go about solving questions like this? Using the method of dimensions. Now we are going to be looking at that holistically in this question. Just you stay tuned. So we have, let's say we have a particular string attached to, let's say, maybe some wall, okay, and then we're told that for this particular string, if this is a string, the velocity of a wave that will be experienced in that particular spring is going to depend on the tension T. So let's say there's a force that's being applied, which is the tension in the spring. Then the spring itself has some mass, okay, and it also has some length. It has some length L, okay. Now we're being told to obtain an expression for the velocity in terms of T and mu, and we're to use the method of dimensions. The method of dimensions means that we need to go back to the base unit of the SI unit, in which we are going to be having the mass, which is denoted as m, okay, the length, which is denoted as L, and the time, which is denoted as T, okay. So this we are going to be making use of to actually solve this question. But look at the question originally. What are we given? We are told that the velocity depends on the tension and the mass per unit length. So if you want to write that just like we do in normal mathematics, that we write variation, we can say V is proportional to the tension, let's say raised to some power. I'm coming to that, and then the mass per unit length also raised to some power. Now we are putting this as raised to some power because we don't know what the constant of proportionality will bring. So if we are actually to do that, we can now say V is equal to K multiplied by the tension raised to power A multiplied by the mass per unit length raised to power B. Now our mandate in trying to solve this is to find the value of A and B in such a way that the constant of proportionality will have taken care of it, and we'll be able to find the expression for this velocity by using this method of dimensions. Now we have some quantities that we are given in this particular equation. You can see we have velocity, we have tension, we have the mass per unit length. So we need to go down and drill on how we can actually make use of the method of dimension to break velocity, tension, and mass per unit length to their base units. Okay, so ideally we know that velocity is displacement over time, and displacement over time we can just refer to as displacement is measured in length, so we have that is L. Time is measured in T, so we have that is T. So if you want to put that in the dimension, we have L, then T raised to power minus 1. We are putting T raised to power minus 1 because we are expressing this just in a linear form in its indices, and when you have division in indices, it is the same as raised to power minus 1. Okay, then we have tension. Tension, by reason of its formula, is force per unit area. So we have force over area. Now this is where it gets interesting. We need to also further break this down to its base unit. So force itself, we know it is mass times acceleration, okay? So we still have the area as the base, but acceleration we also know to be velocity over time. So we have m over a initially, okay? But acceleration we know it to be what? The velocity over the time. But yet we have not got to the base dimension, because even velocity we just got here to be LT minus 1. So we can further break this down to say we want to put the dimension, since we already have v initially, like in this place it is L over T. So we have mass, that is m. Area is length times length, that's why we have the unit as meter square. So that is L raised to power 2, okay? V itself is L over T. We have L over T, but we also have this other T. So that T will become 2. We have T raised to power 2. And then this L and this L can cut such that what we have eventually is, here we have one L remaining. So we have m over L T raised to power 2. And that will be linearly m L raised to power minus 1 T raised to power minus 2. Again, the law of indices is coming into place here, such that those in the denominator, they will carry negative power. And T that is raised to power 2 will become T raised to power minus 2. So now we can also use the same method to find the dimension of the mass per unit length. By that definition, it is mass over length. Okay, so once it is mass over length, mass is m, length is L. So linearly, this is m L minus 1. Now we have these three that we can actually use here. And we have K is constant, but the one that introduced that, okay? So we can say, instead of writing all of this equation now, we can put in the dimensional unit of each of these quantities. Like for velocity, we have it to be LT raised to power minus 1 is equal to K. Then T itself, the dimension is m L minus 1, T minus 2. But we have it raised to power A, okay? And then the mu we have is m L minus 1, also raised to power B. So this is what we work with to actually equate the left hand side and the right hand side to find the value of A and B, such that we will evaluate the expression for the velocity in this particular question. So I'm going to clear this right hand side, but this is how we actually go to the base of those units, and then we'll solve that as appropriate. So if you want to continue working on that, on the left hand side we can see that we don't have m at all. And what is the implication of that? From our rules of indices, we know that any number raised to power 0 is 1. So on the left hand side, the power of m is 0, okay? That is why it's not reflecting here at all. So we have L, then T raised to power minus 1 is equal to K. We will try to open this bracket. Since A is acting on the whole of this entity, it will be that we have m raised to power A. L raised to power minus 1 times A will be minus A. T raised to power minus 2 times A will be minus 2A, okay? And the same we also do here for the mass per unit length of the spring. M raised to power B will be m raised to power B. And then L minus 1 raised to power B will be L minus B, because we multiply this particular power with this outer power. It's also part of the laws of indices. So as physics students, you should actually have a very good grasp of the understanding of mathematics. So here now, again, we are going to use indices because we are having m and m. And from the law of indices, what we know is that we have m raised to power A multiplied by m raised to power B. We can say this is a single m, and we add the power. So that is what we are going to employ now to try and open up this bracket and equate the left hand side and the right hand side, okay? So we can say here it will be m raised to power 0 L T minus 1 is equal to K. M here we have A and we have B, so we can have a single m raised to power A plus B, okay? L we have minus A and minus B, so if you add the two, it will be minus A minus B. Then T is just a singular entity raised to power minus 2A. Now looking at this and comparing the left hand side and the right hand side, we can conclude that from here, since the bases are equal, then the powers, they will also be equal, so that we can have A plus B is equal to 0 as a function of the power on m, okay? And then as a function of the power on L, we can say that L is just 1 here, but L is minus A minus B here, so we can have minus A minus B is equal to 1, okay? And then for T, we can have minus 2A is equal to minus 1. So we have these three that we can actually attempt to solve by whatever means is appropriate to us so that we can get this. But looking at this third entry, I can say I want to divide by minus 2 so that this minus 2 will cut and this negative sign will also cut, and I will find A to be 1 over 2. Okay, that is interesting. If A is 1 over 2, from here B is equal to minus A, and therefore B will be minus 1 over 2. All right, okay. I think that is getting quite interesting. So if I want to go back to this equation that we coined out of the expression that was given in the question, I can say that means the velocity is equal to K multiplied by the tension. Now, what's the power of the tension? It is 1 over 2 multiplied by the mass per unit length, having a power of minus 1 over 2. Again, wow, you see, our understanding of maths needs to be very, very sharp. If we have this, that means what we're having is that V is K multiplied by T. This negative sign on mu will mean that it is over mu and then raised to power 1 over 2. You can leave it as this, but even I know that 1 over 2 as a power means it is the square root. So I can just outrightly express the solution like this. I want to erase this. With my understanding of indices, I can now say that this means that V is equal to K multiplied by the square root of T over mu. Now, this negative is what affected mu to actually come to the denominator, and this power of 1 over 2 common to both is what is bringing in the square root. And just like this, we've been able to find an expression for the velocity in terms of the tension T and the mass per unit length mu as given for this question. The good thing about this type of questions is that you don't just get to know them by watching videos like this. You practice, and the more you practice, the better you are going to become. All right. In this question, we are told that a satellite launched with velocity VE just escapes the Earth's gravitational attraction. Now, given that the radius of the Earth is r, we are to show that that escape velocity is equal to the square root of 20 multiplied by the radius of the Earth, given that the acceleration due to gravity g is 10 meters per second square. So, if you want to have a pictorial view of what we are talking about, it is just as shown here. And from the question already, you can look at the radius of the Earth from the center of the Earth to the point where the satellite is escaping the Earth's gravitational pull, and we can take that as radius r. Okay, now we are told that there is an escape velocity with which the satellite just escapes the Earth's gravitational attraction. There are basically two ways we can go about to evaluate the formula for the escape velocity. We can use the gravitational force, but here I want to use the conservation of energy. That originally we know that the kinetic energy with which the satellite is launched is going to be equal to the potential energy at the height where the satellite had already reached to escape the Earth's gravitational attraction. Okay, so you can actually attempt that other method by making use of the gravitational force. Okay, but here this is what I want to use. And what do we notice? Now, there is an escape velocity VE in which this satellite of mass m is actually going at. Already we have the radius I, but the height that the satellite is escaping with will actually be the radius of the Earth to the point where it escaped from the attraction pull of the Earth. Okay, so if you want to just put in the formula for this particular equation, the kinetic energy is half multiplied by mv square. Okay, the potential energy is the mass multiplied by the acceleration due to gravity multiplied by the height, but now that height is the radius of the Earth that we are looking at. So with all of this that we have, we can just say that this mass is going to cancel this mass, okay, so that v square over 2 is equal to acceleration due to gravity multiplied by r. And if we cross multiply, we can see that v square is going to give us 2 multiplied by the acceleration due to gravity g multiplied by the radius of the Earth. G already we have been given as 10 meters per second, so if you multiply that, that will be 20r, such that this is what we are asked to find, such that we can see v is equal to the square root of 20r. So this is a very, very simple means by which you can just evaluate this and we'll get our full marks. But if you want to make use of the gravitational equation, you can also use that, and you will also see that you are going to arrive at the same answer. All right. In this question, we are told that a bullet is fired from a gun at 30 degrees to the horizontal. The bullet remains in flight for 25 seconds before touching the ground. We have to calculate the velocity of projection, given that acceleration due to gravity g is 10 meters per second squared. So we can look at a pictorial view of what we have as a case scenario here, and I just want to give some little explanation so that students will be able to just do this on the fly. We are going to be making use of the equation of motion v is equal to u plus at. But now, looking at this particular diagram, there are a number of things that we can notice. Okay, now this can be taken as the maximum height, h maximum. Then from here to here, so from here to here, that is the distance covered. The bullet in this case generally referred to as a projectile, so that is the range. But there's something we need to note. In this particular case, the bullet is being fired at an angle to the horizontal. It's going to have two components. The initial velocity, we have a vertical component, okay, vy. It will also have an horizontal component, vx. Okay, so these are the things that we can actually make use of to tweak the general equation of motion that we know, so that we can see how we apply it in this particular case of the projectile. So I want to just start by looking at the maximum height. At that maximum height, we are noticing that the final velocity v will be 0 at the maximum height. The initial velocity, because it's not a component along the horizontal, it will only be a component along the vertical. So that initial velocity, that will now be v sine the angle that we are given, which in this case is 30. Okay, this 30, but it is the vertical component, which is vy, that is v sine 30. Now for the acceleration due to gravity, because the bullet is fired and moving in a direction opposing the pull of acceleration due to gravity, this will be minus g. Okay, and t is the time taken to reach the maximum height. Okay, this is the time. So if you just look at this, we will see that what we have is 0 is equal to v sine theta minus gt. Okay, so that if you rearrange, we will see that the time taken to reach the maximum height is going to be v sine theta over g. We should be able to do this since we are science students. This is actually a very simple thing. But now the total time taken for this particular projectile motion will be 2 times this particular set of time that we are having, so that we can derive the equation that t is equal to 2v sine theta over g. And this is actually how they derive the formula for the total time of flight for this particular equation. Now look at the information that we have. We have the angle theta to be 30. Okay, we are looking for the velocity of projection, which is v. Okay, we have the acceleration due to gravity, which is g, given as 10 meters per second, and we have the time t as 25 seconds. So we can easily use this formula. This is very good for us to actually solve this particular question, and that is what we are going to do right now. So we have the formula that we derive to be the total time of flight to be 2v sine theta over g. Now from the question, we have been given t to be 25 seconds. Okay, we have been given theta to be 30 degrees, and we have g that was given to be 10 meters per second square. So we can put all of this into this equation to say, therefore we are going to have t is 25 is equal to 2v, v is what we are looking for, sine 30 divided by 10. So we can have 2 here, 1, 2 here is 5. When we cross multiply, we are just going to have this to be v sine 30 is equal to 25 times 5, that is 125. So you can divide both sides by sine 30. So over sine 30. Sine 30 itself is 0.5. So here you can see that we are just going to have this cutting out. Okay, and then we have our v to be 125 divided by 0.5. Okay, we are multiplying 125 by 2, so this is 250 meters per second. So that is the velocity with which the bullet is fired from the gun inclined at 30 degrees to the horizontal. And with this, you've been able to actually get your question correctly. The trick is to resolve the velocity to the vertical component and the horizontal component, and you just put that in the equation of motion and you get your answer out. All right. In this question, we're asked to state 3 properties of lasers that make them preferable to using ordinary light beam. So there are some special occasions in which people will prefer to use lasers instead of just using any ordinary light beam, and a pictorial view will show us some of those properties now. Now, lasers are the kind of the light that snipers and the soldiers they use, they mount on their rifles, on their guns, automatic guns or whatever it may be, so that they can actually trace the target that they want to focus on. And you can see if that's what they are trying to use, they cannot be using the normal light like the one coming from your torchlight that will give wide range of light emanating and expanding as it leaves the light source, just as being shown in this particular case. For those particular lasers, they need it to focus on a single entity, so it should be monochromatic. If it is a visible laser light, it should just be monochromatic. You don't want it to diffuse and go up and down like this. It should just be monochromatic. It should also be coherent. These are differences between it and the normal light, which is non-coherent. Then it should be directional. It should just have a single point of focus where it's directed to, and it will aim at that. And because it has high intensity, you can actually be focused. It's not going to lose its power. Unlike the ordinary light beam, if you put on the torchlight, you will notice that from the source of the torch, it will be very bright, very light. But if you go to a far distance and you want to see something very far, that will not be feasible in the case of a normal light. So these are some of the properties that makes lasers more preferable. If you want to put it down, you can say it travels very long distance without losing its intensity, and it gives more intense power. It has narrow optical bandwidth. It can be emitted continuously, and it is monochromatic. Stating any 3 of these, you are going to get your full marks as requested. Here in this question, we are told to define a torque and to state 3 factors that determine a torque. So if you want to look at that solution, like I normally advocate, a picture is worth 1,000 words. And here you can see a picture that we are looking at, and we can see in this picture here, this is a spanner. Okay, so imagine you are making use of a spanner to actually turn a particular bolt, just as being shown here. Now, for you to do that, you bring in a spanner into the bolt, but just putting the spanner on the bolt is not going to affect anything. You need to apply a force F, that is as shown here, and that force that you are going to apply, you will see that it's going to run perpendicular. These are very key important concepts when we are talking about torque or moment about a pivot, moment about an axis. So it's the application of the force in this particular direction that will ensure that the bolt is either being loosened up or being tightened, as the case may be. Okay, so if you want to define a torque, it's just as shown here, that the torque is the turning effect of a force about a pivot or an axis. And looking at this example that we have here, you can see now the force that is being applied is this particular F. Okay, the pivot or the axis where it's being applied is also shown here, and we have some distance, okay, between that point of application of force and the axis that we are looking at. That is the distance R, and the force that is being applied is force F. So the factors that determining a torque include the magnitude of the applied force F here, so how big a force or how small a force is being applied, and then the direction of the applied force. Here you can see that this particular direction is a clockwise motion. Okay, so it's moving just like the same way your wall clock will be moving. Okay, so it is a clockwise movement. And then the perpendicular distance of the force from the pivot, you can see this is a force, and this distance denoted as R from the point of application of the force here to the axis, which is the location of the bolt. This particular length is the perpendicular distance of the force from the pivot. Notice something, it is the perpendicular distance. Okay, so it's not as if the force should be in this particular direction. If that is the case, then this is just a linear force. It's not a torque. Or if you're having it being applied in the opposite direction here, that is also not a torque. That's just a linear force. In this particular case, it needs to be applied perpendicular to the pivot on which it is being applied. Okay, so that is just all there is to answer this question on torque. In this question, we're asked to define free fall. And to define free fall, just imagine the popular story about the scientist that was looking at an apple fall down from the tree, and because of that he got to deduce the gravitational law. So free fall is the vertical motion of a body under the influence of gravitational force or its own weight. So that's why there's that popular proverb in Yoruba language that any object that goes up will definitely come down. Okay, so here you can see even apple that is falling from the tree will definitely come down. Why? Is as a reason of the influence of the gravitational force and even his own weight in which is being exerted and pulled towards the center of the earth. So that is the definition of free fall. So in this second question, we're told that a body is thrown vertically upwards from the top of a tower 40 meters high with a velocity of 10 meters per second. We have to calculate the time taken for the body to reach the ground. Now, I want to bring in a pictorial view for us to really understand what is happening with respect to this body that's being thrown vertically upwards from the top of a tower, which is 40 meters high. So let's take this as the 40 meters tower. So the body, which is denoted in red here, is being thrown vertically upwards. So we have two sets of motion that the body is going to undergo. First, the upward motion, and then the downward pull as a reason of gravitational force. So in the upward moment, the initial velocity was given to be 10 meters per second. So that was the velocity with which the body was thrown upwards. Then at the point that it got to its maximum height, the velocity at that particular point is going to be 0. So if the initial velocity is 10 meters per second, at the maximum height, the final velocity is going to be 0, because at that point it's not moving upward again, but it will momentarily come to a rest before it now starts to come down. Then for that downward motion, that initial velocity is now 0, and then it will have a final velocity, but it is coming down as a result of the gravitational force that is pulling it downwards. So in the initial case, when it's being thrown upwards from the 40-meter tower, it will also travel an additional distance d upwards, so that when it's coming down, the total distance it needs to traverse will be the height of the tower, which is 40 meters, plus the distance that it has traversed from the top of the tower where it was being thrown. So that is why we have 40 plus d. Now, the mandate for us is to calculate the time taken for the body to reach the ground. That time will be first the time it took to reach the maximum height, and then the time it used to come down to the ground level from that maximum height. So let's look at how we can get those two times. We have the time going up and the time coming down. Using the equations of motion, here we have the initial velocity as 10 meters per second and the final velocity as 0 meters per second. We don't know the distance, but we are concerned about the time. So if we are to look at the equation, v is equal to u plus at. Okay, now we know that our v for the upward motion, in the upward motion, okay, the v is 0 meters per second. The u is what? Is 10 meters per second. And then we can use the a, which is the acceleration due to gravity, that is going to be pulling the body down so that it will be reducing its velocity as it's traveling up. So that is opposing the direction of motion. So it's going to be negative. So minus 10 meters per second square. And then t we can find as a t in moving up. So if we substitute all of this into this equation, we are going to have that we have, let me use ink, we have 0 is equal to 10 minus 10t, okay, such that t here will be 10 over 10, and that is equal to 1 second. So the time for it to go up to reach its maximum height is 1 second. Now for the downward motion, let's see what we can use. Here we have the initial velocity to be 0 meters per second. We are not actually concerned about the final velocity. We have the acceleration due to gravity acting on the body, and we have the distance to be 40 plus d. Okay, so if you want to say we want to make use of s is equal to ut plus half at square, since we are looking for t, the u is 0, so this can easily knock out, but we need to find the s. The s is going to be 40 plus d, but we need to get the value of d. So if you want to take that value of d, we can say initially from the upward motion, from v square is equal to u square plus 2as for the up. Here we can see that our v is 0 is equal to the u square, that is 10 raised to power 2 plus, now since it is going in the negative direction, it has to be minus 2 times 10 multiplied by s. Our s in this particular case now is d. That is for the upward motion. Okay, so from here, if we are to solve, we can see that 20D is going to be 100, because if we move this to the left hand side, to be 20D is equal to 10 raised to power 2 is 100, so that D is equal to 100 over 20, and that is going to be 5 meters. Okay, so for this particular S, we can say we have our S here to be 40 plus D will be 40 plus 5, and that is 45 meters. Okay, already A is the acceleration due to gravity that is acting on the body, and T is what we are looking for. So we can just employ that to say, therefore, S, which is 45, is equal to half multiplied by G, which is 10, then multiplied by T raised to power 2. 2 can go here 1, 2 in 10 is 5, so that we can have T square is equal to, here we're going to have it as 45 over 5, that is 9. Then T in coming down is equal to the square root of 9, and that is 3 seconds. But what we're asked to find is the total time it's going to take for the body to reach the ground. That total time, T total, is going to be the time it took to go up, which is 1 second, plus the time it took to reach the ground, which is 3, and that will be nothing plus 4 seconds. So this is the total time it will take for the body to reach the ground as appropriate. In this beautiful question, we're told that a cube of wood of side 8 centimeters floats at the interface between oil and water with 2 centimeters of its lower surface below the interface as shown in the diagram below. So here's the diagram. This is the wood in black, and here is water. It is 2 centimeters submerged in water, while 6 centimeters of it is in the oil. But we need to remember that it is a cube. Okay, now given that the relative densities of oil and water are 0.72 and 1.00 respectively, we are to calculate the mass of the wood. Now I want to reiterate this. We are told that it is a cube of wood that we are looking at. So this diagram is actually not 2-dimensional, it is 3-dimensional, just as I'm going to show now. So this is the true picture of what this diagram should originally look like. It is a 3-dimensional thing, in which here for the cube of wood, this is 8 centimeters, okay, and this particular base is also 8 centimeters. But I want us to note something. We are told that it has 2 centimeters of its lower surface below the interface. So here, from here to here, this is what, 2 centimeters, just as is being denoted here. While the other one that is not shaded, this will be 6 centimeters. Okay, so the 2 centimeter is the one in water, so that's why I just differentiated with this yellow light color. So this 2 centimeters is on water, and the one that is not shaded at all is in oil. So we need to get that, because not getting that, we're going to miss this question outrightly. So the mandate is that we are to get the mass of the wood. Originally, we know that density is mass over volume, such that the mass, in this particular case, the mass of the wood will be the density multiplied by the volume. Okay, and now we are told that the relative densities of oil is 0.72 and that of water is 1. That's why we are saying respectively. But now for the mass of the wood, we need to consider the upthrust in water and the upthrust in oil. But again, look at the unit we are giving. We are giving all our units in centimeters. We need to convert them to meters before we'll be able to work with the volume of the wood, so that we can get the mass of the wood. So we just want to do that. We can say for 8 centimeters, that will be 8 over 100 meters, and that will be 0.08 meters. Then for the other ones, we have 2 centimeters will also be 0.02 meters, and 6 centimeters will be 0.06 meters. So having this will help us to use the right unit in calculating the volume and eventually getting the mass for this particular cube of wood. But this is what I want us to get. The mass of the wood is going to be the density of the wood multiplied by the volume of the wood. But because we're having 2 case scenarios here, that will be the density in water multiplied by the volume in water plus the density in oil multiplied by the volume in oil. So this is the 2 case scenarios that will generate the total mass of the wood for us in this particular situation. So if you want to just calculate that, we can say the mass of the wood is now going to give us, now the density in water, we have been told that it is relatively 1, so we have 1 multiplied by the volume in water. So what is the volume in water? Here we have 8 centimeters by 8 centimeters by 2 centimeters. That is the region that is submerged in water. But we cannot use centimeters because we need to use the standard SI unit. So we need to use meters. That will be 0.08 meters times 0.08 meters multiplied by 0.02. So we have 0.08 times 0.08 multiplied by 0.02. Okay, then plus the density and multiplied by the volume in oil. The relative density in oil we have been given to be 0.72, so we have 0.72, okay, times the volume in oil we now need to be 8 centimeters by 8 centimeters by 6 centimeters. But again, we are working with the SI unit, so we need to convert them to meters. That would be 0.08 times 0.08 times 0.06. So this is the correct way to go about trying to solve this. So if you want to just use a calculator to evaluate this, so we have in the first case 1 times 0.08 times 0.08 times, for the one in water it is times 0.02. okay, so that's what that is 1.28 exponent minus 4, 1.28 times 10 raised to the power minus 4 plus the mass in oil, that will be 0.72 times 0.08 times 0.08 times 0.06. so what's that? That is 2.7648 exponent minus 4, 2.7648 exponent minus 4, and if we add the two together, 1.28 exponent minus 4 plus the answer that we just got. Okay, so that is going to be 4.0448 times 10 raised to the power minus 4 kilogram. All right, so this is going to be the mass of the wood as we are expected to calculate, and we're able to get this because we understand that first we are working in a three-dimensional space because of the information that we are given that it is a cube. It is a cube of wood that we are working with. Then we're able to actually use the formula that mass will be density times volume, and then our volume we are calculating in the standard SI unit of meters and not centimeters. And doing that, we're able to evaluate the mass of the wood as appropriate. In this question, we're asked to explain resonance frequency as applied in RLC series circuit. So let's look at our diagram of how RLC series circuit look like. So this is a typical scenario of an RLC series circuit, and that is meaning that it has a resistor, okay, and then a capacitor and an inductor. Now across the circuit, we are going to be having a voltage operating at a certain frequency which is being used to generate a current, and that current will be the ratio of the voltage to the total impedance in the circuit. In a normal simple circuit, we use the voltage over the resistance, but here we need to factor in the capacitor and the inductor so that we have what we call an impedance. The impedance, which is here, will now be the combination of the resistance and the inductive reactance and the capacitive reactance, just as is shown in this particular equation. Furthermore, we can get the capacitive reactance of the circuit as 1 over WC, where C is the capacitance of the capacitor, okay, and then we can get the inductive reactance as WL, where L is the inductance of the circuit, and then W itself we can get as 2 pi the frequency of generation of the voltage across the circuit. So this is a typical scenario of a RLC circuit, but now we are talking about resonant frequency. What happens in resonant frequency? What happens in that particular case is that the inductive reactance and the capacitive reactance, they are equal, such that the impedance is now going to only be the value of the resistance across the circuit, because from here you can see Z will now be the square root of R square, and that will be just R. So that is the case in which you have the resonant frequency in an RLC circuit. So what that means is that, number one, the inductive reactance and the capacitive reactance, they are equal, okay? So they are not going to have any effect on the circuit. And then the total impedance Z will be the resistance of that particular circuit. That's also going to affect the phase, the angle, because here, since SL and SC, they are equal, so you have it to be arctan 0 over R, and arctan 0 over R is arctan 0, which means that the phase, the angle between the resistance and the impedance is going to be 0. So like we said there, the Z will not be equal to R because this angle would have been nullified, okay? So that is the scenario of the resonant frequency as applied in RLC series circuit, and we can just define it like this, that the resonant frequency is the frequency of oscillation when the capacitive reactance, this capacitive reactance, is equal to the inductive reactance, this, okay? And at such occurrence, the impedance, which is Z, is equal to the resistance, such that the current is maximum while the impedance is minimum. So the impedance will be minimum, and here this impedance will be minimum, and the current definitely will have its highest value. So that's the explanation of resonant frequency as applied in RLC series circuits. Continuing with that question, we're told to sketch a diagram to illustrate the variation of frequency F with the resistance R, the capacitive reactance ZE, and the inductive reactance ZV in RLC series circuit. And then we have to use the diagram that we draw to state whether the current in the circuit leads, lags, or is in phase with the supply voltage when the frequency is equal to the resonant frequency, the frequency is less than the resonant frequency, and then the frequency is greater than the resonant frequency. You can see we're told F0 is the resonant frequency. So first, looking at the diagram is going to look just like this, and I want to just explain this particular concept. If you recollect from your understanding of mathematics, when you have an inverse function like here, the capacitive reactance is 1 over 2 pi Fc. Because of this C, 2 pi left, 2 pi left, you can see that those are constants in both the capacitive reactance and the inductive reactance. But because the capacitance is an inverse function, that's why this curve is looking like this curve, okay? And it is at its highest when you are starting out, and then to gradually reduce just as shown. But for the inductive reactance, look at this, it's just a linear equation. So it's going to be a straight line graph passing through the origin. You can see, like when you are saying y is equal to ms plus c, the c here is actually not existent. So that means the intercept is 0. It is passing through the origin. So your understanding of mathematics can really help you, but I'll still further explain some things that you need to note. Now, the resistance is going to be a constant. It's not changing in value because we are not using a rheostat. It's just a resistance. Now, we are having the graph of the reactance against the frequency. But if you notice on this left-hand side, this is the resonant frequency where the value of the inductive reactance and the capacitive reactance, they will knock out each other, okay, here at this particular place. So at that point, it's only the R that will be the value in consideration. But on this left hand side, you can notice something. For this particular green, you can see that here the capacitive reactance in red is greater than the inductive reactance on the left hand side, whereas on the right hand side the inductive reactance XL is greater than the capacitive reactance. So this will help us to actually answer the second question. So if you have your graph like this, I want to look at the second question. I will just want to show you some things there, just as it is here. You can see now this is actually the explanation. If I want to denote correctly of this question, this is the answer to A2. This is A2 here, and here this is A3. But if you recollect, we are saying that the phase, the angular phase, is equal to arctan the difference in XL and XC over the R. Okay, that is actually the value for the phase. Now look at this. In this particular left region to the resonant frequency, I told us that the XC is greater than the XL. So in this particular case, that means for F less than F0, you are going to have the angle to be arctan a negative number, because here, since XC is greater than XL, then it will be a negative number. And if you take your calculator, just look at this. After, let's say, just minus 1, for example, that's going to be minus 45. That means that angle is also negative. The angle is negative means that it is lagging. So when f is less than f naught, you can see like here in beta, when f is less than f naught, then the current is going to lag the supply voltage. And interestingly, when, like the gamma question, when f is greater than f naught, what you will notice is that for that particular case, let me just show you here. When f is greater than f naught, then your tan is going to be arctan positive, because in that case XL will be greater than XC. Is going to be this particular side. It is f naught, f here greater than the resonant frequency. Then for that particular region, XL is greater than XC. So this particular expression in brackets is going to be positive. Then your theta is positive, meaning that current is going to lead the supply voltage. But in the first case, the alpha case, when your f is equal to the resonant frequency, then current is in phase with voltage, because the inductive reactance and the capacitive reactance are going to knock out each other, so that we only have the resistance. And like I explained before, in that particular case, I will just be V over R, and that will just be in phase. So this is the correct solution to this particular question. You will do well to note the application of your mathematical reasoning, so that you can apply in questions like this in subsequent times. All right. In this question, we're asked to define mutual inductance. So this is the pictorial view of what we have whenever we are going to have mutual inductance. And what is happening is that as a reason of the current that is changing in this particular coil, this first coil, we are going to have a magnetic field being induced. This magnetic field being induced in the second coil in such a way that is going to produce an induced EMF that will be observed in the coil. So if you want to define, we can just say mutual inductance is the ratio of the induced EMF in one coil or circuit here to the time rate of change of current that is producing it. Or we can say it is a production of EMF in a circuit, in this circuit, as a result of the change in the magnetic flux or the circuit in an adjacent circuit linked to it, as shown in this particular picture. So EMF is being induced in this coil 2 as a result of the changing current in this coil 1, and that is mutual inductance. In this question, we are told that the coil of an electric generator has 500 turns and 8 centimeters diameter. If it rotates in a magnetic field of intensity 0.25 Tesla, we are to calculate the angular speed when its peak voltage is 480 volts. Then pi will be given to be 3.142. So let's list the parameters that were given in this particular question. Starting from n was given to be 500. All right, we have the diameter is 8 centimeters, but we need to use the standard unit, so that should be 8 over 100 meters, and 8 over 100 meters is 0.08 meters, but that is the diameter. Okay, what we need is actually the area of that particular coil, and since it is a circular coil, the area is pi r square, so that will be the pi we have been given as 3.142. okay, then the radius will be half of the diameter, so we have 0.08 over 2 raised to power 2 over 2, because radius is half of diameter. That's why I have 0.08 over 2. So we can evaluate this. Let me just use my calculator. Say 3.142 times 0.04 raised to power 2, because 0.08 over 2 is 0.04. So that is 5.0272 exponent minus 3, 5.0272 times 10 raised to power minus 3 meters square. That is the area. Okay, then what else are we giving? We are giving the magnetic field strength. B was given to be 0.25 Tesla, and then we are giving the voltage to be 480 volts. What we are asked to find is the angular speed, W. W is what we have to find. So the question is, what formula is relating the number of turns, the area, the magnetic field intensity, and the voltage in an electric generator? The formula is that the EMF is equal to the area multiplied by the number of turns multiplied by the magnetic intensity multiplied by the angular velocity, such that that angular velocity we are looking for will be the voltage divided by the area multiplied by the number of turns multiplied by B. And if you are to substitute all the values that we have, we will see that our W will be, what is the voltage? That is 480, okay, divided by the area we just got to be 5.0272 exponent minus 3, okay, multiplied by the number of turns, that's 500, multiplied by the magnetic field intensity 0.25. So this is what we need to input into the calculator, 480 over the initial answer that we got multiplied by 500 multiplied by 0.25. So I can just say this is 480 divided by, I want to put all the denominator in a bracket, okay? So I have the answer that I just got multiplied by 500 multiplied by 0.25. So I can close that bracket and find my answer. So this is 763.845, 763.845, and the unit is radian per second. So this is the value of the angular speed for this particular case scenario of the electric generator that we are looking at. It is this formula that we know that will really help us to solve the question, and without knowing the formula, we will not be able to solve this, okay? In this question, we're asked to explain eddy current and state two practical uses of eddy current. So, eddy current is a current that is induced and flowing within a metal block when there is a change in magnetic flux linking the block. Or we can say it is the loop of electric current that is induced within a conductor by reason of the changing magnetic flux or field in the conductor. If you look at the previous question we are looking at, we are talking about an EMF being induced as a reason of an electric current in another coil. But here, in that case, we are talking about mutual inductance. But here, in eddy current is actually induced as a reason of a change in the magnetic flux that is linking the particular block. And so here is a picture that's showing us a coil that is having some electromagnetic field, and as a result of that electromagnetic field, eddy current is being generated from that coil. The other case, we are looking at mutual inductance, in which we have a particular current flowing in a coil and it's inducing EMF in the other coil. But here we have a coil that is having an electromagnetic field that is generating current in another coil. So this is just the definition, and it can be used in induction furnaces, induction coils, speedometers, and induction motors. Here we are being requested to define the critical angle as used in optics, and then to state two conditions necessary for total internal reflection to occur, and finally we are to list three practical applications of total internal reflection. So let's just look at a typical diagram of what is being requested of us in this particular case, okay? So here, for us to define the critical angle, we need to consider two media in which light rays is traveling from a denser medium to a less dense medium. So the one being shaded in this light blue is the denser medium. That means that in this medium, light rays will not travel as fast as in the other medium. It will be faster in this white region than in this denser medium. Denser meaning that it is more compact. It's more partly packed together such that it will resist the flow of light rays. But even though it's resisting, it means that light ray can still pass through, but it will pass through faster in the other medium. So if you are looking at that, we can look at the incident ray of light coming into that medium, and at the point of meeting the interface between the denser medium and the less dense medium, the light ray is going to be refracted. So in this particular case, what we notice is that the incident ray is at an angle that is less than the critical angle, because if it is getting to the critical angle in this particular second case scenario B, okay, let's call this A, B, and we'll call this C, okay. So if the incident ray, the angle of incidence, is now getting to be equal to the critical angle, then the refracted ray will be at a right angle to the plane, okay, to the plane where we are taking the angle. That's why you have this as theta to be 90 degrees. So at that particular point, we are having the critical angle, that the angle that the incident ray makes with the normal is actually what is tagged the critical angle. And what we notice is that after that critical angle, okay, you can see here is the critical angle, but immediately after that critical angle, we are going to see that light rays will not be refracted into the less dense medium. It will just reflect back into the denser medium. So in the first case, Snell's law of refraction is being obeyed. So in this second case, we are going to have, by the Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. But here, theta 2 is 90 degrees and sine 90 is 1. Okay, so that n1 sine theta 1 is equal to n2. And that is why we now got that sine theta, which is the incident angle, is going to be n2, the refractive index in the less dense medium, over the refractive index in the denser medium. It is from this explanation that we are going to get this particular formula, okay? And then in the last case, if we are looking at a case in which total internal reflection is occurring, means that the reflection is occurring inside the denser medium. You can see we are not having refracted ray go out to the less dense medium. We are not having the critical angle in which it is normal to the plane. Here we are seeing that it is totally reflected internally to the denser medium, and that is the case in which we have the total internal reflection. You can just use this as a guide to understand. If you want to put those in words, we will have it that in the first case, the critical angle is the angle of incidence in the optically denser medium, okay, the more packed medium, for which the angle of refraction in the less dense medium is 90 degrees, okay? And the condition that is necessary for that to take place is that first, light rays must travel from a dense medium to a less dense medium. So we are coming from a medium in which it is difficult for light rays to traverse as compared to the other medium. Then angle of incidence in the dense medium must be greater than the critical angle as explained in the other case. Then this total internal reflection finds practical applications in prism periscopes and binoculars, in fiber optics cable, in which you don't want the light rays to bounce into the cladding of your fiber optic material. You want it to just bounce back inside the fiber optic material so that it can travel for a far distance, okay? We also can find this application in the transmission of radio signals, and then we can also find this application with the view of the fish eye. You can see that normally the fish is operating in a pool of water which is denser medium as compared to the atmospheric outside, which is here, which is less dense medium. So how will the fish be able to actually see correctly the shapes that are outside the water body? It's making use of total internal reflection in its biological modulus operandi, okay? So that is that about this question. We're asked to state two effects of refraction in this particular question, but we need to know what is refraction itself. Refraction is the bending of light as it travels from one transparent medium to another. And by that definition, we can see its effect in mirages, in apparent displacement of objects placed in a liquid medium, and in the dispersion of white light, for example, in the rainbow. A picture is going to convince you. Now, sometimes you get to put, like in this particular case, you get to place objects in water, and you see that originally the object is supposed to be coming straight, but refraction will cause it to actually look as if it is distorted. Okay, it's the same effect by which we actually see rays of light, which is normally white, being dispersed in the rainbow, and of course in mirages, in which we see objects in the wrong position as if the eye is playing a trick on us. All this are actually the effect of refraction. All right, in this question we're asked to define progressive waves, and this is the definition that a progressive wave is a disturbance which travels through a medium that enables energy to be transferred from its source to another source without the transfer of the particles of the medium transfer. So what you need to note is that in progressive waves there is a transfer of energy, even though the particle that is transferring the energy itself is not being transferred. It is stationary, it is maintaining its position, but yet it is transferring energy from one point to another. There is a pictorial view of how a progressive wave generally look. Now there is a general formula for the progressive wave that is defined as y is equal to the amplitude a sine omega t minus 2 pi over lambda multiplied by x. Okay, now if you need to note further, the omega is actually 2 pi f, and f itself is 1 over period. So this is the same as 2 pi over the period. So these are actually general equations that we can know. So instead of writing omega t, you can actually write 2 pi ft, okay? But in the next question, we are going to see how we practically apply this equation of a progressive wave. So here in this question, we are told that a plane progressive wave is represented by the equation y is equal to 0.5 sine 1000 pi T minus 100 pi over 17x, where Y is in millimeters, okay, T is in seconds, X is in meters, and we have to calculate first the frequency of the wave, the wavelength of the wave, and the speed of the wave. So this is what I would like us to do. What we are given is Y is equal to 0.5 sine 1000 pi T minus 100 pi over 17x. Okay, now I want us to compare with the general formula that I just gave the other time, that Y is equal to A sine. Here I was saying that we can write WT, or we can write 2 pi FT, okay, minus 2 pi over lambda x. So these are two equations that we can compare already, okay, and some things are just coming out directly. Like for example, comparing the two equations, we can see that A is equivalent to 0.5, so we can say that the amplitude A is equal to 0.5 by comparison, okay. Then for us to get the frequency of the wave as it's being requested there, you can say the question on alpha. If you are to get the frequency of the wave, if you compare these two entities, this 1000 pi T over 2 pi left T, we will see that 1000 pi T is equal to 2 pi ft, and if that is the case, you can cut out pi, you can also cut out T, such that we have 2f is equal to 1000, and that will render the frequency f to be 1000 over 2, and that will be 500 hertz. Okay, that's the frequency of the wave. Then to get the wavelength, okay, what is the wavelength of the wave? It is lambda, okay, and again by comparing, you can see that this entity, that is the coefficient of x, and this entity, that is the coefficient of x, they are going to be the same. So we can say 100 pi over 17 is equal to 2 pi over lambda. Okay, again we can cut to say pi can cut here, so that if you cross multiply, we can have it that 100 lambda is equal to 2 times 17, so that lambda will be 2 times 17 over 100, and we need to look at that. Okay, so we want to use our calculator. 2 times 17 divided by 100, that is 0.34. so the wavelength is 0.34 meters, okay, because already we are told that s is in meters. Then we have to find the speed of the wave. So what is the formula for the speed of the wave? The speed is given as v is equal to frequency times lambda. So if you have missed the frequency and the lambda, definitely you are going to miss the speed. So here we can just see that our speed is 500 multiplied by 0.34, and if you bring in our calculator again, so our previous answer 0.34 times 500, that's going to give us what? That's 170. So this is going to be 170 meters per second. So with this, with the understanding of the fact that we know the general formula for the equation of a progressive wave, we can compare each of the entities. Like the amplitude is 0.5, 1000 pi T is 2 pi left T, then 100 pi over 17 is 2 pi over lambda, and we can get the frequency, the wavelength, and then we can get the speed to be 170 meters per second. All right. Here we have this beautiful question from WAEC, and it is looking exactly like an alternative to practicals, but it's being featured in a theory paper. So students, you just need to prepare for whatsoever may be coming from your exam paper, and that's why we're taking our time to walk you through this. And you can find a whole lot of other examples by checking our videos and playlists, so that you can best be prepared to gain that academic excellence in the exam. So here we have been told that in an experiment to measure the specific latent heat of vaporization of water, a student places a heater in a beaker containing water. The beaker stands on an electronic balance so that the mass of the beaker and water could be measured. So don't worry, I'm going to show you this pictorially so that you understand what we're talking about. So the heater is switched on and readings were taken every 100 seconds when the water starts boiling. The table below shows the reading. So we have the time in increment of 100 seconds, okay. We have the reading on the balance measured in gram, 203 and co. Then we have to fill in the mass of the water evaporated. Here, the mass of the water evaporated in grams. Then we are also to get the energy supplied by the heater measured in joules. But before we go ahead to do that, like I promised, I want to show you what this is really looking like. So here, this is a typical example of what we're talking about. Here, this is the heater that the student is using to heat up the water. It is standing on a balance, an electronic balance, to take the measurement of the mass of water that have been evaporated. Okay, so if the water is boiling, of course, some water molecules will be lost to the atmosphere, so the remaining mass of the water will reduce. So we can take that reading from the balance. Okay, then this heater can be switched on. You can switch it on here, and of course it is getting its power from the socket here, and the timing is 100 seconds intervals. Okay, so in 100 seconds intervals we are going to be taking those readings. Now this is what I want you to note. What's going to be the means of getting the mass of water evaporated in 100 seconds intervals? You can see that if we have an initial reading, I think we're given one, let me confirm, 203.22 and 201.62. So initially we have 203.22 and 201.62 afterwards. Okay, so this is the initial measurement, this is the second measurement. Between these particular two, how do we get the mass of water that is evaporated? You can see that this mass measured in grams here, this here, initially at the first instance, it is greater. So the amount that was lost is going to be the difference in the 2 grammage of the mass of water that is being measured. So it's going to be 203.22 minus 201.62. So the mass will be the difference between these two. So we have it as 203.22 minus 201.62. And if you just do that mathematics, 2 minus 2 is 0. Here we can borrow 1. 12 minus 6, that is 6. And here we have 2 remaining, 2 minus 1. So it is 1.6 grams. That is the mass of water evaporated. And just like this, we also do for the subsequent ones. Okay. Another thing I want to point out from the look at this particular statement in 2. We are given that the heater supplies energy at the rate of, this is what I need you students to notice, at the rate of 38 joules per seconds. Then we're asked to fill in the values of the energy supplied by the heater in 100 seconds, 200 seconds, 300 seconds, 400 seconds. But it was originally given it's supplying energy at the rate of 38 joules per second. And look at what we're being asked to find. We are to find the energy supplied by the heater, but the unit is in joules. These are small things that students can really help you to make the best of your exam. So 38 joules per second, we have the energy. The energy rate is 38 joules per second. Then we are giving time to be 100 seconds, then 200 seconds, and so on. How do we get the energy that is used up? It's going to be the multiplication of the rate of supply of the energy multiplied by the timing, because look at this, this is joules per second. So if you multiply joules by second, you will see that the seconds will cancel and we have only the energy in joules remaining. So those are the understanding that will perfectly help you to just have a walkthrough in this exam and you have your full mark seamlessly. But without this understanding, you are not going to get the exam. But that is why you are here walking through this together, so that you can gain that understanding and you can use it to leverage on your exam and gain the academic excellence. So 2 things we have discovered. First, to get the mass of water evaporated, we need to subtract from the previous measurement that was taken, and to get the energy that was used to evaporate that mass of water, we have to multiply the rate of energy supply with the time that we are looking at. So we are going to go ahead and do that now. So from our previous discussion, we can now go ahead to compute the value of the mass of water that is evaporated measured in grams. Okay, so here it's just going to be 0. That's the initial one. But for subsequent ones, so in this particular case, we are going to have this 203.22, which is the initial mass, minus each of these subsequent entries that we have in the table. So it will be 203.22 minus 201.62, and that is 1.6 as we got initially. So this is 1.60 grams. Okay, here for the second one, it's going to be the same 203.22 minus now the new value that we have here, that's 199.79. so minus 199.79, that's going to give us what? 3.43 grams. So this is 3.43 grams. In the third case, we also have 203.22 minus 198.26, 198.26. So that is 4.96. So this is 4.96. And then finally, we're also going to have 203.22 minus 196.50. Okay, so that is 6.72 grams. Okay, so that is for the mass of water evaporated. Now we can also move on to the energy supplied by the heater. Initially, there is no energy supply, but once we begin to have some mass of water getting evaporated, that is an indication that some amount of energy has been supplied. And like I explained before, it's going to be the energy rate multiplied by the time that we are using. So in the first case, there is going to be 38 joules per second multiplied by 100, and that is going to be 3,800 joules. Okay, in the second case, it's going to be 38 joules per second multiplied by 200 seconds. So I can have 38 times 200. So that's 7,600 joules. 7,600 joules. In the third case, it's going to be multiplied by 300. That's 11,400 joules. And finally, it's going to be multiplied by 400. And that's 15,200 joules. So this is 15,200 joules. So this is the table that we are going to use to plot the graph of energy supplied on the vertical axis, okay, and the mass of water evaporated on the horizontal axis, just like this. And then we can determine the slope of the graph and find what the value of the slope means. So that's what we're going to do right about now. So here we can have this as our table of values, which we extracted from the bigger table that we got the values from initially. And then we have our graph. Now this is a modified scaled graph. Okay, your graph will be like twice the scaling for this one, but this is just representative, and I believe that you as a student out there, if you can understand it from here, you should be able to transfer it to your graph as appropriate. So we are going to have our vertical axis. So we have our vertical axis, and we also have our horizontal axis, just as is shown here. Now we are particularly told that we should start from the origin. So this have to be the origin, okay, and for this particular set of values that I have to get to fit into the graph, I have to use a scale of 4 units. Okay, so from here to here, I will say this is 4, this is 8, this is 12, and this is 16. Okay, so this is the axis for the energy in joules. Okay, and here on the horizontal axis, I can just use a scale of, I have 0 to 6.72, so I can say I have 0 to 7, so I can just scale like this is 1, 2, 3, 4, 5, 6, 7. Okay, so in that case, I can take it to be 2, 4, 6, and 8, and this is the mass in grams. Okay, so yeah, it's good to always title your graph. So I can say this is graph of the mass in grams versus the energy in joules. Okay, so we can now go ahead to compute the corresponding values for this. You can also note your scale. Here I could have said, okay, 2 centimeters represent 4 units. Okay, because it's a modified scale, I just want you to note that I said, okay, from here to here is 2 centimeters, so that is representing 4 units, but this is just a modified graph. Okay, so let's be on the same page with respect to that. So here, when m is 0, e is 0, so both of them are starting from the origin. So you have both of them starting from the origin here. Now when m is 1.6, e is 3,800. Now here on my graph, this is how you can actually go about to get your scale correctly. I have 10 divisions between 0 and 2, so I can say that 10 division is corresponding to 2. So what is 1 division corresponding to? 1 division, what is it going to give me? I can just cross multiply to say the value of 1 division is going to be 1 times 2 is 2 over 10, and 2 over 10 is 0.2. Okay, so each of these small division is 0.4, like here is 0.2, 0.4, 0.6, 0.8, 1, okay, 1.2, 1.4, 1.6, 1.8, and 2. You can see there's that consistency because I've been able to get the base value of each of the small units. Okay, and the same thing here, I can say 10 divisions corresponds to 4 on the vertical axis. Then I can say what is one division going to correspond to. I can also cross multiply to get that division to be 4 over 10, which is 0.4. So each one here, this is 0.4, 0.8, 1.2, 1.6, 2.0, 2.4, 2.8, 3.2, 3.6, and 4. Okay, incremental value of 0.4. So once I know that, I can actually compute all of the values that I have on the table of values correctly and extrapolate as appropriate. So in the first case, when m is 1.6, you can say I know this is 1. Okay, so here this will be 1.2, 1.4, 1.6. So this is 1.6, and for E it will be 3,800. So I know this is 2.4 here, 2.8, 3.2, 3.6, and between 3.6 and 4, this here is going to be 3.8. Okay, so I can just say this is now 3.8, and I'm going to look for the point of intersection of the two. So I just want to trace that out just very faintly for you students out there to see. So I have something like this and something like this, and the point of intersection is my point of interest that I can just denote as what I'm looking for. Okay, now when m is 3.43, yeah, I know this is 3. Then after that 3, I can say I have 3.2, 3.4, and 3.6. So 3.43 will be close to 3.4. Okay, and then that'll be like here, and then 7,600. So in between 4 and 8 is 6. So this is 6, 6.4, 6.8, 7.2, and 7.6. So there again, I can just look at this to be 7.6, and here 3.43, and I can just denote that as appropriate. Now students, let me just give you some very important hints. Now this is going to be a straight line graph, okay, because you can see already it's like it's going to be consistent. As a rule of thumb, if you just want to hack into what you are doing, this is what I could as well just ask you to do, that you just draw a straight line from the origin and pass through what you already have as your line of best fit, so that you can fit in all other values as appropriate. So something like this should be good for your graph, and then I will go ahead and just extrapolate the other values. Like for example, when I have 4.96, here we have 4.96 will be close to 5. So I can just say I count to trace from here. So I can just trace this up, and then the value for the energy is 11,400. This is 8, this is 10, 10.4, 10.8, 11.2. okay, so 11.4 will just be around there, and you can see how that is just consistent, and you'll be able to just scale to get your full mark and your line of best fit. Okay, so the other one, we have 6.72 and 15,200. so yeah, 6, 6.2, 6.4, 6.6, 6.8, so it's around there, 6.72, and then 15.2 will just be somewhere around there too. Okay, so that's just a reverse way for you to quickly also extrapolate your values, and you get your line of best fit. All right, so furthermore, we have to calculate the slope of the graph. Okay, the slope of the graph, that's going to be, if I call it m, that's going to be the change in the vertical axis, that's change in energy in joules, over the change in the horizontal axis, that's change in mass in grams. Okay, so we need to evaluate 2 points. So I just want to highlight my 2 points. So on the graph, if I want to take 2 points, I think I love this, it's directly on 12. Then I can also take this, which is directly on 4. Okay, so I can just take out those points to say I have this coming here and I have this going here, so that I can get the change in the vertical axis. The change in energy is here. The first one is 12 minus the second one is 4, and then the change in the mass, this is 4, this is 5, this is 5.2, 5.4. We have 5.4 minus, here we have it at just before 2, that will be 1.8. Okay, so the slope is going to be 12 minus 4 divided by 5.4 minus 1.8, and the unit, you don't forget that, is joules over gram. Okay, so if you want to get that m, 12 minus 4 is 8, that's 8 joules over 5.4 minus 1.8, 14 minus 8 is 6, so I've borrowed 1 here, remaining 4. 4 minus 1, that is 3.6 grams. So if we put, this is becoming quite interesting. You cannot leave your unit in grams, so you need to convert to kilogram to say that is 3.6 times 10 raised to power minus 3 kilograms. Okay, so that's quite an interesting one. If you leave it in grams, the definition of your slope will not be correct. You need to convert from grammage to kilogram, and to do that you divide by 1000, which is the same as multiplying by exponent minus 3. Okay, so if you want to just use a calculator to do that, you can say 8 divided by 3.6 exponent minus 3. Okay, let me put that in bracket to ensure that I'm doing the right thing. Okay, all right, so that is 2222.2, that's 2222.2 joules per kilogram. Alternatively, you can say this is 2.22 times 10 raised to power 3 joules per kilogram. So that is the slope of the graph. And finally, now we are finally asked what is the meaning of that slope. Look at this graph. We are taking the energy against the mass in grams. So this particular slope is meaning that it is the amount of heat that is needed to evaporate 1 gram of water. So it's the amount of heat needed to evaporate 1 gram of water at constant temperature. You know, it's at the boiling point that the evaporation is taking place, so it is at constant temperature. So that is the solution to this question that was created to look like alternatives of practical, but we've been able to demystify it and look at it holistically to answer the questions and plot the graph and interpret the slope of the graph as appropriate. All right. In this question, we're asked to explain what is meant by saturated vapor pressure and to state the factor that affects the saturated vapor pressure. So if we look at a system like this, in which we are increasing the temperature of a body system, if it is not closed, normally evaporation occurs and molecules of the liquid will escape. However, in a closed system, what we'll notice is that the molecules that will gain energy will normally tend to get evaporated from the liquid, and they will also get to exert pressure on the particular system, such that at the point the molecules that are evaporated will reach equilibrium with the liquid surface, that the rate at which molecules are being evaporated and the rate at which they are actually coming back to the liquid, they will be the same. Okay, and at that point the system is said to have reached saturation. So if you want to explain the saturated vapor pressure, we can say that at any given temperature, some energetic molecules of a liquid in a given system escape from the liquid surface as vapor, and at the same time they also return to the liquid. So vapor pressure is built up above the liquid in the process, and when the rate of escape equals the rate of return, the vapor is said to be saturated, and the pressure it exerts is called the saturated vapor pressure at that particular temperature. The factor that affects the saturated vapor pressure is temperature. So that is all there is about that question on saturated vapor pressure. All right. In this question, we're asked to define isotopes. Now, isotopes are atoms of the same element that have the same number of protons but different number of neutrons. So that will warrant that such atoms, they have the same atomic number but different mass number. And the classical example is carbon 12, carbon 13, and carbon 14, which all happens to be isotopes of carbon. Okay, so you can see in the first case, carbon 12 has 6 protons and 6 neutrons. In the second case, carbon 13 has 6 protons and 7 neutrons in its core. Okay, and then carbon 14 has 6 protons and 8 neutrons as shown in the diagram. So these are isotopes of carbon, and that is the definition for isotopes. Here in this question, we are being mandated to mention 2 uses of radioactive tracers in each of the following areas. So in medicine, in industry, and in the agriculture, we are to mention 2 uses of radioactive tracers, and here they are listed here. In medicine, radioactive tracers are used to monitor the function of thyroid glands. They can be used to detect blood clots in the brain, and they are used to sterilize medical equipment. In the industry, the radioactive tracers are used to detect leakages in underground pipes. They can be used to detect wear and tear of moving parts of machinery, and they can be used to detect traces of pollution in the environment. And in agriculture, radioactive tracers can be used to determine the absorption of mineral elements by plants. It can be used to study the mechanism of photosynthesis. It can be used to preserve seedlings and other food items, and is also used in the sterilization of insects. In this question, we are told that when light of frequency 5.4 times 10 raised to the power 14 hertz is incident on a metal surface, the maximum energy of the emitted electrons is 1.2 exponent minus 19 joules. Now we are asked to calculate the minimum frequency of radiation for which electrons can be emitted, and we are given the Planck's constant H to be 6.6 times 10 raised to the power minus 4 joules seconds. So here is the pictorial view of the scenario that is being given to us in this particular case, in which we have this light of photon energy HF, okay, in yellow, that is incident on this metal surface, okay, and then the maximum energy of the emitted electrons, this kinetic energy, is the energy with which the electrons will be emitted, was given as 1.2 times 10 raised to the power minus 19 joules. We are now asked to calculate the minimum frequency of radiation for which the electrons can be emitted. Now, this is what is happening in the emission of electrons from a metal surface. The photon of energy that is coming from the light source is actually the sum of the work function of the metal plus the kinetic energy with which electrons will be emitted. Okay, the work function itself is given as the Planck's constant multiplied by the threshold frequency. Okay, so we can express this as HF naught plus the kinetic energy. Since we are given the kinetic energy directly, we can just use that. Now, what we are asked to find is this minimum frequency, okay, that is the threshold for which electrons can be emitted. And looking at the information that we have been given already, we have the Planck's constant, okay, we have been given the frequency of the light rays that is coming onto the metal surface, and then we are looking for the minimum frequency of radiation. We have the kinetic energy, also we have the Planck's constant. So it's just a matter of rearranging this equation to effectively solve for the F naught that we are looking for. Okay, so rearranging this, we just have HF naught is equal to HF minus the kinetic energy when this kinetic energy moves to the left hand side, such that the minimum frequency of radiation we are looking for is going to be 1 over H multiplied by HF minus the kinetic energy. So if we want to express that, we'll see that the minimum frequency of radiation is going to be, what's the Planck's constant? That is 6.6 exponent minus 34. Let me just express this as 6.6 times 10 raised to the power minus 34. HF will be 6.6 times 10 raised to the power minus 34 times the frequency of the incident rays, okay, that is 5.4 times 10 raised to the power 14, okay, minus the kinetic energy that was given was 1.2 times 10 raised to the power minus 19 joules. So this is what we need to express on our calculator to find the minimum frequency of radiation for which electrons can be emitted. So we just need to bring in our calculator now. So I just want to put everything directly. So I'm going to have a bigger bracket taking care of the numerator before I now insert the denominator. So I have double bracket here. Okay, the second bracket for this particular expression, 6.6 exponent minus 34, okay, times 5.4 exponent 14. So I'm closing this particular bracket, then minus 1.2 exponent minus 19. So I'm closing the bracket for the numerator now, then divided by this denominator 6.6 exponent minus 34. Okay, so I just need to check, hope there is no mistake anywhere, and if I'm convinced that there is none, I can just press the equal to sign. So this will be 3.582 exponent 14. So this is 3.582 exponent 14 hertz. Frequency is measured in hertz. So that is the minimum frequency of radiation for which electrons can be emitted from this particular metal surface. Here we are asked to state 3 features that are common to electromagnetic waves. So this is a pictorial view of the electromagnetic waves with its wavelength, the direction of propagation, magnetic field in this particular vertical axis, and the electric field in the horizontal axis. And the features that are common to them are listed here. It is that 1, they travel with the speed of light in vacuum. Okay, they can be propagated through vacuum medium, which is an addendum coming from the first point. Then they undergo reflection, refraction, diffraction, polarization, and also interference. And interestingly, they are also transverse waves. So these are some features that are common to electromagnetic waves. In this question, we also mention 4 components of the nuclear reactor, and then we have to state the function of the components that we mention. Okay, so you need to be careful here that you just don't mention some components that you will not be able to state their function. So make sure that the components you want to mention, you can state what they do in the nuclear reactor. So this is a typical feature of the nuclear reactor, in which some of the components that we have there include the uranium fuel, the graphite moderator, control rod that is made of boron, the coolant, the heat exchanger, and the sheet. Okay, and we want to look at the functions of these components. We are going to see it now. So here, these are the components listed for us to see. The uranium rod serves as a fuel in the nuclear reactor, whereas the graphite moderator controls the speed of the neutron. The control rod made of boron is used to control the population of the neutron in the system. Then the coolant reduces the excess heat. Look at that, the word coolant. It reduces heat that is produced in the reaction. The heat exchanger is the one that converts the produced heat energy to other forms of energy to be used at the consumption level. And then the sheet protects against extraneous radiation, which is not good for the health. And that is all about this. So in this question, we are told that a man stands on a spring scale placed in a lift. The man is descending at constant velocity, and as a result, we are being asked what the scale is going to read with respect to the weight of the man. Now, normally for the man, if he's not in a lift, his weight will be the product of his mass and the acceleration due to gravity. Now, the weight is reading the reaction that the man is exerting on that scale. That's what the scale is going to read, and that is the weight of the man, which is mass times acceleration due to gravity. But the case in which the man is accelerating upwards, then the reaction that the scale is going to read is going to be his mass times acceleration due to gravity plus his mass times the acceleration with which the lift is ascending upward. And if it's accelerating downward, it will be the subtraction of the product of that mass and acceleration from the product of the mass and the acceleration due to gravity. But for this particular question, we are being told that the man is moving at constant velocity. Now, what is the interpretation of that? Constant velocity means that is not accelerating. So acceleration is 0. That's what constant velocity is going to talk about. And in that case, since it is constant velocity, we can see that the reaction on the scale will only be the product of the mass of the man and the acceleration due to gravity. So that will read the exact weight of the man, which is option B. In this question, we're asked which of the following is a derived unit. Now, being shown in blue ink is the list of all the standard SI units, and we can see that kilogram is there as a measure of mass, meter as a measure of length, Kelvin as a measure of temperature. Now, that is leaving Newton as the derived unit. And if you want to get it, Newton is the unit for force, and force is mass times acceleration. Acceleration is velocity over time. So that will be mass over time multiplied by distance over time, because velocity itself is distance over time. And we want to put the units. We have kilogram for mass, meter for distance, and second square for the time. Okay, so that is for Newton, which is the derived unit. Which of the following assumptions is made in a simple pendulum experiment? That's the experiment that is just shown, in which we have a bulb that is dangling from a rope and we'll be swinging it all around. Now, for this, looking at the experiment and the option A, that the suspending string is inextensible, that is not extensible, that is the correct option, because bulb having a finite size, having a definite mass is not the consideration. The other consideration is that the angle of oscillation must be small, not that it must be large. So the correct option is option A. A dentist obtains a linear magnification of 4 of a hole in a tooth by placing a concave mirror. We need to note that a concave mirror at a distance of 2 centimeters from the mouth. We are asked to find the radius of curvature of the mirror. Now, for a real object placed between the focal length and the mirror, there is going to be a virtual image that is formed behind the mirror. The image is going to be upright and it's going to be larger. It's going to be magnified. Okay, so now that means that with the understanding of this peculiarity of the image placed between the focal length and the mirror, we can use that to solve the question that we are given. For example, if you are to actually draw out the ray diagram for the particular situation we are talking about here, now this is going to look like this, and the image will be behind the mirror, and that's going to have an implication for solving the question. That image that is behind the mirror means that it is virtual. All right, now it's going to be erect, is magnified, and these are the attributes that we need to use to solve for the question. Like, for example, we've been told that there's a magnification of 4, and then the object distance is 2 centimeters. So if you are to just represent all of those on the diagram, magnification is the image distance over the object distance. Okay, we have been given the magnification as 4. We've been given the object distance as 2 centimeters, so we can get the image distance if we want to use that formula. Okay, so if you just want to put that on the diagram that we are told that is a linear magnification of 4. The object distance is 2 centimeters. So here, that's 2 centimeters, and then the image distance is going to be behind the mirror, and the image distance will be the magnification multiplied by the object distance. That's 4 times 2 centimeters, which is 8 centimeters. Now, because it is behind the mirror, this is translating to something we need to take note of. That means it is negative. It's not in front of the mirror, it's behind the mirror. That renders it as negative. So you don't just use 8 centimeters for your image distance, you use minus 8 centimeters. So now from the mirror formula, 1 over f is 1 over phi plus 1 over u. We can put in our values now. 1 over f, where f is the focal length, 1 over v, we now have v as minus 8, not 8, then 1 over u, that's 1 over 2. Now, if you just try to solve this, that will give us 3 over 8, and if you cross multiply, the focal length will be 8 over 3. But now, we are not asked to find the focal length, we are asked to find the radius of curvature. The radius of curvature is normally 2 times the focal length of the mirror. So, that means we are going to have another 8 over 3, so that the center of curvature that we are asked from the question, the radius of curvature that we are asked from the question is 2 times 8 over 3, and that's 16 over 3. Now, 3 can go in 16, we know that is 5, remaining 1. 3 can go in 1, that will be dot 3. So the correct option is option A. Okay, in the figure above, a resonance tube experiment is performed using one turning fork. As the water level is lower, the first resonance is obtained when the length of the air column L is lambda over 4. That's as shown on the diagram. Then we are being asked when the second resonance is going to be obtained. Now, if you are to actually look at the second resonance, while we are lowering the water level, the second resonance will also be obtained where the base of the sound waves coming from above where they normally meet. Now, that is another half lambda. So initially we have lambda over 4. Now we have lambda over 2. If we sum the two together, we are going to get the second resonance at the sum, which will amount to lambda plus 2 lambda over 4, and that's 3 lambda over 4. So the correct option is option B. Which of the following is true of the loudness of sound? Now, generally, we can deduce the correct option from all the above from the general formula for the loudness of sound, for the intensity of sound waves. And that is change in the pressure variation, change in pressure raised to power 2 divided by 2 times density multiplied by the speed of sound in the medium that we are talking about. So, if you were to look at these parameters that the loudness of sound depends on, and looking at the option, we will see that the correct option is that it depends on the square of the amplitude of the vibrating body, because the vibration is a measure of the pressure of that particular medium. So the correct option for this question is option A. It depends on the square of the amplitude of the vibrating body. A man clapping his hands at regular intervals observes that the echo of a clap coincides with the next clap. If the reflecting cliff is 160 meters away and the speed of sound is 320 meters per second, what is the frequency of the clapping? So if you are to depict that and just show it in the diagram just for the sake of representation, we have the man, we have the reflecting cliff, then we are told that the man is standing 160 meters away from the cliff. So this is 160 meters. So now, already we have been told that the speed of sound is 320 meters per second. As the man is clapping, the sound wave will travel to the cliff, and we know that here we are asked to find the frequency, which is 1 over the period. But normally, from the formula for the speed of sound, that is frequency multiplied by the distance, okay? Now that's f times lambda. Now the distance for us to actually get will be 2 times 160 meters, because the sound will normally emanate from the man, go to the cliff, and also reflect back to him, though we're having a double of the distance, which is 320 meters. So from the formula C is equal to frequency times lambda, we can have that 320 is 320f, and we divide both sides by 320. The frequency in that case is going to be 1 Hz. So the correct option is option A. The vibration of an ear column produces the sound in the, is it piano or guitar or flute or school bell? Now the correct option is flute, because that's where you put your mouth and you blow air into it. So it's the vibration of that ear column that produces sound in the flute. So the correct option is option C. So we are being asked which of the following unit is equivalent to a kilogram meter per second. Now, interestingly, normally if we are very vast, we could have just picked the one, but let's show our working. For the first one, we are seeing Newton multiplied by second raised to power minus 1. That's Newton per second. So that's the unit of force over time. Force is mass times acceleration. Acceleration itself is velocity over time. So that will give us mass over time raised to power 2. Velocity is distance or displacement over time. So with this, we can actually now say that mass, time, and distance, okay? Mass, the unit is kilogram. Distance, the unit is meters. Time is seconds, and that's raised to power 3. Now, this is kilogram meter second raised to power minus 3. That's not what we are looking for. Now, for the second one, we have Newton meter seconds, okay? That will be force times mass times time, all right? Now, force already we have gotten the previous one, and that is being shown in blue. That's mass times distance over time raised to power 2. That's force. So if you bring that in, we are going to have, for this, we have mass times mass over time raised to power 2 times distance, then times mass times time again. The other ones we can cut out. So we have this is mass times distance times mass, okay, over time, because only one time will remain at the denominator. Now that will be kilogram square, which is the mass, distance is meters over seconds. But that is also not what we are looking for, okay? Because this is kilogram square. Now the third option, we have Newton seconds. That is force times time. And force, like we got initially, is mass over time raised to power 2 times distance. Then we have another time here. Now that means we have time in two places. We can call that. So we have this is mass times distance over time. Now if you want to bring in the unit, mass is kilogram, distance is meter, over time is seconds. This is the option we are looking for. So the correct option is option C. A man walks 8 kilometers north and then 5 kilometers in a direction 60 degrees east of north. We have to find the distance from a starting point. So interpreting our question is the first thing that we need to get right so that we can solve the question. So if you draw our cardinal points, the north, south, east, and west, we are told that the man walks 8 kilometers north. So we can go in the north direction, that's 8 kilometers. And then from that location, he now moves 60 degrees east of north. So we need to also draw the cardinal coordinates, okay? And then locate 60 degrees east of north. So we have north, south, east, and west. East of north means that we start from the north and measure 60 degrees, and then we can get the movement of the man for another 5 kilometers, just as it is being shown. So what we are asked to is, we are now asked to get the distance from its starting position, which you can call the distance. That's what we are looking for. Now, already looking at this particular diagram, if you look to the point at the uppermost part, this is going to be angle 120 degrees because 120 and 60 they add up to 180, and that is angle on a straight line. And looking at this diagram, it can be solved with the cosine rule. Okay, this is where we need to understand the type of rules that we can employ in solving our question. If we take this as triangle ABC with small letter a facing the angle capital letter A, now we can say b squared beside b squared is equal to a squared plus c squared minus 2ac cos b. That is the general form of the cosine rule. And we can see that we can use this to get the distance, which is now b. Alright, so if we are to plug in our values, b squared will be 5 squared plus 8 squared minus 2 times 5 times 8 cos 120 degrees. Now, our aim as far as we are concerned is that we want to limit the use of calculator as much as possible. So, how do we find the cosine of 120? Cos 120 is minus cos 60, and we know cos 60 is 1 over 2. So, that means instead of using cos 120, we can say minus cos 60, which is minus half. So, if you are to just bring that in, we now have b squared is 25 plus 64 is 89. 80 and half, they can cut, that will be 40. Minus and minus will multiply each other to give plus. That means b squared is 139 and b will be root 139. But looking at the option, we need to open this bracket. Now, if we want to find the square root of 139, we can just oppose. 12 times 12 is 144. 13 times 13 is 169. 11 times 11 is 121. So, the answer we are looking for will be between 121 and 144. Okay, and with the options we are looking at, that is 11.36 kilometers. So I can do that and get my answer right. An electric kettle with negligible heat capacity is rated at 2000 watts. Now we are told that if 2.09 kilogram of water is put in it, how long will it take the temperature of water to rise from 20 degrees centigrade to 100 degrees centigrade? This is a classical example of the conversion or the conservation of energy, in which energy is being transformed from one form to another. And the forms we're talking about here is from electrical power to electrical energy to heat energy. Okay, now we have been given the power rating to be 2000 watts. We are looking for the time. We have the mass of the water, which is 2.09 kilogram. We have the change in temperature is from 20 to 100 degrees centigrade. So if we are to plug in all these values, I'm going to have 2000 T is 2.09 times 4200, which is the specific capacity of water times the change in temperature, and that will be 100 minus 20. That's ideally normally supposed to come in Kelvin, but the change in Kelvin is in response to the change in centigrade, so we can just plug the difference in there. Now we can divide both sides by 2000 and cut out the zeros. Then 2 can go here in 1, 2 in 8 is 4. We can just multiply these out. That the time will now be, now 42 and 4 is 168 times 2, this is like 336, but we need to factor the 0.09 into it, but already we are seeing that 336 seconds is part of the option, so that is our answer. Which of the following is the dimension of pressure? For us to get the dimension of pressure, we need to know the formula of pressure, and pressure is force per unit area, so that is force over area. Now we need to break this into its constituent standard international unit, SI unit. Okay, so force is mass times acceleration, and we have over area. Acceleration itself is velocity over time. Okay, so now we have mass over area times time, but velocity itself is displacement over time. So now these are the standard SI units that we can now use their dimensions to represent each one of them. Mass is a measure of kilogram. We can use capital M. Displacement capital L. Area, we have area is length times breadth. That's 2 lengths. Then time, we have 2 of them. So we can cancel one L, we cancel the other L to have M divided by L times T raised to power 2. So our correct answer from the option is option B. When a ball rolls on a smooth level ground, we are being asked what type of motion its center is going through. Now, if the ball is rolling in the positive X direction, what we'll notice that at the top, that will be rotating to the right also. At the base, that will be moving to the back. But the center of the ball only moves in a translational motion parallel to the ground. So the correct option is A. A bus of mass 40 kg is being dragged along the floor by a rope inclined at 60 degrees to the horizontal. Then we're told that the frictional force between the box and the floor is 100 newtons. So this is frictional force, that's 100 newtons. And the tension in the rope is 300 newtons. So here we have this to be 300 newtons. So we need to determine how much work is done in dragging the box through a distance of 4 meters. Now work is force times the perpendicular distance, okay? But here we need to find the amount of force that is being applied across the vertical axis, that's across the ground. And looking at this, we can actually resolve to evaluate the force by using the trigonometry, in which here our adjacent will be 300 cos 60. Okay, so the force in this particular acting on this particular body on the horizontal ground is 300 cos 60. Now, because it's working against the frictional force, we need to subtract that frictional force from it. So we have 300 cos 60 minus the frictional force, which is 100 newtons. Cos 60 is 1/2. So we have 150 minus 100, which is 50 newtons. And then our work will be the product of the force 50 times the distance, 4 meters. So that is going to give us 200 joules. And the correct option is option C. A cube of size 0.1 meters hangs freely from a string. We have to find the thrust on the cube when the cube is totally immersed in water. Now, what we need to understand is that an object will always displace its own volume whenever it is immersed in a fluid. So if you have an initial volume and place an object there, the rise in volume will amount to the volume of the immersed object. Okay, so that change in volume is actually the volume of the object that was immersed in the liquid. So in this particular case, we can say we want to evaluate the volume of the cube will be the length of the cube raised to power 3. Okay, and that will be 0.1 times 0.1 times 0.1, which is 0.001, the decimal place in 3 places. So that is 10 raised to power minus 3 meter cube. But what we are asked to find is the upthrust. Okay, but before we can get the upthrust, the density here we are given is 100 kilogram per meter square, 10 meters per second square, acceleration due to gravity. So that is the density. So now we can go ahead to get the upthrust, which is the force that the water is using to push the object that is immersed in it, and the upthrust is the volume multiplied by the density of that particular object. So that is just 10 minus 3 times 10 raised to power 3. Now from indices, we can sum the powers, and that will just give us minus 3 plus 3, and then the units can be cut just as is being shown, and the remaining unit that we are having is actually newtons. So that is 10 newtons, and the correct option is option number D. That's option D. An electric water pump rated 1.5 kilowatts lifts 200 kilograms of water through a vertical height of 6 meters in 10 seconds. We need to find the efficiency of the pump. Now, just as is being shown, that's a pictorial view of what we are talking about. Now, the efficiency is generally defined as the work output divided by the work input times 100%. Okay, is measured in percentage. So, yeah, what is the work output? The work output is the work being done to get the water up to the tank, and that will be mass times duration due to gravity times the height that is being raised to. Then the work input is the rating of the pump multiplied by the time that is being used. So if you just put in all the values for this, you can say it's 200 times 10 times 6 divided by 1.5 exponent 3 times the time, that's 10 seconds. Okay, so if we just cut out all that needs to be cut out, we just have 2 times 6 is 12 divided by 1.5 times 10, which is 15. We can divide further. This will be 4 times 20, and that is 80%. An object of mass 100 grams is projected vertically upwards from the ground level, and it has a velocity of 20 meters per second at a height of 10 meters. We have to calculate its kinetic energy at the ground level. Okay, so now this is the height that it attained, that's 10 meters, and then the velocity at that 10 meters is 20 meters per second. We don't know the initial velocity, okay, but we are given the mass to be 100 grams, which is 0.1 kilogram when we divide by 1000. So now we need to find a way to get the initial kinetic energy with which the stone is launched vertically upwards. Now that initial kinetic energy is actually the potential energy when it gets to that height of 10 meters. So we just need to use maybe mgh, or we can, if we need to use the potential energy, but here we can actually use half mv square to actually calculate the energy. But from the equation of motion, from v square is equal to u square plus 2as, now our s will be the height, which is 10 meters. Our a will be the acceleration due to gravity, but because it's going upwards, that's acting against acceleration due to gravity, so it's minus g, that's minus 10. Then the final velocity v is 20 meters per second. So if we input all this value, we can solve for the initial velocity just as is being shown. So the initial velocity, the square of u will be 600, such that we can now use that square of u in the formula for the kinetic energy to have half mv square, that's half times 0.1 times u square. Okay, that's 600. So if we just cut, this will give us 300, and times 0.1 is 30 joules. A 5 kilogram block is released from rest on a smooth plane inclined at an angle of 30 degrees to the horizontal. We are being asked what is the acceleration of the block down the plane. So we can just reflect the diagram of what is being asked in the question. This is the 5 kilogram block, and the plane is inclined at an angle of 30 degrees to the horizontal, and then is released from rest on that smooth plane. Now the question is, what is the acceleration of a body that is inclined on a smooth plane when we have the angle of inclination? That acceleration is given by the acceleration due to gravity sine the angle of inclination. So in this case it will be 10 sine 30, and that will be 5 meters per second squared. So the correct option is option A. The physical quantity that has the same dimension as impulse is momentum. This is just as simple as it can get. Impulse is just momentum, and that's all there is to this. Which of these statements are correct for the pressure in liquids? Okay, so we have all this pressure in a liquid at a point equally in all directions. Pressure increases with depth. Pressure at the depth depends on the shape of the container. Pressure at the same depth in different liquids are proportional to the density of the liquids. If you look at the formula for pressure, that's force over area, or we can say is density times acceleration due to gravity times the depth whenever we're talking about objects. So now that is telling us that, of course, pressure in a liquid at a point that's equally in all directions. That is correct. For the second case, pressure increases with depth. Now we are seeing the depth h that's being represented there. So that's correct. The third case, pressure at a depth depends on the shape of the container. That has nothing to do with pressure. Then finally, pressure at the same depth in different liquids are proportional to the densities of the liquids. Now we can see that density is being reflected in the relationship for pressure. So the correct option is option B. Okay. An ebonite rod rubbed with 4 attracts a glass rod rubbed with 6. Why? That's the question we are being asked. Now the ebonite rod will generally generate negative charges, okay, while the glass rod will generate positive charges. Now negative charges on the ebonite rod, positive charges on the glass rod will always attract, because opposite charges they attract, so that will cause the attraction between them, and the correct option is option A. The tension in a man's leg is 0.01 meters long, and we are now being told that if a force of 5 Newton stretches the tendon by 2 exponent minus 3 meters, we have to calculate the strain on the muscle. Now in the question we are given the force to be 5 newtons and the length to be 0.01 meters, and then the extension, the increase in length, is 2 exponent minus 5 meters. Now we need to get the strain, but the formula for strain is the extension over the original length. So what's the extension in this particular case? That's 2 exponent minus 5. What's the original length? That's 0.01, which is 1 times 10 raised to the power minus 2. So if you have to just solve this with normal indices, this will be 2 times 10 raised to the power minus 5 minus 2. The first minus because it's division, the second minus because of the power that is carrying, and the solution to that is option C. The diagram shows the velocity time graph of a vehicle. Its acceleration and retardation are what we need to calculate. So now, looking at the diagram, acceleration is a change in velocity over a change in time. So if you start from the origin and take that as 0, the acceleration is the increase in velocity in the first stage, in the first triangle, and looking at that, the slope will correspond to the acceleration, and that is 80 minus 0 over 20 minus 0, which is 4 meters per second square. Now that means we only have options B and C that are looking like they can be our answer, but let's get the retardation. That will also be the change in velocity, but from the initial velocity to 0. Okay, so now we have 0 minus 80. 0 is the final now, 80 is the initial, then the time 90 minus 50. That will be minus 80 over 40, and that's minus 2 meters per second. It's negative because it's a retardation. So the correct option is option C. The core of an efficient transformer should consist of laminated pieces of metal in order to do what? Okay. Now the reason that is doing done is to reduce the heat produced, because that the use of laminated pieces of metal will reduce the eddy currents. Gamma rays are produced when what happens? Now, generally, gamma rays are produced by the disintegration of radioactive atomic nuclei and in decay of certain subatomic particles. Like if you have the uranium can actually be broken down into, we have helium and thorium, and then to accompany that, there will be gamma rays that are actually also coming out. Okay, so that is how gamma rays are produced. So it occurs when energy changes occur within the nucleus of atoms. At what frequency should a 10 Henry inductor have a reactance of 2000 ohms? If we are to look at the inductor, we said this is 10 Henry, okay? Then the inductive reactance is 2000 ohms. We are looking for the frequency. If we just make use of the formula that the inductive reactance is 2 pi F multiplied by the inductance, we can just find the frequency by saying that is the inductive reactance divided by 2 pi L, and putting in our figures, that will be 2000 divided by 2 pi 10, and once we cancel out, that will give us 100 over pi hertz. So the correct option is option C. A semiconductor diode is used in rectifying alternating current into direct current, mainly because the semiconductor diode will rectify the current that is coming through. Okay, so instead of having a full wave, it's going to cut it off and only give us a one-dimensional, like here is only giving us in the positive y-axis, and that's how the semiconductor is used, because it allows current only in one direction. In semiconductors, the carriers of current at room temperature are electrons and holes. Electrons are going to carry the negative charge, holes are going to carry the positive charge. Okay, so in a typical semiconductor, the carriers of electricity at room temperature are just electrons and holes. So electrons will carry the negative charge, holes will carry the positive charge. So current will just flow as shown in the circuit, but the correct option is option B. A ball of mass 0.1 kg is thrown vertically upwards with a speed of 10 meters per second from the top of a tower which is 10 meters high. Neglecting a resistance, we have to find its total energy just before hitting the ground. So if you have the tower that is 10 meters high and the initial velocity with which this ball is being thrown is 10 meters per second, now we are told that this tower is 10 meters high. So now the ball will, of course, travel vertically upward and then descend down from its maximum height to the ground, and we have to just find the total energy just before hitting the ground. Now, how do we go about this question? Since we've been able to get the interpretation, especially through this picture, of what it's talking about. The first thing we need to know is that at the maximum height, the final velocity from its movement is going to be 0 because it will momentarily stop before descending. So at maximum height, the final velocity is 0, but we have that initial velocity u to be 10 meters per second. But what's the distance that it travels from that 10 meters height when it was thrown? What's the distance that it traveled before reaching that maximum height? Let's try and get that first, because if we can add that to the 10 meters, we can actually calculate the total energy just before hitting the ground as the potential energy at the top at its maximum height. So if we just use mass times acceleration due to gravity times the height, we can get that total energy, which is the potential energy at that height. So we need to get the distance d, which you can add to 10 to get that maximum height from the ground level that we can use to find the total energy. Now to get d, we can use the equation of motion. V square is u square plus 2as. Now that is at the maximum height. That's why we want to verify that the final velocity is 0, the initial velocity is 10 meters per second. Acceleration is going to be minus 10 meters per second square. It's going against acceleration due to gravity, so it's minus. Okay, so if you put in all this value, we are going to get 10 square plus 2 times minus 10 multiplied by d, which is the distance. Okay, so that 20d will be 10 raised to power 2 and d will be 100 over 20, and that is 5 meters. That means the total height from a maximum height to the ground level is 10 plus d, and d is 5. So we can find the total energy, which is the potential energy at the top at its maximum height, to be the mass times acceleration due to gravity times the maximum height, which is 15. So that's just 15 joules, and our solution is solved. A car of mass 800 kg attains a speed of 25 meters per second in 20 seconds. We have to find the power developed in the engine. Now, if you have the car here and it's 800 kg, okay, when they say it attains a speed of 25 meters per second, since we are not told, we can say the initial velocity is 0, okay, then that final velocity is 25 meters per second, and the time taken is 20 seconds. Now, from here, we can get our acceleration as change in velocity over time. The change in velocity is 25, the final, minus the initial, which is 0, divided by 20 seconds, and that will give us 1.25 meters per second square. That's the acceleration of the car. Now, power is energy over time. So we need to find the energy, and that is force times distance. So you can find the force and multiply with the distance and divide by the time. We can get the power that we are requested to find. Now, to find the distance, we need to use another equation of motion. V square is u square plus 2as. Now that s is the distance that it traveled and we know the final velocity is 25 meters per second, initial velocity is 0. Putting in the value for the acceleration that we just got, we can find the distance s to be 25 times 25, because 2 times 1.25, that is 2.25, and then we can divide to get our distance is 250 meters, but the power is force times distance over time. Now the force now will be the mass times the acceleration. We need to get that, then multiply by the distance over time. If we just put in all these values, that will be 800 multiplied by 1.25 multiplied by the distance is 250 over time. Time is 20 seconds. So we can just cut out. This is 40 times 250. 40 times 250. Okay, 40 times 1.25. That will give us 50. Then times 250. That will give us 12,500. Okay, if we are to round up, that is 1.25 times 10 raised to power 4, and that is the power that is developed in the engine for that period. A boy observes a piece of stone at the bottom of a river which is 6 meters deep. If he looks from the surface of the river, we need to find the apparent distance of the stone from him. Okay, now if we are to use the formula for refractive index, that is real depth over apparent depth, and we have been given the real depth of the river as 6 meters, and we have been given the refractive index of water as 4/3. We just need to equate all this so that we can find the apparent depth, which will give us 3 times 6 over 4. 3 times 6 is 18 divided by 4. That will be 9/2, which is 4.5 meters. So the correct option is option A. A metal of mass 0.5 kilogram is heated to 100 degrees centigrade and then transferred to a Euler calorimeter of heat capacity. Let's note that of 80 joules per Kelvin, containing water of heat capacity 420 joules per Kelvin at 15 degrees centigrade. The final temperature of the mixture is 25 degrees centigrade, and we have to find the specific heat capacity of the metal. Now, this is a classical example of the transfer of heat. The metal is going to be transferring heat both to the calorimeter and the water. Okay, so if you are to just look at that, the metal is a hot body. Calorimeter and water, they are not as hot as the metal, but there will be a transfer of heat. So if we use MC multiplied by change in the temperature for the metal, we have the mass is 0.5 kilogram. We are looking for the capacity. The change in temperature is 100 minus 25 because it's coming from 100 and then reducing temperature to 25. Now for the calorimeter, we already have the heat capacity, so we don't need the specific. We will just multiply the heat capacity by the change in temperature as shown, and then the same for the water. We have the heat capacity, then multiply by the change in temperature. Calorimeter and water are taking the temperature from 15 to 25. So if we just solve this and open up our bracket, we are going to get C is 5000 divided by 75 times 0.5. Now 0.5 is 1/2, so we can bring the 2 up to give us 5000 times 2 over 75. So we can cut now that C will be 10,000 over 75, and 25 can go in 75 in 3, 25 can go in 10,400, 400 over 3, 3 in 4, 1, 3 in 10, 3, remaining 1, 3, then 3 in 10 again, dot 3. So the correct option for us is option B. If the frequency of an emitted X-ray is 1.6 exponent 16 Hz, we are to find the accelerating potential. Now, generally, the energy for emitted X-ray, we can actually get in electron volt, or we can use the Planck's equation, which is the Planck's constant multiplied by the frequency. Already, we can also extend that frequency is speed over lambda, but let's just stay with this. Now, we are given the Planck's constant, we are given the frequency, then we can use all this to solve for the acceleration potential. If you just put in all the values now, okay, you can say the accelerating potential will be 6.63 exponent minus 34 times 1.6 exponent 16 over 1.6 exponent minus 19. 1.6 will cut out. So if we bring in all the bases of 10 and add them together through indices, this will give us 6.63 times 10 raised to the power minus 34 plus 16. Now divided means minus, then minus 19, those will now amount to plus. So you can say 16 plus 19, that's 35. 35 minus 34, that's 1. So this is 6.63 times 10 raised to the power 1, and that's 66.3 volts. So the correct option is option B. The effect of a particle in a fluid attaining its terminal velocity is that the what? Okay. Now the correct answer here is that it is option C, that the buoyancy force is equal to the viscous retarding force. Now the liquid in which the object is placed will normally want to exert a force upward to push it up, but the weight of the object itself will want to push it down. So when these two forces are equal, the object, the body, will attain its terminal velocity. It's not moving up, it's not moving down. It's like, let's say we can see it's at equilibrium. So the correct option is option C. All right. The eye controls the amount of light reaching the retina. How? Okay, this is a brief overview of the function of the eyes, and in the order that it happens, that first, light passes through the cornea, covering the eye, and it will refract it. Okay. Then 2, the eye rays regulate the size of the pupil, and that will control the amount of light that is allowed to enter into the eye. Then 3, the lens focuses light for the image onto the retina, and 4, the retina, which contains many photoreceptors, convert light into electrical signals. These signals are now processed to the brain and we get the image. So for this question, what controls the amount of light entering the eyes is the iris, and that's the correct answer. From the generating station to each substation, power is transmitted at a very high voltage so as to reduce what? What we want to reduce by using high voltage is heating in the coil. Why? Now, heat is actually directly proportional to the current. So if you are using high current, then there will be high amount of heat being dissipated. So to reduce that, which is amount to a loss, we use high voltage and not high current. Okay. A wire of 5 ohm resistance is drawn so that its new length is 2 times the original length. If the resistivity of the wire remains the same and the cross-sectional area is halved, what is the new resistance? Now, generally, resistance, resistivity, length, and area are related with this formula. So, like in the first case, the first resistance will be the resistivity multiplied by the length over the area in the first case, and the same will repeat for the second case. But now, looking at what we are told that the resistivity remains the same, the cross-sectional area is halved, and then the length is 2 times the original length. That means we can have the second length, L2, is 2L1, okay? But the second area, A2, is half of the original area. So A2 is 1 over 2A1. So we can just use all this information to find the resistance in the second case, okay? Since we know that resistivity remains constant. Now, from the first scenario, we can find the resistivity by saying it is R1 multiplied by A1 over L1, okay? And if we put in the value, we know the resistance is 5. So we're going to use this formula in the second scenario because resistivity remains the same, okay? So instead of resistivity, we now write 5A1 over L1, which is the area and the length, okay? Then multiply by L2. Now, L2 is now 2L1, okay? Then divided by the area. Let's bring the area down. The area is now half of the initial area. Though we have 1 over 2A1. We just need to cut out all this and our solution will come out. Now, half, that means the 2 will come up so that we have 5 times 2 times the 2 that is coming up, which is 20. So the new resistance is 20 ohms. The binding energy of helium is what? Okay, now we need to understand what is the binding energy. Actually, the binding energy is the energy that is released when a nucleus is being separated into its nucleon constituents. Okay, So like here we have for helium, helium is going to break down into 2 protons and 2 neutrons, but originally the helium contains 4 nucleons. So the change in energy from the energy of the nucleons to the energy of the protons and neutrons, that change, that difference is what is called the binding energy. Is the energy that must be broken for the helium to break into its protons and neutron constituents. So here we are going to have 4 nucleons plus the binding energy is equal to the 2 protons plus the 2 neutrons. Okay, so we just bring in the value of the atomic mass. 4 nucleons, the nucleon is just 1 atomic mass unit, so that is 4, plus the binding energy is 2 times the atomic mass of proton is 1.00783 and the atomic mass of the neutron is 1.00876. So the binding energy will be 2 times this. We just need to multiply them out, and this is what we will get, plus 2 times this will be 4, then 6, 13, 16 plus 1, 17, remaining 1 and 2, then minus 4 that is coming from the left hand side. So 2 and 2 is 4, so the 4 will knock out themselves. We just need to add the other decimal places, 0.01566 and 0.01734. So if you are adding us, that will give us 0.033 atomic mass units. Okay, so that's option A. A car battery rated 45 amp hour is charged with a charger whose rating is 2.5 amps. How long will it take to charge the battery fully? Now, just as it's being shown, we have 45 amp hour and we have 2.5 amps. From the formula Q is IT, we can just input our values to get the T will be 45 amp hour over 2.5 amps. Now, 2.5 is actually 5 over 2. So if we say 45 divided by 5 over 2, we are still on the same page. We can reverse that to say it is 2 over 5. And when we cut, that will be 9 times 2, which is 18 hours. So the correct option is option C. An electric heater with a potential difference of 240 volts is connected across its terminals. It has a total resistance of 960 ohms. We have to find the power rating of the heater. Now, the voltage is 240 volts. And the resistance is 960 ohms. Normally, the power rating is IV, Y is the current and V is the voltage, but we can get I from V is equal to IR, R will be V over R, and if we substitute that in the formula for power, instead of I, we now have V over R multiplied by V. That will give us V squared over R. So, yeah, if we want to use that, that will be 240 times 240 over 960. We can cut, 0 can cut, 24 here 1, 24 in 96 is 4, 4 here 1, 4 in 240 is 60. So the solution is 60 watts.
In this question, we are being asked that the time rate of increase in velocity is called what? Is it force, momentum, acceleration, or speed? If we try to look at the definition of what we are given here, we are told that the time rate, and every time we are talking about the time rate, that is saying something like we are dividing something with time. And what we are dividing here is the increase in velocity. Okay, this is what we are dividing. Increase in velocity will mean that we have a change in velocity. Okay, so if you are to interpret that in physics, you can say this is something like a change in velocity, then we have the final velocity minus the initial velocity over the time t. And if you are very conversant with formula A in physics, you know that final velocity minus initial velocity over time is nothing but acceleration. Okay, acceleration is defined as the rate of change of velocity with respect to time. So the correct option is option C. Acceleration is the correct answer here. In this question, we are being asked that which of the following quantities is a vector? Is it volume, momentum, energy, or speed? For us to be able to answer this question correctly, we should be able to know what a vector quantity is. Generally, quantities are divided into scalars and vector. So we have scalar quantities and we have vector quantities. Scalar quantities have only magnitude, meaning that you can find the value, we can quantify the magnitude, the amount of whatever it is. But vector quantities, they have magnitude and they also have direction, meaning that we don't just measure the value of our measurement there, but we also talk about the direction in which such a measurement is being applied. Now, looking at the options that we are given, here we have volume. We can measure volume in, say, liters and co, liters, centimeter cube, decimeter cube, but we know that volume is only a scalar quantity, okay? When we're talking about speed also, speed is a scalar quantity, because if you want to talk about a vector quantity in that case, we are going to be talking about velocity. Velocity is a vector quantity because it is displacement over time. Displacement itself is a vector quantity. Speed is distance over time. So speed is also a scalar quantity. So the correct option is lying between momentum and energy. If you want to really understand which of these is correct, we need to break this down. Let's look at energy. What is energy? Energy is defined as force multiplied by distance moved in the perpendicular direction. And when you hear distance moved in the perpendicular direction, that means it's talking about displacement, because the direction is already being specified in that. Meaning that if you are looking at energy, we know that force is a vector quantity because it has acceleration embedded in it, and acceleration is a vector quantity. So we have a vector multiplying a vector. Okay. Now, in physics, this is actually a dot product of two vectors. And when you are talking about dot product of two vectors, what that is going to give you is going to be a scalar. That is going to amount to a scalar quantity, because dot products always amount to scalar quantity. It's like you're having the x component and the y component multiplying by the x component and the y component. What we have is something like s squared plus y squared, and that is a scalar quantity. Okay. However, if we are talking about the momentum is a different case scenario in which we are having mass multiplied by velocity. That's what we talk about when we're talking about momentum. And looking at this, mass is a scalar quantity, okay, but velocity, like I explained before, is a vector quantity. It's as if here we are having a factor to either multiply or divide to increase or decrease a vector quantity. So the product of a scalar and a vector quantity will always give us a vector quantity. And with this explanation for this particular question, the correct answer out of all these quantities that we are given, the one which is a vector is momentum. The mistake that students may want to do is to pick energy. No, energy is not the correct answer. The correct answer is momentum. In an elastic collision, momentum is conserved as well as what? Is it velocity, kinetic energy, potential energy, or speed? Generally, for elastic collision, what is being meant is that the net loss in kinetic energy is zero. So every time we are talking about a body or a set of bodies undergoing elastic collisions, we are saying that this means that loss in kinetic energy is zero. And of course, there are generally two formulae that we use to evaluate the parameters of bodies undergoing elastic collision. And the first case, we talk about the momentum. Okay. And for the momentum, we are saying that the sum of momentum mass times velocity before collision is the same as the sum of the momentum after collision. And then the other case is that we are talking about the kinetic energy. that the sum of the kinetic energy is half mp square before the collision, okay, is the same as the sum of the kinetic energy after collision. So with this definition, looking at the options, what needs to be conserved alongside momentum in elastic collision is kinetic energy. So that's option B. The induced current in a coil always flows in a direction so as to oppose the change that causes it. This statement is known as what? Is it Coulomb's law, Lenz's law, Faraday's law, or the Ampere's law? Now let's have a holistic look at all the options that we are given, so that even if we are having this question in some subsequent exam, we'll be able to identify which is which and know the right answer to pick. And as a guide to that, I've drawn up a little brief which we are going to be looking at here now. So in the first case, we are talking about the Coulomb's law, and the Coulomb's law is a statement of the force of attraction between two bodies of different charges or of the same charges, and is saying that like charges they repel while unlike charges they attract. Okay, so that's the statement of Coulomb's law. The like charges repel, but unlike charges they attract. So the force of attraction between two charged bodies is expressed by Coulomb's law, and it is given as the constant of proportionality multiplied by the product of the charges divided by the square of the distance between them. That is Coulomb's law in option A. In option B, we are talking about the Lenz's law, but we are going to come to that later. Let's look at option C, the Faraday's law. Faraday's law is a statement that when the magnetic flux, which is linking a circuit, changes, an EMF is induced in the circuit, which is proportional to the rate of change of the flux. So now this is a magnet, and what we notice is that as the magnet is being moved forward and backward, what will happen is that there will be an induced EMF in this coil, okay, and the EMF induced is proportional to the rate of change of the flux that is producing it, the flux from the magnet. So that is the statement of the Faraday's law in option C. Now in option D, we are looking at Ampere's law, which is a statement that the magnetic field created by an electric current, like here we have an electric current, the magnetic field that such a current will produce is proportional to the size of the electric current with the permeability of free space as the constant of proportionality. So that is why we are saying this current is proportional to the circumference of this wire, okay, which is expressed as 2 pi r, and the permeability of free space is the constant of proportionality. So this is the statement of Ampere's law. And looking at all this, I want to isolate them out so that we don't get confused with what Lenz's law is talking about. Now we're clear with this also. The Lenz's law is actually a law that is riding on the Faraday's law. You know, we've talked about the magnetic flux that's being generated, which will also generate an induced EMF. But the Lenz's law is talking about the direction in which the current will be induced, and that's why we're having this negative sign. So this is a statement of the Lenz's law, okay? And what that means is that, look at this now. If the magnet, let me use the blue ink, if the magnet is being taken into the coil, what will happen is that the current that will be generated will be opposing the flow of that. So this will be the direction of the current. However, if the magnet is being taken away from the coil, then in that case, the current will move in the opposite direction also. So in this current in a coil always flows in a direction so as to oppose the change that causes it. Is a statement of the Lenz's law. But if we come across any of these other laws in some subsequent exam, we'll be able to tackle them correctly now. And the correct answer to this question is option B. It is the Lenz's law. Which of the following instruments can be used to compare the magnitude of charges on two given bodies? Without missing words, the correct option out of all this is the option C, the gold leaf electroscope that is being shown here. And what is normally the process that can be done to compare these two charges is that a charged body can be brought to the metal plate. The metal plate will ideally have some charges on it. So let's say these are some charges on it. And then the charged body is also coming with some charges. And the gold leaf is going to be deflecting, this gold leaf foil here is going to be deflecting to show the amount of charge that is being brought in contact with the gold leaf electroscope. Now, it is the amount of deflection that will determine the comparativeness of the two bodies that are being compared together. So, the amount of deflection of this gold leaf will tell us that, okay, this deflection is far higher than the other deflection. So, this body is having more charge than the other one that we are comparing. So, the correct option in this question, that which of the following instruments can be used to compare the magnitudes of charges on two given bodies, is the gold leaf electroscope, option C. A body of mass 2 kg is released from a point 100 meters above the ground. We are to calculate its kinetic energy 80 meters from the point of release. A good understanding of this question is going to help us to solve this. Look at the parameters that we are given. The mass of the body is 2 kilograms. Okay, it is released from a point 100 meters above the ground, but we are to calculate its kinetic energy when it is 80 meters from the point of release. Okay, so if you are to input that into a diagram, we'll have something like this. So we have 100 meters is the point of release. Okay, so the body, which is 2 kilograms, is released from that point. But what we are asked to find is the kinetic energy when it got to 80 meters from the point of release. So it's at this point that we are being asked that what is the kinetic energy at this point. This is the question that we have to solve for. Now, for us to get the value of the kinetic energy when it is 80 meters from the point of release, we make use of the principle of the conservation of energy. And here, in this case, we are having energy conversion from kinetic energy to potential energy. Okay? And now, for the potential energy, we need the value of the mass of the body, which we got to be 2 kilograms. Then, the height at which is falling from, which we got to be 80 meters. And the acceleration due to gravity, g. So, that potential energy at 80 meters is going to give us mass times the acceleration due to gravity times the height. So now for the mass, we have been given as 2 kilograms. Okay, acceleration due to gravity we can take as 10 meters per second square. And then the height we have been given as 80 meters from the point of release. Okay, we don't use 100. We are asked to calculate its kinetic energy 80 meters from the point of release. So we use 80. And in this case, if you are to multiply this, 2 times 10 is 20, 20 times 80 is 1600 joules. So from the options, the correct answer is option A. Which of the following waves is not mechanical? Is it waves in pipes, water waves, radio waves, or sound waves? For us to be able to answer this question, we need to understand the two basic types of waves that we have. And in physics, we have categorized them as mechanical and electromagnetic waves. The distinctive features of mechanical waves is that they need material medium for them to be propagated, for them to move from one point to another. And they are produced by the oscillation in a material medium. So if you are looking at mechanical waves, we'll be talking about waves in pipes, because that is needing the pipe to propagate from one point to the other. Water waves, because the water is the medium of propagation of those kind of waves. And sound waves, because air is the medium through which that type of wave is propagating. Now, looking at radio waves are not mechanical because they don't need any material medium for their propagation. They can even travel in a vacuum, and they consist of disturbances in the form of varying electric and magnetic fields. So that's why you need a radio antenna to broadcast them and to also receive them. So out of all these options, the wave that is not a mechanical wave is radio wave. So option C, radio waves, is the correct option. A loaded spring is set in simple harmonic motion. The force that tends to restore the load to its equilibrium position is what? Is it adhesive, elastic, frictional, or gravitational force? If you are to look at the example of what is being shown here, these are diagrams that can help us to depict that particular question as it's being asked. And we are being told that it is set in simple harmonic motion, meaning that looking at this is the loaded spring, okay? This is a spring, this is a spring, these are springs, okay? And then it is loaded. It can be either loaded from the top, as in the first case A, or it can be loaded to the side, as in this second case. And now if it is set in simple harmonic motion, that means that this particular attachment will first move towards the downward position and then also move back. And for this case, that means it will first move to the right if it is displaced to the right, and also move back to the left. Then it will continue the to and fro movement, constituting a simple harmonic motion. Now, we are being asked that what force is tending to restore the load to its equilibrium position. That means to its starting position. Like here, this can be the starting position. So if it moves here to the right, it will still go back to the starting position before moving back to the left. And the same also in this case, maybe here, that will be the original position, okay? Now, if you look at the options that we are giving adhesive, elastic, frictional, and gravitation. Frictional force is a force that tends to oppose motion. Gravitational force is a force that acts as a reason of the Earth's gravitational field pulling body towards the center of the Earth. Adhesive force is a force that mostly occurs in molecules to adhere them together, to bind the energy together. So in this particular case, the only option that is correct is the option B. It is the elastic force, because the spring is actually having some elastic properties that is tending to restore the load back to its equilibrium position. So the correct answer is option B. It is the elastic force. Which of the following cases cannot produce total internal reflection? A light ray traveling from A, glass to water, kerosene to air, air to water, water to ice. Before we can solve this question, we need to understand total internal reflection before we can find the case which cannot produce the total internal reflection. And as a reason of guide, I've drawn up this. For total internal reflection to occur, there are two conditions that need to be met, and these two conditions are highlighted as shown on the board now. The first one here is that light must be traveling from a dense medium to a less dense medium, meaning that the source of the light, the point where the light is emanating from, will be a denser medium. It should be the medium in which it is difficult for air to really pass through compared to the other medium. So like in this diagram, this region that is indicated in light blue will be the dense medium. So this is the dense medium. Okay. And then the outer one is the less dense medium. That's the first condition that needs to be met. And then the second condition, the angle of incidence must be greater than the critical angle. The critical angle is the point at which the rays of light is at normal to the surface where the reflection is occurring. So it is theta C, is this theta C in this particular diagram. So that is the critical angle. And you can see immediately after that angle is exceeded, here in this case here, we now have total internal reflection occurring. So let's look at the options we are given. Definitely the options are not talking about the angle of incidence being greater than the critical angle, meaning that we need to look at the density of the medium that the light is traveling from and that the light is going to. So in the first case, we have that glass to water. Definitely glass is denser than water, okay? So glass is a dense medium, water is a less dense medium. So total internal reflection can occur in that medium. In the second option, kerosene to air. Kerosene is a dense medium while air is less dense. If we are looking at the density of the medium, we need to consider something like, let's say, the heaviness of the medium, okay? So the dense one will not permit light rays to really pass through because it is dense, whereas the less dense will permit light rays to pass through because, of course, it has some permeability. The light can easily pass through it better than the dense medium. So looking at kerosene and air, kerosene will be dense, the air will be less dense, okay? Now looking at air to water, air and water, air is less dense compared to water. So the light ray, we find it easier to propagate through the air than through the water. So definitely this option C is a point in which total internal reflection cannot take place. The other one is water to ice. Water and ice, maybe you may not be too sure, but definitely air to water, that is a critical case. So for this question, which of the following cases cannot produce total internal reflection? It is definitely option C. Air to water cannot produce total internal reflection because it has to go from a dense medium to a less dense medium. And so C is the correct answer. The vacuum in a thermal flask reduces heat loss resulting from, is it radiation only, or conduction and convection only, or radiation and convection only, or conduction only? To understand this, let's have a look at the thermal flask. And here we are seeing the thermal flask with a stopper at the top, a double-walled container, then the containing liquid which we need to keep hot or cold as the case may be, insulated support, silver double glass top, and the vacuum. Okay, so now our question is asking us that from all this, what is the work of the vacuum? Okay, and if you look at the diagram, this is the vacuum, and we are to determine the kind of heat loss that the vacuum is preventing in the thermal flask. Now, looking at this diagram and by understanding of the transfer of heat, looking at the first option here, radiation only, the vacuum cannot be what is responsible for reducing the heat loss by radiation because radiation is the heat loss that occur without any material medium, okay? So actually, the radiation loss can occur whenever there is vacuum. So definitely the vacuum is not stopping the heat loss from radiation. Now, looking at the second option, conduction and convection only. Now, what is conduction? Conduction is a heat loss that occurs as a reason of heat loss through a solid body from a region of higher temperature to a region of lower temperature. And now, looking at vacuum, vacuum will not allow conduction loss because it's a vacuum. So, for conduction to occur, it needs a solid medium. Okay, so definitely the vacuum will stop that kind of heat loss. Looking at convection, convection is a heat loss that is associated with liquid or gas. Okay, so of course the vacuum is an empty space, so there's no liquid, there's no gas. So definitely what the vacuum will reduce in the thermal flask is heat loss by conduction and convection. So the correct option here is option B, by conduction and convection only. The diagram above represents an experimental setup for verifying which of the following laws. We have the lens law, refraction laws, reflection laws, and mirror formula. Let's look at the diagram to determine which law this is being set up for. So looking at the diagram that have been given, we can deduce that this O here is the object and this I is the image. Okay, so we have an object and image. We have this line as solid and we have this line as a broken line. What we can notice is that look at this distance to this distance, they are approximately the same, and that is telling us something like the object distance is equal to the image distance. Okay, that's the first observation that I'm noticing. And then if you look at this point, let me call that point A, let me call this point B. At point A, look at this angle and look at this angle. This is definitely the incidence ray. So I can say at point A, I can see that the angle of incidence in the first case is the same as the angle of reflection, okay, for the first case. And also at B, I can also notice that, look at this also at B, this angle and this angle, okay, this I2 and R2, I can also observe that they are the same. So I can also see that I2 is equal to R2. So the angle of incidence and the angle of the reflected ray are both equal. So I have this observation that I can deduce from the diagram that I'm giving. The object distance is the same as the image distance. At every point in which we draw rays of light, the angle of the incidence ray is equal to the angle of the reflected ray. These are properties of the mirror. The mirror is a case in which there is this wonderful symmetry all across the image of the object that is being formed, that we have the object distance and image distance, they are equal. The angle of incidence and the angle of reflection, they are also equal. And so the solution to this problem is definitely option D. So this is the mirror formula, and the correct option is option D. Which of the following statements about a moving object is correct? So we are given these 4 options that we will do well to examine one after the other. And so if we consider a moving object, let's say this object is moving in this direction, okay? So in the first case, we are told that when accelerating, the resultant force acting on it must be equal to 0. From the equation for force, we know that force is mass times acceleration, okay? So for this statement that is saying that the resultant force F must be equal to 0, that is not going to be possible, because when the acceleration A is 0, definitely F will also be equal to 0. So option A is not going to be the correct statement. In the second case, we are being told that there must always be a non-zero resultant force acting on it. But the fact that a non-zero resultant force is acting on it does not mean that the object may be moving. For example, we can have the Earth pull on it due to the acceleration due to gravity, but that does not mean that the body is moving, okay? Then we can knock out option B. Option C, at a steady velocity, the resultant force acting on it must be equal to 0. What does a steady velocity imply? A steady velocity means that the change in velocity is 0. So we can say V, the final velocity minus initial velocity, is 0. This warrants that, of course, since it's a steady velocity, acceleration, which is the change in velocity over t, is also equal to 0. So therefore, this acceleration will be 0 and the force will also be 0. Definitely that is going to be true, because at steady velocity, the resultant force acting on it must be equal to 0. There is no force to warrant the increase in acceleration. So option C is looking like our likely answer. But let's look at option D. At the steady velocity, the air resistance must be equal to 0. No, the air resistance has nothing to do with the steady velocity. So definitely the correct option out of all these 4 is option C, that at a steady velocity, the resultant force acting on it must be equal to 0. If the efficiency of a transformer is 100%, which of the following equations would be correct? If you are to consider the ideal transformer, the equivalent circuit, and we are to look at the parameters that we have, ideally what is given is that the voltage across the primary coil is proportional to the number of turns in the primary segment of the transformer, and the same is also applying to the secondary segment of the transformer. So if we are to look at the primary segment, okay, the primary, we can say that the voltage Vp is very proportional to the number of turns NP. And also in the same way, looking at the secondary side of the transformer, we can say the secondary voltage is proportional to the number of turns of the coil of the secondary side of the transformer. Now, if you are to include the proportionality constants, we can just divide these two statements so that we have Vp over Vs is equal to Np over Ns. Okay, such that we can conclude that Vp Ns is equal to Vs Np. Now we need to look at our equations, the options that we are given, and see which is corresponding to this. In the first case, we are having NPEP is NSES. There is no, look at what we got here. There is the primary multiplied by the secondary multiplied by the primary. But in option A, that is not what we are having. So definitely option A cannot be the solution. Okay. Then in the option B, the NSIP is equal to the NPIS. Okay. Looking at that, we are having a crossover, the number of turns in the secondary and the current in the primary. Okay. Then the number of turns in the primary and the current in the secondary. Now, the current is actually produced as a result of the voltage. So, this our equation. We can also say this is synonymous to the current in the primary multiplied by the number of turns in the secondary is equal to the current in the secondary multiplied by the number of turns in the primary, which is confirming that option B is a likely solution. Let's look at the other options. The number of turns of the secondary and the current of the secondary is equal to those of the primary. That is wrong because we are having a cross equation. Now, looking at this, number of the current in the primary and the induced EMF in the secondary. No, it's not the relation between the current and the induced EMF. It is the turns ratio that we are using. So we need to make use of the number of turns. So definitely the correct option among all these that we are given is option B. NSIP is equal to NPIS. A freshly demagnetized bar magnet is placed in the east-west direction to ensure that what is the purpose of that placement on the freshly demagnetized bar magnet. To understand this, let's look at a means of demagnetizing a bar magnet as shown on the diagram. Now, here we are using the process of hammering. It can be any of the other processes. What this process is doing ideally is to break the alignment of the magnetic field lines on the magnet such that instead of the magnetic field to be flowing as shown, we are going to have breakage and the alignment is going to be lost. Okay, so this is what is happening, is breaking that alignment, and once that alignment is broken, for the magnet not to realign, it is placed in the east-west direction so that the north-south pole will not realign what we are just scattering from the magnet. So the correct option out of all the options that we are given is that the molecular magnet will remain randomly arranged. They will be random. It won't be aligning in the way that it is for the magnet when it was not demagnetized. So the correct option here is option A. Which of the following graphs of a charge Q against potential difference V across capacitor is correct? So we have all these four graphs and we are trying to see which of these graphs is correct to express the relationship between the charge Q and the potential difference V across a capacitor. If we are to look at the capacitor with two dielectric plates, one plate and another plate, okay, separated like that. Ideally, there is a voltage that is going through the capacitor, voltage V, let's say is capacitor to capacitance C, okay. Then there is a charge associated with the capacitor Q. The relationship between Q, the charge of the capacitor, and the voltage V is given as Q is equal to CV, where Q is the charge, C is the capacitance of the capacitor, and V is the voltage. Now, if we recollect the equation of a straight line, the equation of a straight line says that Y is equal to mx plus C. And we have to compare this equation of a straight line to the equation Q is equal to CV. We can see that this is the same as CV plus 0 because the intercept C is now amounting to 0. Okay, the variable X is now amounting to voltage V, and the slope M is amounting to the capacitance of the capacitor, and then our Y will now be synonymous to Q. If we look at this critically, we can see that an increase in voltage will result in an increase in the charge Q across the capacitor. So this is a classical example of a straight line graph that is starting from the origin, since the intercept C is 0. So out of all the options that we are given, the one that is correct is option B. Option B is expressing correctly the equation between the charge Q and the potential difference V. You see, this is Q and this potential difference V of the capacitor. So correct option is option B. A small amount of air is introduced into the vacuum above the mercury in a mercury barometer tube. The mercury level goes down because the air molecules, we are given 4 options to consider. Is it because the air molecules eat the mercury and make it to expand? Or is it because the air molecules increase the pressure above the mercury? Is it because the air molecules cool the mercury and make it to contract? Or is it because the air molecules decrease the pressure above the mercury? For us to understand this, let's have a look at the mercury barometer tube, and it is as shown on the board now. So what we are being told is that there is a small amount of air that is introduced into the vacuum. So this is the vacuum, this is the vacuum. So now, if you are to introduce a small amount of air, let's put that in blue. Okay, so let's say this is small amount of air. What we notice that will happen is that this air that is introduced will exert some pressure on the mercury, and that will drop the level of the mercury. So the correct option in all the options that we are given is that the mercury level, this mercury level will have to go down. Okay, it will have to go down, it will go down because the air molecules will increase the pressure above the mercury. So the correct option in this case is option B. It will increase the pressure above the mercury. In this question, we are to calculate the quantity of heat needed to change the temperature of 60 grams of ice at 0 degrees Celsius to 80 degrees Celsius. We are given the specific latent heat of fusion of ice to be 3.36 times 10 raised to the power 5 joules per kilogram, and the specific capacity of water to be 4.2 times 10 raised to the power 3 joules per kilogram per Kelvin. Okay, now if you are to look at this question, there are 2 phases that we need to focus on to get the amount of heat needed to change the temperature of the ice at 0 degrees Celsius to 80 degrees Celsius, and it is as shown on the board. First, the ice at 0 degrees Celsius, okay, like here is at 0 degrees Celsius. We first need to transition to water also at the same temperature. The amount of heat that will be applied to this system, we first need to convert the ice at 0 degrees Celsius to water at 0 degrees Celsius. And then for the water that is now obtained, the heat will be added to the water to transition it from 0 degrees Celsius to 80 degrees Celsius as required in the question. So these are the 2 stages that we need to focus on. But first, we notice that the mass of the ice was given in grams. So that mass we need to convert to kilogram, so that we know that that mass will be 60 over 1000 kilograms. Okay, and that will be, and divide this, that will be 0.06 kilograms. That's the mass of the ice, and of course subsequently the mass of the water that we'll be working with. So now the 2 stages that I was referring to that we need is that first, we need the amount of heat that will convert the ice at 0 degrees Celsius to water at 0 degrees Celsius, and that will be giving us the mass of the ice multiplied by the specific latent heat of fusion of ice, which was giving us 3.36 times 10 raised to power 5, okay? Because that will be the amount of heat that we need to convert that ice to water, even though the temperature is not changing. But that's not all. We also need to compute the amount of heat needed to convert the water from 0 degrees Celsius to 80 degrees Celsius. And for that, we need to use the mass multiplied by the specific heat capacity of water multiplied by the change in temperature. Okay, so these are the two steps that we need to go through to get the amount of heat that will be needed in this system. And looking at the parameters that we are given, we already have our mass in kilogram. We are given the specific latent heat of fusion of ice, and we are given the specific heat capacity of water, and we can also see that we can get the change in temperature. So now with the parameters that we are given, we can look at how to evaluate this. So the heat that is needed as requested in the question will be first the mass at 0.06 kilogram multiplied by the specific latent heat of fusion of ice, that's 3.36 times 10 raised to power 5 joules per kilogram, okay, plus now for the amount of heat needed to raise the water from 0 degrees Celsius to 80 degrees Celsius. We still have the same mass because it's still the ice that was converted to water, so we still have 0.06 kilogram times the specific heat capacity of water, which is 4.2 times 10 raised to power 3 joules per kilogram per Kelvin, multiplied by the change in temperature. Now we don't need to be confused. The change in temperature in Celsius is the same as the change in temperature in Kelvin. Okay, so because of the consistency of the units, I'm going to put that in Kelvin because it's a linear change. If you have a 10 unit change in Celsius, it's also the same 10 unit change in Kelvin. So my change in temperature is 80 minus 0 because we are starting from 0 and going to 80. So the difference is 80 minus 0, and that is 80. So 80 multiplied by LT Kelvin. So this is the value that this is the amount of heat that we need to compute to get the quantity of heat needed to change the temperature of 60 grams of ice at 0 degrees Celsius to 80 degrees Celsius. So to compute that, I will bring in my calculator, and first I have 0.06 times 3.36 exponent 5, okay, plus the second case 0.06 times 4.2 exponent 3, all right, times 80. Okay, then I need to check, do I get all my values correct? I hope I didn't make any mistake. And once that is done, I can press the equal to sign, and so I have 40,320 joules. So this is going to give me, so the amount of heat needed is 40,320 joules. And of course, looking at the options, we are given kilojoules. So kilojoules is meaning that in thousands, so that will warrant 40.32 kilojoules as a solution to this, and that is option C. The correct option to this question is C, 40.32 kilojoules. The wire of a platinum resistant thermometer has a resistance of 3.5 ohms at 0 degrees Celsius and 10.5 ohms at 100 degrees Celsius. So we have to calculate the temperature of the wire when its resistance is 7.5 ohms. To address this question, I would love to drop a scale. Let's call it a linear scale. So if I want to just drop something like this, and we have the lower scale and the upper scale, we're told that the thermometer has a resistance of 3.5 ohms at 0 degrees Celsius. So let's say this is 0 degrees Celsius at the minimum, okay, that is corresponding to 3.5 ohms, and then it's having a resistance of 10.5 ohms at 100 degrees Celsius. So at the maximum, this is 10.5 ohms, and we're having this as 100 degrees Celsius. So we have to find the temperature of the wire when its resistance is 7.5 ohms. So when the resistance is like say around there, this is 7.5 ohms, but we don't know the temperature of the wire. So let's call that X. Let's say this is X degrees Celsius. I know students generally would love to bring in a formula to try and use, but I would rather want to approach this from the bottom up. Okay, let's say we are just starting from scratch and trying to solve this as a relational scale so that we can find the value of X. Since this is a linear scale, one of the things that can be done is to say that we can take some reference points, and already we have our reference point as the base, 0 degrees Celsius and 3.5 ohms, and then we can interpolate the value of X that is corresponding to 7.5 ohms that we are trying to find. And this is how we are going to do that. We can say that X minus 0, the difference between X and the base, okay, X minus 0 over the difference between the maximum and the minimum over 100 minus 0, okay, is equal to, here, the same way we did for the temperature, we're also going to do for the resistance. So the middle case, we are saying 7.5 minus the least 3.5, okay, and we are dividing by the difference between the maximum and the minimum, that is 10.5 minus 3.5. So you can see, and this is the place location for X, which is corresponding to 7.5. This is the minimum corresponding to 3.5. This is the maximum corresponding to 10.5. This is the minimum corresponding to 3.5. So if you know this approach, you can use this method to actually solve the question no matter the type of question that is coming. Not only in this type of question in which you are relating temperature to resistance. It can come in any format. But once you understand this, you can easily apply them so that you can get your solution on the fly. So if you want to solve this, you know, X minus 0 is X over 100 is equal to 7.5 minus 3.5, that is 4, okay. 10.5 minus 3.5, that is 7. So if you just cross multiply, if you are to cross multiply this, we are going to have 7x is equal to 4 times 100, meaning that x will be 400 over 7. And to do that, we can just bring in our calculator and say we want to put in 400 divided by 7, and I press SD button. So this is 57.14, I can say 0.14. So I have this as S is equal to, so I can say S is 57.14 degrees Celsius. But looking at our answers, we're only giving whole numbers, so we can round this off to 57 degrees Celsius. And looking at the options that we are given, that means the correct option is option D, 57 degrees Celsius. A transverse pulse of frequency 9 Hz travels 4.5 meters in 0.6 seconds. We have to calculate the wavelength of the pulse. We'll be able to solve this question if we're able to relate the equation for velocity, okay, both on the frequency and wavelength and the distance and time. So we know that generally velocity is given as distance over time, okay, but looking at what we are being given here, we are given a transverse pulse of frequency 9 Hz. We also know that in that case velocity will also amount to the frequency multiplied by the wavelength, okay. Frequency is f, the wavelength is lambda. So we just take these two formulae and we'll try and relate them together. We should be able to find this question as we are given. Now we are given from the question that there is a distance that was traveled, that the distance traveled is equal to 4.5 meters and the time taken to take that travel is 0.6 seconds. We are given frequency as 9 Hz and we are to find the wavelength. Lambda is what is unknown in this case. So all we just need to do is to input the value for all this into these two equations, and once we do that our solution will come out straight and direct. So this is what we are going to do. The distance is 4.5 meters and the time is 0.6 seconds, okay. So you have to say, even say this 4.5 meters, 0.6 seconds, that is equals to the frequency is 9 Hz, and if you recollect, Hz is 1 over seconds, okay. So 9 Hz multiplied by the lambda that we are looking for, multiplied by lambda, and with this we can just see that our lambda will be, by cross multiplying, 4.5 meters over 0.6 seconds times 9 Hz. Like I said, Hz is 1 over seconds, so the seconds here and the Hz will cancel out so that we can get our lambda by computing this on the calculator to say 4.5 divided by the product of 0.6 and, no, I didn't get that right, 0.6 and 9, okay. 4.5 divided by the product of 0.6 and 9. If I press my equal to, that's 5 over 6 or 0.83. So this is equal to 0.83 meters, okay. And looking at the option, the correct option is option C, 0.83 meters. In which of the following media is speed of sound the least? Is it air, brass, water, or wood? We need to look at this question critically to see what we are being asked. We are told that which of the following media is speed of sound is least, and they even embode that particularly. So we need to understand what we are doing when we are trying to address this question. Easily we could have said maybe it is air or wood, but let's look at the properties of the speed of sound in different medium. Now it has been established that sound travel faster in solids than they do in gas, okay. In short, the speed of sound, if you have to look at it, speed of sound is greater in solids, in solid is greater than liquid, which is in turn greater than gases. And why is this so? This is because in solids, the molecules are more compacted together. They are packed closely together. So they are able to transfer the sound energy from one molecule to another easier than in liquid, and of course least in gases. By reason of understanding of gases, the molecules of gases are loose. They are able to move around freely. They are not packed together. So the exchange of the sound energy is not as coherent in gases as compared to solids. So looking at this question, we will see that sound will travel fastest in brass, okay, then in wood, then in water, which happen to be liquid, and just travel least in air. So the solution to this is that out of all these media, the speed of sound will be least in air. So the correct option is Option A, that is where it will be least. It will be fastest in brass, but least in air. Which of the following characteristics of waves can a ripple tank be used to demonstrate? So we are giving those characteristics: reflection, refraction, and diffraction. So is it that the ripple tank will be able to can be used to demonstrate the three properties of waves? That's option A. Is it only 2 and 3? Is it only 1 and 3? Is it only 1 and 2? Now we need to understand the ripple tank and its operation for us to be able to answer this question. And here is a picture of the ripple tank that I just drew and came up with. If you are to look critically, let's take them one after the other. But first, to understand the setup of the ripple tank, here, this is a shallow tank of water, okay, that can be used to demonstrate the properties of waves. And this is an oscillating paddle. This is an oscillating paddle, and that oscillating paddle can be set in motion by a motor that is mounted on it to generate ripples on the shallow tank of water. There is a viewing screen that is set up below the shallow tank to observe what is going on, and then there is a source of light suspended above the setup to provide rays of light into the experimental setup. So looking at reflection, if we are to look at reflection, now the source of light coming from the illumination, we can see that we can have rays of light coming from here and coming on the shallow tank of water, but that ray of light can be reflected and an observer can just be looking, and that observer will see the same reflection on the screen below. So definitely reflection can be observed on the ripple tank. Okay, what about refraction? If you are to get another ray of light into the ripple tank, since this ray of light is traveling from a less dense region to a denser medium, because here above, before it gets to the shallow tank, above is here, and that is less dense. But getting to the tank, that will be a denser medium. The light ray will be refracted. Okay, so it will change direction a bit. We can have something like this. Okay, and then the observer can also see that a normal can be constructed. Normal can be constructed like that, and we can get the angle of incidence. We can get the angle of refraction, and on like that. That means that refraction can also be observed. Okay, what about diffraction? An aperture can be set up on the ripple tank just as is being shown, okay, so that the ripples that are generated on the shallow tank, once it gets to this aperture, it can actually be observed to be doing diffraction just as seen. So looking at all this, the correct option in this case is option A, that is telling us that the ripple tank can be used to demonstrate reflection, refraction, and diffraction. So the correct option is A, all of the above. Which of the following graphs gives the correct relationship between energy and mass when mass is converted to energy? So we are given these 4 graphs, and we have to pick the correct one that is depicting the true relationship between energy and mass when mass is converted to energy. The underlying principle of which this question is being asked is the Einstein's equation that relates energy to mass by saying E is equal to mc squared, where E is the energy, okay, E is the energy, m is mass, and c is speed of light. Okay, so this is the equation. All right, so what we need to now look is, looking at this formula, how do we translate the relationship between the energy and the mass and pick the correct option out of 4 that we are given? Definitely in the first equation in the option A, it's telling us that energy remains constant even if the mass is increasing. But looking at the equation that we have, this cannot be the solution. So option A is definitely out of it. I want us to look at option D. Looking at option D is telling us that with increase in mass, as mass is increasing, energy is decreasing. Okay, starting from the origin. And we also know from this equation that's not correct. So option D is also not it. Now, considering option C is telling us that there is a quadratic increase in energy as a result of increase in mass, because if you recollect your quadratic equation in which we have the x and y axis, this is actually a quadratic equation. So that is why this is going in a U shape, and this is meaning that the variable on the horizontal axis is actually of degree 2. That's why this is coming into place. That would have been correct if we have the speed of light here and no mass. But looking at what we are given, we are not looking at the relationship between energy and the speed of light. What we are looking for is the relationship between energy and mass. So that leaves us with only option B. And option B is telling us that there is a direct variation relationship between energy and mass, that an increase in mass will result to a corresponding increase in energy. And looking at this equation, E is equal to mc squared. You can see when we increase the amount of mass, okay, that will also result in the amount of the energy that will be generated. And that means the correct option out of all that we are given is option B. There is this linear relationship between them, that an increase in mass will result to an increase in energy. So the correct option is option B. An 800 kilogram car moving at 80 kilometers per hour collides with a 1200 kilogram car moving at 40 kilometers per hour in the same direction. So we need to note that these two cars, we are told they are moving in the same direction. If the cars stick together, we have to calculate their common velocity. So what we need to make use of here is the principle of the conservation of momentum, that the sum of the momentum before collision is equal to the sum of the momentum after collision. And to do that, we can look at the case scenario of the collision of these two cars, okay, as being shown on the board now. So we have in the first case, the mass of the first car was given as 800 kilogram. You can say this is M1 is 800 kilograms and is moving at 80 kilometers per hour. So U1, the initial velocity for this particular car, is 80 kilometers per hour. Okay, we are saying told that if we take this as the direction in which it's moving, it's colliding with another car whose mass is 1200 kilograms. So we can say the mass of the second car is 1200 kilograms. Okay, and then this car is moving with an initial velocity of 40 kilometers per hour. 40 kilometers per hour. But they are both moving in the same direction, so you can also denote its direction as this. Now we are told that after the collision they stick together, and that's why you can see they are sticking together here. We have to calculate their common velocity. If we call that common velocity V, because these two vehicles cannot be moving to the positive direction, and this one will now be resulting into this. This will be very, very wrong. Okay, so the direction of their final velocity will have to correspond to where they are coming from initially. So this is the correct location. But then the masses for the two vehicles will now amount to the addition of M1 plus M2. So here I can say this is M1 plus M2. That's their mass. That's the sum of their masses after collision. And that is 800 plus 1002 will give me 2000 kilograms. Okay. So if I want to use the principle of the conservation of momentum and momentum is the product of the mass and the velocity. Conservation of momentum warrants that the sum of the momentum before and after collision, they are the same. So we have the sum of m multiplied by u before is equal to the sum of m and the velocity after the collision. So that's what we need to just bring in into this equation to solve for it. And if you want to do that, that means that we will have m1 multiplied by u1, okay, plus m2 multiplied by u2 is equal to, now after the collision we are told that they stick together, so that's why we are adding their momentum, their masses together. So we have m1 plus m2 multiplied by the common velocity they are moving with v. Okay, so in that case, if we make v the subject of the formula, therefore the common velocity v will be m1 u1 plus m2 u2 over m1 plus m2. So what we need to do is, into this equation we are to input the value of all these, the mass and the initial velocity for both vehicles, and then we can solve for the common velocity. The first mass is 800, so we have 800 times the velocity is 80 kilometers per hour, okay, plus the second mass is 1200 multiplied by that initial velocity 40 kilometers per hour, when we are dividing this by the sum of the masses m1 plus m2. m1 plus m2 we have gotten to be 2000, okay, so all divided by 2000 kilograms. Now to evaluate this, we can just bring in our calculator and we can say, okay, first we have 800 times 80 plus 1200 times 40. Okay, I can check to see that I get everything correctly and can press equal to, so this is 112,000. okay, so I can say that this is my v is 112,000 over 2000. So I can cut with all these 0. 2 in 11, that is 5, remaining 1. 2 in 12, that is 6. So 56 kilometers per hour happens to be the common velocity with which the two cars will move when they stick together after the collision. So you can see, to avoid the common errors that come with calculations, you can see how I first evaluated my formula and expressed them in terms of the mass and the initial velocity, and then I input my values for the mass and the velocities. This is a good way to work so that you don't make mistake in trying to move and resolve your equations. So for this question, the correct solution is option D, 56 km per hour.
The mass of a load is doubled while the force acting on it is halved. The resulting acceleration of the load is what? Is it quadrupled, quartered, halved, or doubled? Let's look at the scenario that is being created here. So we can say in the first case, we have our M1, and in the second case, we are told that the mass is doubled. That's why we are showing that the mass is actually double of M1. But let's say this is M2, noting that the M2 is equal to 2 times M1. That's the implication of the fact that it is doubled. If you are to look at the force that's being applied, let's say on the M1, we have a force F1 that's being applied, and on the second case, we have a force F2 that's being applied on that body, on that mass. We are told that F2 is equal to half of A1 because they say the force acting on it is halved. Okay, so for us to put that into consideration, we can say F2 is equal to half of F1. So now we are being asked to evaluate the effect on the acceleration of the load. So what we're going to do is this. From our understanding of physics, we know that F is equal to ma, force is mass times acceleration. So in this first case, we can say that F1 is equal to m1 multiplied by a1. So 1 for the first case, and therefore our acceleration in the first case is F1 over m1. All right. Now in the second case, we can also do the same thing. We can say that from the fact that force is mass times acceleration, we're only considering this second case. Acceleration A2 will be F2 over M2, right? But looking at what we have deduced initially, that M2 is 2M1 and F2 is half F1, we can input that into this equation to say this is the same as, what is our F2 is 1 over 2 F1, okay? And what is our M2? M2 is 2 M1. Now this is what we need to evaluate to say that we can see that our A2 is going to give us, this is as if we are saying 1 over 2 F1 divided by 2 M1, and by reason of operation of mathematics, you know, that will give us 1 over 2 F1 times 1 over 2 M1. So this will be 2 times 2 is 4. We have 1 over 4 F1 over M1. Now, look at this. What's F1 over M1 here? That is A1. Meaning that what we have is that the A2 is equal to 1 over 4 A1. Okay? That is the resolution of the second acceleration that we deduce from our workings. And that means that that acceleration had been quartered. 1 over 4 is a quarter. So the correct option out of all these options will be option B. The resulting acceleration of the load is quartered whenever we double the mass and we halve the force. So option B is the correct answer. In this question, we're asked what the maximum and minimum thermometer reads. Is it the maximum temperature during the day and the minimum temperature at night at all times? Or the maximum temperature at night and minimum temperature during the day from the last reset? Or the maximum temperature at night and minimum temperature during the day at all times? Or the maximum temperature during the day and the minimum temperature at night from the last reset? For us to be able to answer this question, we need to understand the operation of the maximum and minimum thermometer, and it is as shown on the board below, in which there is a flow of mercury below and it is granulated in 2 units. There is a Fahrenheit unit in the inner region and the Celsius unit on the outer region. The maximum is taken from the bulb to the right and the minimum reading from the bulb to the left. That bulb is containing alcohol plus low pressure gas, and to reset, the marker is normally moved to the upper region, and that will be the reset, and it is from that reset that the temperature will be taken. So looking at all the options that we are given, the correct option will have to be the option D. So the maximum and minimum thermometer reads the maximum temperature during the day. Of course, the day will be hotter, and minimum temperature at night. Of course, the night will be cooler, but it is based on the last reset. That is the key word that we need to take. It's not at all times, okay? It is at the last reset. So the correct option is option D. An AC generator can be converted to a DC generator by replacing the, is it that we replace the commutator with an armature, or replace the armature with a commutator, or replace the commutator with slip rings, or the slip rings with a commutator. There are generally 2 methods to convert an AC generator to a DC generator. The other option that is not being mentioned there is by the use of rectifying diodes. But since they are not talking about this, we need to look at the AC generator and the DC generator, and this is an overview of those two. Here, this is the AC generator, and to the left, this is the DC generator. So what is generally done is that, looking at the AC generator, you can see we have a slip ring, but instead of the slip ring, we use a commutator. Okay, so what happened is that the slip ring is replaced with a commutator, and doing that, the output, instead of we having a sinusoidal output, in this particular case we are going to just have half wave output, because the alternating output have been changed to a direct output, so we are not having it alternating between the positive and the negative. So the correct option out of all the options that we are given is option D. We replace the slip ring with a commutator, and with doing that we can convert an AC generator to a DC generator. Which of the following statements is the correct reason for using soft iron in making the armature of an electric bell? Is it that it's a diamagnetic material, or it loses its magnetism readily, or is not easily magnetized, or it retains its magnetism for a long time? Now let's understand the basic principle of operation of the electric bell for us to be able to answer this question. So in looking at the operation of the electric bell, what happens in the electric circuitry? Now once this switch is pressed, what happens is that an electric current is induced in the electromagnet here, this and this, and that electromagnet will cause that this soft iron armature, this iron armature will immediately get magnetized, and once it will become magnetic, then it will draw this spring onto it, and as a result of this hitting it, the hammer will continually hit the gong as long as the switch is being pressed. That being said, immediately the switch is released, we want this electromagnet to actually stop its induction on the soft iron armature, and immediately that stops, we want the soft iron armature to lose its magnetism. Losing its magnetism will cause the spring to stop functioning, and then there will be no sound coming into the gong. So the feature we need on the soft iron armature is that it should lose its magnetism readily. Once the switch is released, it should also lose its magnetism, and in that case the correct option out of all the options we are given is option B, that the armature should lose its magnetism readily, so we use soft iron in making that armature. So option B is the correct answer. In this question, we are told that the diagram above illustrates a meter bridge circuit under balanced condition. We are to determine the value of X. What we need to understand is that we are talking about a meter bridge that is under balanced condition. And for a meter bridge, is ideally set up with a 1 meter rule. So meaning that from this end to the other end is 1 meter, which is the same as 100 centimeters. But already we are told that X have been taken out of it, so the remainder will be 100 minus X centimeters. So furthermore, we are now seeing that the 2 ohm resistance corresponds to X centimeters, and the 5 ohm resistance corresponds to 100 minus X centimeters. So we can just express that by saying 2 corresponds to X, okay, and then 5 corresponds to 100 minus X. What we need to do with this to solve is to just cross multiply these two equations so that we have 5x is equal to 2 times 100 minus x, and if we open the bracket to the right hand side, we have 2 times 100 is 200 minus 2 times x is 2x, so that we can take this minus 2x to the left hand side, and that will give us 5x plus 2x is equal to 200. 5x plus 2x is 7x, and that is equal to 200. To solve for x, we can divide both sides by 7. So this 7 will cancel this 7, and x will now be 200 over 7. Okay, so x is 200 over 7, and for us to express that on the calculator, we can just say 200 divided by 7. What is that going to give us? I'll press the SD button to express that answer in fractions, from fractions to decimal, and here we are seeing 28.57 centimeters. So S is 28.57 centimeters. But looking at the options, we have 71.4, 10.0, 28.6 with 7.2. We don't have 28.57, but we can see that that is a rounding up to this particular value, because what we do is that we can say that means x is approximately equal to 7 can be rounded up to 1, and that one will be added to 5. So we have it as 28.6 centimeters. So for this particular question, the correct answer is option C, 28.6 centimeters. Which of the following devices is used for storing electric charges? So we are given transformer, ammeter, potentiometer, and capacitor. Let's look at the functions of each one of them. A transformer is used to step up or step down voltages and currents. So this is a voltage or current scalar device. Okay, you either step it up or step it down. The ammeter is an instrument used to measure current. The ammeter measures current I. Okay. The potentiometer is used to measure voltage, and is actually the device that is mostly used to control electric devices, like say the volume in your audio mixer and co. However, the capacitor is a device that is used to store electric charge. So these store charges, and as such, the correct option out of all that we have been given, that which of the following devices is used for storing electric charge, the answer is capacitor, option D. An electron of mass 9.1 times 10 raised to the power minus 31 kilogram moves with a speed of 2.0 times 10 raised to the power 6 meter per second round the nucleus of an atom in a circular path of radius 6.1 times 10 raised to the power minus 11 meters. So this information has been provided for us, and we have to use it to answer questions 30 and 31. So first, in question 30, we are being asked to determine the angular speed of the electron. Let's have a look at the information that was given to us. So this is our electron. Let's say this is our nucleus. This is the nucleus at the center. Okay, this is the nucleus. So from the nucleus, we are told that the radius of the movement of the electron is given as 6.1 exponent minus 11 meters, and we're given the velocity, the speed with which the electron is moving, to be 2.0 times 10 raised to the power 6 meters per second, and the electron itself is having a mass. The mass of the electron was given as 9.1 times 10 raised to the power minus 31 kilograms. So these are the information that we need to make use of to evaluate the angular speed of the electron. And to get the angular speed of the electron, the angular speed W is given as velocity over the radius, the speed with which the electron is moving over the radius of its orbit around the nucleus. So to evaluate that, we can just say W is equal to, what's the speed that we are giving, 2.0 times 10 raised to the power 6 meter per second, okay, over the radius of the orbit, which is 6.1 times 10 raised to the power minus 11 meters. But now that angular speed, the unit will be in radians. So we need to bring in our calculator to calculate this. So if I bring in my calculator, I can say 2 exponent 6 divided by 6.1 exponent minus 11. That's the ideal way to input this. And if I press my equal to, so I'm getting this as 3.27 or approximately 3.28 exponent 16. So this is equal to 3.28 times 10 raised to the power 16 radian per seconds. And looking at the options, we can see that option A, that is the correct option. So that is the question number 30. So here in question number 31, still with the information that we are given, we are also asked to calculate the centripetal force acting on the electron. Okay, so what is the force that is acting on the electron and binding it to the nucleus of the atom? There is also a formula that is generally employed in use when we want to find that centripetal force, and it's given as F is equal to mv square over r, and m, that's the mass of the electron, v is the speed of the electron, and r is the orbital radius of the electron to the nucleus of the atom. So we just need to evaluate that by inputting all the necessary values. The mass is 9.1 times 10 raised to power minus 31, okay, multiplied by the square of the velocity. The velocity is 2.0 times 10 raised to power 6, okay, but the velocity is raised to power 2, so we have raised to power 2 here, all divided by the radius of the orbit of the electron around the nucleus of the atom, which is given as 6.1 times 10 raised to power minus 11. So we can evaluate that, and we bring in our calculator. We need to put the things in the right perspective, put them into the calculator correctly. So I'm going to put the numerator in bracket. I have 9.1 exponent minus 31, okay, times, now we have 2.0 times 10 raised to power 6, but this is now raised to power 2. Then I can close the bracket for the numerator, the ones on top, divided by the denominator is 6.1 times 10 raised to power minus 11, and then close the bracket. And I need to confirm, I hope I didn't make any mistake, 9.1 times 10 raised to power minus 31, 2 times 10 raised to power 6 raised to power 2, okay, then 6.1 times 10 raised to power minus 11, I can press equal to, and this is giving me 5.967 times 10 raised to power minus 8, or I can say 5.97, so this is 5.97 times 10 raised to power minus 8 newtons. Looking at my options, I didn't see any option corresponding to that, but we can see here, we can see 6, and that's an approximation of what we just got. So this is approximately equal to 6.0 times 10 raised to power minus 8 newtons. So the correct answer in this particular case is also option B, 6.0 times 10 raised to power minus 8 newtons. A device consumes 100 watts of power when connected to a 120 volt source. We have to calculate its resistance. So let's say this is the voltage source and the device is a load here, okay. So we are told that the power that it consumes is equal to 100 watts, and voltage is 120 volts, and then we have to calculate the resistance R of this device. Generally, power for an electrical device is given as P is equals to IV, but looking at this question, we know that we are not given I at all, but from Ohm's law, we know that V is equal to IR. That's a statement of Ohm's law. Since V is equal to IR, we can evaluate I to be V over R. And if we are to use this in our equation for power, then power will be I, we have gotten to be V over R, right? Which is I, that's I. Then we'll multiply that with V, meaning that power is the same as V squared over R. But looking at this question, we are looking for R. We know P and we know V. And in that case, we can just say we can invert this equation, make out the structure of the formula so that R will be V raised to power 2 over P. And what's the value for our V? Our V was given as 120 volts, so we have 120 raised to power 2 divided by the power. The power was given as 100 watts, right? 120 raised to power 2, if you take our calculator, 120 raised to power 2, that's equal to 14,400. So we have this as 14,400 divided by 100. So these two zeros will cancel these two zeros, so that our resistance will be 144 ohms. And if you look at our options, option D is corresponding to that the resistance for this device that consumes 100 watts of power when connected to a 120 volts source is 144 ohms. Which property of a wave remains constant when the wave travels from one medium to another? And here we are given 4 properties of a wave and we have to pick one of them. The correct option out of all these options is option D, frequency, because if you look at the wave formula, velocity is frequency times lambda. Generally, based on the medium, the velocity will be affected, the wavelength will be affected, but the frequency will not change. And a very good example of how to explain this is, consider your radio waves that, let's say there is a radio station that is broadcasting, and normally they are broadcasting at whatever frequency they are broadcasting. Wherever you are, if you tune in your device, say your radio device, and you are to get their signal, one of the things you notice is that your antenna will pick the frequency of the radio station no matter what it is. So if it is, let's say it is 92.5 FM megahertz, it's not going to change. It's the same frequency with which they are broadcasting that you still receive it, but every other thing they will definitely change. So the property of a wave that remains constant when the wave travels from one medium to another is frequency. So the fact that you are here in your room, maybe this is the location for your room, or maybe you are actually even underwater, you are on the sea, and you have your phone with you, maybe you're in a submarine. Once the frequency can get there, you will still get that wave at the same frequency. The frequency will not change. So the correct option is option D. The anomalous expansion of water occurs in the range, is it 0 degrees Celsius to 100 degrees Celsius, 0 to 4 degrees Celsius, 4 to 100 degrees Celsius, or minus 4 to 0 degrees Celsius. Let's try and understand the anomalous expansion of water. This is a diagram that is showing that anomalous expansion of water. And what we notice is that, let's consider a case in which we are freezing water. Okay, from the boiling point at 100 degrees Celsius, let's say we are freezing water. Ideally, what we expect is that since the water is initially liquid, okay, as it is liquid, the more we are freezing, the liquid will begin to solidify, okay, and if it is solidified, it will become more dense. So it will become more dense, it will get more compacted together. But what is noticed with water is that once water gets to 4 degrees Celsius, what happens is that the water will begin to expand. So instead of the contraction that we were noticing before, the volume or the mass of the water will seem to expand, and of course this is abnormal, hence the name anomalous expansion of water. So what happens during the anomalous expansion of water has just been explained, and it typically occurs between 0 to 4 degrees Celsius. So this is the range, and looking at the options for what we are given, we can see that the correct option out of all those options is option B. It occurs in the range 0 degrees Celsius to 4 degrees Celsius. A ray of light traveling from a rectangular glass block of refractive index 1.5 into air strikes the block at an angle of incidence of 30 degrees. we have to calculate its angle of refraction. Okay, so this will warrant that we are going to be using Snell's law to calculate the angle of refraction given the angle of incidence. And if we are to draw the diagram of the information we are given, so let's say this is our rectangular glass block. Okay, so this is the glass, and let's say here we have the here, this is the here. So what we need to look at in trying to solve for this is that in this question we are told that the light ray is traveling from, look at that word, we are told that it is from a rectangular glass block. So if you want to depict that correctly, we could have said that this is the ray of light. Let me use blue would be ideal. This is a ray of light traveling and getting to the edge of the glass block, and at the point where it's getting to the edge of the glass block, we can draw a normal. So this is the line of the normal, but the ray of light will now be refracted, so to be refracted from here, and all these angles are measured relative to the normal. So I can say the ray of light is traveling from the glass block and then to here, and then the angle of incidence is 30 degrees, so this is 30 degrees, and what we are asked to find is the angle of refraction. This angle, we can call it angle theta. Okay, so okay, let's use the ideal. If this is I, this is R in that particular case. So looking at this, Snell's law is the formula that is employed to solve this type of question, and it's saying that the refractive index is the sine of the incident angle to the sine of the refracted angle. Now we are giving n as 1.5, we are giving the angle of incidence as 30, and then we are looking for the angle of refraction. So all we need to just do is to plug in those values, that n, which is 1.5, is equal to the sine of the incidence angle sine 30 over the sine of the refracted angle sine r. Okay, this is like over 1, and if we are to cross multiply, we can see that sine r, sine r is equal to sine 30, which is 0.5 over 1.5. 0.5 divided by 1.5, let's evaluate that. 0.5 divided by 1.5, that's 0.333. okay, so it's 0.333, and it will continue like that. That's why the calculator just put a bar on top, that is a continual loop. Okay, but we want to find r, we need to evaluate the arc sine of this. So r will be the arc sine of 0.333 and on like that, and you can just evaluate that on the calculator. Shift sine will be the arc sine. Is our answer. We want to find the arc sine also, and we just press answer and close the bracket. So that is going to be 19.47. that is 19.47 degree. And looking at the options, we didn't have 19.47, but we have 19.5, meaning that the approximation was done, 7 was converted, was rounded up and added to 4, making it 19.5. So the correct option out of this question is option B, 19.5 degrees.
A rectangular piece of iron measuring 4 centimeters by 3 centimeters at 20 degrees Celsius is heated until its temperature increases by 100 degrees Celsius. We have to calculate the new area of the metal, but we're given the linear expansivity of iron as 1.2 times 10 raised to the power minus 5 per Kelvin. So, looking at this question, I've been seeing a whole lot of terrible solutions that are proposed, but we are going to find out how to tackle this question so that even if we meet it in subsequent papers, we'll know the proficient and the correct way on how to handle this question. So let's look at the parameters we are given. We are given the linear expansivity of ion. So we have the linear expansivity of ion is 1.2 times 10 raised to power minus 5 per Kelvin. We are given the dimensions of the piece of iron as 4 centimeters by 3 centimeters. So with that, we can calculate the area of the piece of iron. We know area is length times breadth, so that's 4 centimeters times 3 centimeters, which is 12 centimeters square. Okay, then we need not to be confused. We are given the initial temperature as 20 degrees Celsius, but we are told that there is a temperature increase by 100 degrees Celsius. So 20 degrees Celsius is not going to be our concern because we have been given the temperature increase already. So if we want to put that in the right perspective, our change in temperature is 100. Okay, that is the correct thing. It's not that we are saying 100 minus 20. If you have to use that, we'll definitely miss this particular question. But now, looking at this question, we are told that we have to find the new area of the metal when it has changed its temperature by 100 degrees Celsius. So definitely that means this is A1. This is A1 that we just computed as 12 centimeters square. But we are looking for A2. So we have to find A2. That's what the question is given. But look at this question. We are given the linear. This is where students will get to miss this question. We are given the linear expansivity of ion, not the area expansivity of ion. So for us to get the area expansivity of ion, when given the linear expansivity of ion, what we use is the area expansivity of ion is equal to 2 times the linear expansivity of ion. This is going to really help us to solve our question, and if we just miss this out, definitely we are going to miss out on the solution to this question. So this is the correct approach to take, that the area expansivity of ion is 2 times the linear expansivity of ion. Therefore, the area expansivity of ion is going to be 2 times 1.2 times 10 raised to power minus 5 per Kelvin, and that is going to give us 2 times 1.2 is 2.4 times 10 raised to power minus 5 per Kelvin. Okay, so that is the first of what we need to understand. Then, originally, if you are to use the formula for the area expansivity of ion, that is given as change in area A2 minus A1. Initial area is A1, the final area is A2, divided by the original area multiplied by the change in temperature. So looking at all these parameters already, we know our area expansivity, we know the change in temperature, we know the original area A1. All we need to now do is just to compute A2. So if you are to solve for that, I like expressing my equations linearly before trying to solve with the calculator. So here, if I cross multiply, I can say beta A1 theta is equal to A2 minus A1, and if I move A1 to the left hand side and rearrange, I can say the final area will be A1 plus beta A1 theta. And if we just factor out, already if you know this equation directly, you could have written it straight, that it is A1 into bracket 1 plus beta theta. So if I'm to put in all these values, that means A2 is equal to, what is the original area? That is 12. 1 plus, now be careful how you write this, the area expansivity is 2.4 times 10 raised to the power minus 5, okay, times the change in temperature. I've said before that was given as 100 degrees Celsius, okay, not 100 minus 20. That's 100 degrees Celsius. So I will say this times 100. Then I can close this bracket and work this out. So this is what I'm going to input into my calculator. And I'm bringing in my calculator now. So I can say 12 into bracket 1 plus another bracket 2.4 exponent minus 5 times 100. I love, okay, I'm closing this first bracket and I'm closing this second bracket. I love putting my calculations directly like this so that the margin for error will be greatly minimized. I'm not arranging numbers and crossing them. I've done that on the formula already, so I can just input all the values for all the units that I'm trying to compute. So this is the expression for that, and I will press equal to. Now this I can convert to a decimal format by pressing the SD button. So this is giving me 12.0288. So I can say my area is 12.0288 centimeter square. Okay, and looking at all the options that we have, we can see this is option C, 12.0288 centimeter square. A lot of calculations, especially as presented in past questions, went ahead and used the linear expansivity directly in the equation, and they got this. And I can show you they are going to miss that. The correct answer to this question is option C. Two bodies of masses 3 kg and 2 kg are separated by a distance of 50 centimeters. We are to calculate the force of attraction between them. We are given the gravitational constant as 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square. So if you are to consider the two bodies, it is as shown on the board here, the 2 kg and the 3 kg bodies. Okay, so now we are told that the distance between them is 50 centimeters. So 50 centimeters, but we know for our standard unit we are supposed to use meters. So the distance D is 50 centimeters. Well, we know that is the same as 50 over 100 meters. So we can divide this 5 here 1, 5 here 2. That is 0.5 meters. So we can express the distance as this is 0.5 meters. Then we have to calculate the force of attraction between them. But noting that we are given the gravitational constant as G, which is expressed as 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square. Now the formula that we normally use to solve for the force of attraction between two bodies in such a case like this is F is equal to G multiplied by M1 M2 over the square of the distance between them. So this is M1, 2 kg and M2 3 kg. So seeing we have all our parameters already, we can just go ahead to impute those parameters into the equation for our force. So we can have our F is 6.67 times 10 raised to the power minus 11 multiplied by the first mass, that is 2 kilograms, and the second mass, that is 3 kilograms, all divided by the square of the distance between them. So we have 0.5 raised to the power 2. So this is what we'll try and evaluate with our calculator. So if I bring in my calculator here now, you can see I want to express 6.67 exponent minus 11 multiplied by 2 multiplied by 3, but divided by 0.5 raised to power 2. So I can close the bracket for the denominator and check if I didn't make any mistake. 6.67 exponent minus 11 times 2 and 3 and divided by 0.5 raised to power 2. So seeing that I'm on track, I can press the equal to sign and I can see this is giving me 1.6008 exponent minus 9. So this is equal to 1.6008 times 10 raised to power minus 9 newtons. Looking at the options, we are not seeing any in 4 decimal places, so we can do an approximation for this to be 1.6 times 10 raised to power minus 9 newtons. So looking at the options, that means the correct option in this case is option A. Option A, 1.6 exponent minus 9 newtons. The diagram above illustrates an object moving in a circular path at constant speed. Which of the arrows indicates the direction of linear velocity? The question that we are being asked is asking for linear velocity. Normally there will be an angular velocity associated with such a body as moving in a circular path at constant speed, but that's not what we are being asked. And in this particular question, the linear velocity will be the one that Z is indicating. The other parameters we are seeing, this will be the angular velocity, this will be the centripetal force, but the one that is evaluating, that is indicating the linear velocity will be Z.
Which of the following thermometers is used to measure the temperature of the human body? Now, not to be confused, what is used to measure the temperature of the human body is the alcohol in glass thermometer. But let's have a feel of what they also do. For example, the thermocouple is a thermometer that is used to measure the temperature for gas turbine exhaust, diesel engines, and industrial processes. So we can have this to be used for industrial processes and is used for gas turbine exhaust. Okay. And then in the other case, we also have the gas thermometer. The gas thermometer is used for thermodynamics temperature. So this is used for thermodynamic temperatures and for meteorological works. That's basically the use of the gas thermometer. And then we're also seeing that we have the platinum resistant thermometer. The platinum resistant thermometer is unique in that it works on the fact that heat is directly proportional to resistance. So the platinum measures the change in temperature as a reason of its electrical properties, that the increase in heat will also have effect on the electrical properties, and it is used for high accuracy industrial works. So it's highly accurate, and that's why it's used for high accuracy industrial works. So out of all the options that we are giving, the ones that is used to measure the temperature of the human body is the alcohol in glass thermometer. So option B is the correct option. In the diagram above, the time taken to trace a wave between P and Q is what? Is it 2 periods, 1 period, 1.5 period, or 1/4 periods? For us to answer this question, let's look at some brief understanding of the wave. For the wave that is drawn as shown, a complete circle is taken from the point of origin, let's say from here, let's say from the point of origin here, to the complete circle, which is ending here. So from here to here, that's half a circle, but from the node to the node, that is a full circle. We have a maximum amplitude here, and we have the minimum amplitude here. So this is a positive half circle, and this is a negative half circle. So the combination of the positive half cycle and the negative half cycle makes a complete cycle. So having that understanding will help us to look critically at this question and answer it correctly. But here, we are not starting the point from the origin. We are starting at point P. So what we need to look at is, where do we have a complete circle starting from point P? So from here to here, let me use that in blue. From this point P, okay, so here will be half a circle, up to here is half a circle, then here will be a full circle, and the time for one circle is a period. So from P to this point, this is one period, this is one period, and then we can see that the time that we are looking at is not stopping at that one period, it's looking to another circle. But from here that we have taken to here, we can see that that is a half cycle. So this is half cycle, and the combination of the two for us to reach point Q from point P is the addition of 1 and 1 over 2. So for us to evaluate that, we can say that the time taken is 1 period plus half period, and that will be 1.5 periods. And looking at the option, that is option C, 1.5 period. Which of the following materials does not serve as a safety device in electrical circuits? Look at the question we are being asked here. We are being asked that which of these does not, and they put that in bold letters, so we need to note that. So which does not serve as a safety device in electrical circuits? So if you are to look at the basic electrical circuit, just a simple schematic as shown on the board, we can see from this, let's say this is our source and this is our load, okay? Looking at all the options, all the devices that we have, this is the heading, and it provides safety from electrical shocks. This is a switch. You can see that the switch can help to disconnect the circuit. Like here, it is open, so there will be no current flowing through this simple circuit. But if it is closed like this, then current can flow. Therefore, the switch can serve as a means of protection, because once it is open, there is no flow of current in the circuitry. So the switch is a safety device. The earthing is also a safety device. What about the fuse? When we are talking about the fuse, when you look at your plug, generally, when you look at the plug, you have something like the live wire, there is a neutral and the heart, but there is always this fuse that is a small transparent tube with a strand of wire passing through it. What this fuse does is that if there is a high current going into the electrical socket, then the fuse itself will just, the wire in it will cut off. So it will cut off that high voltage that is coming in, so as to protect whatever device is plugged into the circuit. So out of all these options that we are giving, the connecting wire is this line that we are just seeing flowing straight through. So definitely at no point in time can the connecting wire serve as a safety device. It is the means of carrying the electrical power, of carrying the current, of traversing the voltage from the source to the load. So it's not a safety device, it's a connecting device, but all the other ones, they are safety devices. So the correct option out of all these options is option A. Which of these is not serving as a safety device in electrical circuit? It is the connecting wires. Which of the following liquids has the highest surface tension? Is it soapy water, cold water, hot water, or oily water? We need to understand what they mean by the highest surface tension, and that is a measure of the ability of these liquids to resist external materials from being easily permissible into them. Like for example, if you have cold water or hot water and you are putting another substance on top, what is going to be observed is that those substances that you are putting on top will easily
dissolve into the water. The same thing with soapy water. But the oily water, if you are observant, the oil will tend to form a layer of protection. Okay, so if you say we are having something like a tube containing water, the oil will form a layer that is like protective at the top, so that substances that you are pouring will just tend to stay on top, meaning that there is a resistance from the oily water that is not permitting that substance, those substances, to easily dissolve into the liquid. That will not be the same in the case of cold water, hot water, or soapy water. Soapy water may offer some little resistance, but compared to oily water, that will not be the case. So the liquid with the highest surface tension among all those that are given is oily water. Option D is the correct answer. The nucleon and proton numbers of a neutral atom of an element are 238 and 92 respectively. We are to determine the number of neutrons in the atom. This question warrants that we understand how the nucleon, proton, and electrons of this question warrants that we understand the relationship between the nucleon and proton numbers of a neutral atom of an element. But for the case of explanation, let's consider the helium element in its neutral state. Looking at this diagram, we can see that the helium consists of 2 neutrons and 2 protons. So those 2 neutrons and protons are what constitute the mass number of the helium. So like here, we have the addition of neutrons and protons. That is what gives us the mass number. Whereas the atomic number is given by the number of protons. Electrons are revolving around the outer orbit of the helium atom, but we are not concerned about the electron here. We're only looking at the neutron and the proton. And the addition of the neutrons and protons will give us the nucleon. So you can see that from what we have in the question and are generally acceptable, the nucleon consists of the neutron plus the protons. Okay, that's what makes up the nucleon. So we want to find, like in this question, we want to find the number of neutrons. Neutrons in that particular case will now be the nucleon minus the protons. Okay, so and here we are given that the number of nucleon is 238 and the number of protons is what? Is 92. So this is just what we need to evaluate from the question, and if we want to work that out, we can say 238 minus 92, that is going to give us 146. So here we have the neutrons giving us nucleon minus proton is going to be 146. That's option D in our question. So this is equal to 146, and it is option D that is the correct option from the options that we are given. An instrument used to measure relative humidity is from the options we are given, the correct option is the hygrometer. Okay, the hygrometer is the instrument that is used to measure the amount of water moisture, water vapor in the air. So that is hygrometer. But what about the other ones? The hygrometer is used to measure relative density based on buoyancy. So this is used for measuring relative density. Whereas the pyrometer is an instrument that is used to remotely measure the temperature of an object. So if you are looking at the corona case that is so rampant around the year 2020 year, what you notice is that the practitioners that are measuring temperature, they don't want to get close to the patient because they don't even know if the patient is susceptible to COVID or is already COVID infected. So what they do is they take this type of machine and they just point it at the person. Okay, so the person to be measured, maybe the person is just standing aloof and the person measuring is also not standing close, but the person will just use this pyrometer and beam it
to the forehead of the person. So whenever you see that instrument, know that that is a pyrometer you use to measure the temperature, but it is done remotely. Okay, so what about the manometer? The manometer is generally an instrument used to measure the gas pressure. So that is it. If this question is coming out in some other case and they are asking which instrument is used to measure temperature remotely, you know that is the pyrometer. To measure relative density, that's the hydrometer. To measure gas pressure, that's the manometer. But to measure relative humidity, that is the hygrometer. The area under a velocity time graph represents what? Is it the speed, acceleration, moment, or distance? If I bring in a typical velocity time graph as shown on the board here, and we are to find the area under the graph, let's say we are to not look at the whole velocity time graph, just a section. So let me shade the section I would like to look at. Let's say we are to look at this section shaded. Okay, now we can see that that section that is shaded is pointing to the fact that this is a rectangle. This is a rectangle, and it has sides from A to B. This side AB. Let's say this is the length. Okay, let's say this is the length, and let's say this is from the point A to point D. This is the height. Let's say it's the breadth. We know that the area of a rectangle, the area of rectangle is length times breadth. But what I want to actually draw out is the use of the unit to derive the solution to this. And what we will do in that case is that we have L in seconds multiplied by D in meters per second. So we have L in seconds, okay, multiplied by B in meters per second. Okay, so if we are to do that, what we'll do is this is L seconds times B meter per second. So we can say this is over 1, and we can say that the second will cancel the second. So the area is length times breadth, but the unit is in meters. The unit is in meters. It's these meters I want us to actually look at, meaning that the area under a velocity time graph is nothing but the distance, because the distance is what is measured in meters. If it is moment, that will be a totally different unit. Acceleration, that will be meter per second square. Speed, that will be meter per second without a direction. That cannot even be the case. So looking at the option, I just use this means to explain out the fact that the area under the velocity time graph is nothing but distance. So that is as shown on the calculation, and the correct option is option D. Which of the following statements about a neutral atom is correct? Before we consider the statements following this question, let's look at the atom in its neutral state. So here we have as a sample, we are considering helium here, and what we notice is that based on the model of the atom, the electrons revolve in the orbit around the nucleon. So the nucleon is this centerpiece. Okay, this is the nucleon, and it consists of the proton and the neutrons. So looking at the first option, we are being told that the core is composed of electrons and protons. That will be wrong. Why? Because the core is composed of neutron and proton. Electron is in the outermost side. So that option A is definitely wrong. Option B, the number of electrons is equal to that of neutrons. Number of electrons, number of neutrons. No, for the neutral atom, they don't need to be the same. The electron may be far lesser than the number of neutrons, but that is not going to be the case in this option that we are being given, that the number of electrons is equal to that of neutrons. Then option C, the number of neutrons is equal to that of protons. Neutrons, protons, no, that is not the characteristics of the neutral atom. That has nothing to do with the neutral atom. So option C is also wrong. Option D, the number of protons is equal to that of electrons. Look at this. The proton is the positive charge of the atom. The electron is the negative charge of the atom. For the atom to be a neutron atom, those two numbers will need to negate themselves out so that the atom will not be carrying either a positive or a negative charge. So option D is the correct option in this question. That which of the statement about a neutral atom is correct? It is that the number of protons is equal to the number of electrons. Which of the following properties is not exhibited by sound waves? So let's look at each of the properties that are highlighted. In the first case, diffraction. Diffraction is talking about a situation in which the wave that is coming, let's say this is the source of our sound wave in this case. Okay, let's say it's a mic. And then as the wave is coming, if we are to look at diffraction, we can say, let's talk about a window that is open. Okay, an open window. And what normally happens is, once the sound waves get to the window, then it will be diffracted in such a way that it also starts being amplified just as shown. So this is the reflection of diffraction, but that is definitely a property of sound waves. If you are to look at polarization, polarization is a case in which the sound wave is restricted in its movement. That is not applicable to sound waves. Ideally, the sound wave that is even emanating from the mic that we are using as sample can traverse in many directions, and nothing will stop it. If it's like an omnidirectional mic, it will just propagate in all directions without any restriction. But polarization refers to a restriction in the vibration of the source of the wave. So it can be polarization. So definitely polarization is the correct option. But let's also look at the other options. We can look at interference. Interference is a phenomenon in which some other waves will come to distort the particular wave we are talking about. And here, if it is sound wave, like coming from the source here, you can have, let's say you can have a vehicle that is moving along the road, and once the vehicle is also making some noise, maybe the horn is being pressed, and as a result of that, it can come out and interfere with the sound wave that is coming from the sound source. So interference is also possible with sound waves. And then let's talk of reflection. Okay, reflection when it comes to sound waves means that we are talking about echo. Like you have your sound source and it's going out. When it comes to a non-permeable surface, let's say a brick wall in an enclosed room, that wave will also be reflected back. So the reflection is what is going to generate what is referred to as echo. So out of all the options that we are given, diffraction is a property of sound waves, interference is a property of sound waves, reflection is a property of sound waves. That which is not a property of sound wave is polarization. So option B is the correct answer. When ultraviolet light is incident on certain metallic surfaces, particles are emitted. These particles are called what? Is it positrons, protons, photoelectrons, or photons? So let's say this is a metal with ultraviolet light incident on this particular metallic surface. So let's say this is our ultraviolet light. What happens with this ultraviolet light or photon energy E, where E is Planck's constant multiplied by the frequency of the ultraviolet light? What will happen is that if this metal has a work function W, but in the case in which the energy of the photon light is greater than the work function of the metal, then what's going to happen is that the electron, this electron here, is going to be emitted in such a way that it will move out of the metal surface, and it is called a photoelectron. Okay, so what happens is that this electron was emitted from here, and in being emitted, is emitted and is being emitted, and its kinetic energy is given as the difference between the energy of the photon of light that is coming minus the work function of the metal. So in this particular question, the particles that are emitted are the photoelectrons as denoted in this particular explanation. So the correct option for this question is option C. Photoelectrons are emitted when ultraviolet light is incident on certain metallic surfaces, and the energy of the ultraviolet light must be greater than the work function of the metal. So option C is the correct answer. Niels Bohr drew certain conclusions about the structure of the atom. Which of the following statements is one of those conclusions? To answer this question, let's look at the model of the Niels Bohr atom, which is as shown on the board now, in which we have the atom, the nucleon at the center, and the electrons revolving in orbits around the nucleon. So in the option number 1, in the first option that we're given, here we are being told that the allowed orbits contain the same number of electrons. Looking at the model of the Niels Bohr atom, we are seeing that the first orbit contains 2 electrons, the second one contains 8 electrons maximum. Okay, so definitely the first option cannot be correct. They are not having the same number of electrons. We'll come back to option B. Let's look at option C. All the orbits represent the same amount of energy. That cannot be correct because looking at the formula for the energy level, En is equal to minus 1 over n squared multiplied by 13.6 electron volts. We can see that each of the orbits cannot represent the same amount of energy, because the first one, in this case, will have to be E1 is equal to minus 1 over 1 raised to the power 2, 13.6 electron volts, and let's say that is like minus 13.6 electron volts. Then E2 will have to be, now n is 2, so we have minus 1 over 2 raised to the power 2, which is 4, times 13.6 electron volts, and that will be minus 4 in 13, that is 3, remaining 1, 4 in 16, that is 4. So these are not the same amount of energy, so definitely option C is also wrong. Looking at option D, we are being told that the orbit with the least energy is farthest from the nucleus. Let's look at that. Now, the orbit with the least energy means that is the smallest. But looking at this that we just postulated, E1 and E2, you can see that E1 is less than E2. So E2, the one that is farther away, this is corresponding to n equal to 2. E2 that is farther away is more, because on the number line, the higher number will be less when it is negative, while the lower number will be more, because they are both carrying the negative sign. It's as if we are having, let's say we are having a number line, and you have 0, 1, 2, but here you have minus 1, you have minus 2, you have minus 3. So definitely the numbers here, they are lesser. The numbers to the left, they are lesser. The numbers to the right, they are more. So if we are looking at which number is greater, we can see that minus 1 is greater than minus 3. So minus 3.4 electron volts is greater than minus 13.6 electron volts. So the orbit with the least energy is not the farthest from the nucleus. The orbit with the least energy is the one closest to the nucleus. In short, it is the ground state. That is n is equal to 1. So definitely option D is also wrong. And that means that the correct option is, that is remaining here, is only option B. That within an atom, there are certain allowed orbits. Of course, look at this. Here we have the first orbit, n is equal to 1. The second orbit, n is equal to 2. The third orbit, n is equal to 3. So these are the allowed orbits for the electrons of the atom in the Niels Bohr model of the atom. So the correct option is option B, that within an atom there are certain allowed orbits. The graph above illustrates the variation of temperature theta with time t for a solid that is being heated. We are not told the solid, but we just know that it is being heated. Which processes take place at segments P and Q respectively? So we are being asked what process is taking place as we are looking at
this segment P and segment Q respectively. Respectively means that P first, then Q. So to answer this question, let's look at a typical modality that can help us. Let's say we are talking about the solid here that is ice. Just let's take that as an example. Now, on the scale that we're given, we have theta and we have time t. This is the origin of the graph. Let's say this is 0, and this is a negative number. Let's say minus 20 degrees Celsius, okay? And here, I will say this is 100 degrees Celsius, just hypothetically to explain this particular question. We can see that initially in this region, in this first region that we're talking about, here, in this region, that means we are still having ice, okay? That's not too clear. Let me just use the hint that can be seen clearly. Let's say we're talking about ice here. What happens between this point and this point is that the ice as a solid is being converted into water. So there's no change in temperature. So this is a change of state that is converting the ice to water, and that is happening at 0 degrees Celsius. So because we are only going to have the latent heat of fusion of ice in place at that time, there's no change in temperature. So we can see that here, change in temperature, change in theta is 0. So the heat is only being used to convert the ice to the water. And then moving to the right region here, what we have in that particular case is definitely we are looking at water, because from 0 degrees Celsius, the temperature is increasing with time. It's increasing with time to such an extent that when it goes to its boiling point, so definitely that means that here on point Q, the temperature of the water is not increasing again because it has gotten to its boiling point 100 degrees Celsius, and so we are just having the water boiling, and that is all there is to the question. So looking at the first option, we have that as freezing and vaporization. No, that's not what our explanation is telling us. In the second option, we have evaporation and solidification. No, that's not what we are also coming up with. In the third option, we have melting and boiling, and I think this is the correct option, because initially it's a solid at 0 degrees Celsius for a time, for some amount of time. The ice is just being melted from solid to liquid. Then when it gets to the liquid and we continue eating it, so that is being indicated with this straight line, okay? And then getting to point Q, already the water is boiled and is just at its boiling point, and then we have boiling taking place because that's 100 degrees Celsius in the case of the water that I used to explain. Of course, definitely is not condensation and evaporation. It's not moving from the liquid state to the solid state at point P. So looking at all the options, the correct option is option C.
We are being asked that a graph of tensile stress is plotted against tensile strain, and what does the slope of the graph represent? If we are to draw that graph out, we are being told that it is tensile stress against tensile strain. So now, normally the graph will be a straight line graph, and for us, we are being asked that what is the slope of this graph of stress versus strain. Now, this is a depiction of our slope, so you can say this is our slope, and by reason of our understanding of mathematics, slope is the change in the y-axis over change in the s-axis, and if you are representing that correctly, our y-axis is the stress, and then the x-axis is the strain. So we're having this slope to be stress over strain, and stress over strain is nothing but the Young's modulus. So the graph of tensile stress plotted against tensile strain will give a slope that is the Young's modulus. So that's that with that question. Now in this question number B, we're asked to state the energy transformation in shooting a piece of stone using a catapult. Okay, so if you have our catapult here and we have the sling attached to it, normally for us to actually use a catapult, we draw back the sling, okay, and maybe we have a stone there that we want to actually launch for, to shoot at a bird, shoot at a lizard, whatever it is we use that for. Now normally we draw the string back, and then after drawing the string back, what we do is we draw it back like this, and then after release, the stone will fly forward. Now, the energy transformation taking place is the potential energy that is being stored in the string is being released to give the kinetic energy of the stone. So, the energy transformation is potential energy to kinetic energy. And that is the solution to our question here. In this question, we are told that an archer pulls a bow by 0.7 meters with an arrow of mass 60 grams. The stiffness of the bow is given as 200 Newton per meter, and we are to calculate the speed of the arrow immediately after its release. So if you have the diagram of our bow as being shown in the diagram, so we want to look at the case scenario before the bow is being pulled, and we are told that before it is pulled, even just normally, the bow has a stiffness of 200 Newton per meter. So if you are to look at the bow in its resting position before the string is pulled, let's show the string like this. Okay, so this is how the bow is. But then at the point of shooting an arrow, the string of the bow is going to be pulled backward, as being shown now in the red ink. So we are pulling the string of the bow backward. So we have an arrow that is about to be shot at something. Okay, it's shot at a target. So now we are told that the extension by which the bow was pulled, that was given as 0.7 meters. So you can say we want to represent that. So this extension from the initial position before being pulled, and now that it's being pulled, the extension is 0.7 meters. All right. So the mass of the arrow was given as 60 grams. So mass is 60 grams. Now, we can convert that to kilogram by dividing by 1,000. So the mass will be 0.06 kilogram. Now, the property of the bow, we are given the stiffness K. The stiffness of the bow K is 200 Newtons per meter. Okay. So we're asked to find the speed of the arrow immediately after its release. Now, with the understanding of the conversion of energy from, here in this case, potential energy to kinetic energy, we can actually state out what we are being asked. We are being asked what is the velocity. Okay. We know the stiffness of the bow to be 200 Newtons per meter. We know the extension of the bow to be 0.7 meters. Now we know the mass of the arrow to be 0.06 kilogram. But what is happening here is actually a translation of energy from potential energy when the bow is being pulled to kinetic energy when the bow is released and the arrow is shot at a specific target. So the principle of conservation of energy is telling us that the elastic potential energy of the bow is equals to the kinetic energy of the arrow. So if we want to just equate that and put in our equation, what is the formula for the elastic potential energy of the bow? In this particular case, it is 1/2 multiplied by the stiffness multiplied by the extension raised to power 2. Then the kinetic energy of the arrow is half multiplied by the mass of the arrow multiplied by the square of the velocity. We can cut out the half and then substitute for the values of all the values we are having here. K is 200 Newton per meter. Extension is 0.7 meters. Okay. The mass of the bow is of the arrow is 0.06 kilogram. Then we are looking for the velocity of the arrow. Now we can divide both sides by 0.06. And if you bring in our calculator to solve for the left-hand side, we will have that to be 200 multiplied by 0.7 raised to power 2 divided by 0.06. So that is 1633.3. Okay. So V raised to power 2 is 1633.3, such that the velocity will now be the square root of 1633.3. So if we just want to find the square of our answer, square root of our answer, that will be 40.4 meters per second square. So 40.4 meters per second. That will be 40.4 meters per second. And that is the solution to our problem. In this question, we are asked to state 3 advantages of optical fibers over conductors. Okay, now for those of us that don't know what these are, it is just as shown. And because we are talking about optical fibers in comparison with conductors, I think we should be talking about our networking scenarios. And now a scenario is being depicted on the diagram. Now a router may be connected to the internet through some so many various means. Talk about leased line, fiber optics also, whatever it is. But now, particularly, I want to be concerned about the internal connection of the active devices in, say, an enterprise. Now, we can have a router, we can have an aggregation switch or a core switch, we can have an access switch as being just shown, okay? And then we can have our end devices, talk about laptops, PCs, servers. Sometimes we also include some wireless devices. So, but for this scenario, let's talk about, say, a laptop, then a PC with a monitor and a desktop machine, okay? And then this is a PC. Then we also have, let's say, a server where we're actually storing some devices for retrieval and co. Now, if you are looking at this type of scenario, a typical means of connecting all these devices is if the devices are supporting, let's say they are supporting fiber optics, the router can connect to the core switch with a fiber optic cable, okay? Then the switch, the core switch and the access switch can also be connected through fiber optic cables as shown in red. But now end devices can be connecting to the access switches by Cat6 conductors as shown in blue. So blue for Cat6 and red for fiber optics. So what are the advantages of optical fibers over conductors? The very first one we are looking at here is that the optical fibers operate at faster speed because it's called uses light to transmit data, and can do this for up to 10 gigabit per second and sometimes even 40 gigabits per second, depending on the support of the device on which it's being plugged into. Now, because it's optical fiber, it can also cover long distances. So it's used in submarine cables, and typically, maybe for the general use, you can use, whenever you are using a multi-mode fiber optic cable, it can cover 550 meters, but for single mode, it can cover 5 kilometers. Now, Cat6 conductors generally, they only cover a maximum of 100 meters. Now, optical fibers are also more reliable as they are not susceptible to EMI. EMI is the interference that comes as a result of electricity trying to also affect the conduction of the transmission of data in the Cat6 conductors. And then even though initially when you want to set up your fiber optic cables, then they tend to be more costly, but in the long run, the total cost of ownership when using optical fibers is far more lower compared to using Cat6 conductors. So these are some of the advantages of optical fibers over conductors. Here in this question, we're asked to state one use of geostationary satellites and polar orbit satellites. Now, geostationary satellites are generally regarded as satellites that are fixed over a particular equator of the Earth. So if you have the Earth and then we have a particular satellite that is not moving around the Earth, is just fixed at a particular location, that's what is called the geostationary satellite. Now, because of the fact that this satellite is fixed, it's quite useful for monitoring, is used for broadcasting. So all the communication devices, whenever you want to talk about that, you are talking about the geostationary satellite, okay? So these are some of the uses of geostationary satellite. It's fixed at about 36 kilometers above the surface of the Earth. Now, when we're talking about the polar orbit satellite, looking at the world is saying that there's an orbit that this satellite is actually traversing through. So this satellite is moving around the Earth with a period of 24 hours. So in a day, it would have circumvent his way across the globe. And of course, looking at that, one of the very good uses for which they use this is for espionage, for spying. Want to know, okay, what is happening in this particular location after I'm coming back the second time? Is this still the same thing that I'm observing? Okay. It's also used for earth mapping. It's also used for so many other uses. We're asked to state just one use. So I believe that this will suffice in this particular question. In this question, we're asked to list the forces that keep the Earth revolving around the sun. Okay, so the Earth revolves around the sun, and if we are looking at the Earth, why is it that the Earth is not varying off its course of navigation around the sun? This is largely due to two particular forces: the centrifugal force and the centripetal force. Now, if you are looking at the axis of the Earth to the sun, normally the Earth is moving with a particular velocity around the sun, but the centripetal force is directed towards the sun, and then the gravitational force is directed outside the sun, okay, just as shown in the diagram. And then the velocity of the Earth is just moving along as if it wants to veer off, but because of these forces, it is being kept in the orbit so that it is revolving around the sun. So these are the centripetal force and the centrifugal force. Now, in this second question, we are told that a force is applied to an object of mass m such that in time t, the velocity changes by changing v in the direction of f to m. We are to write an equation relating f to m, delta v, and t. Now, generally, what is the formula for the force? In this question, we are giving f, we are giving m, and we are giving change in v in time t. So if you are to recall, we know that the force is generally given as mass times acceleration, okay? But now we are not giving the acceleration outrightly, but we know that the acceleration is change in velocity over t, that is final velocity minus initial velocity over t. So for this particular case, we are not giving initial and final velocity. So we should stick with change in velocity over t. So if we are to substitute that, we can say f is m delta v over t, and that is the expression for the force. This question is asking us the dangers associated with the use of a laser. Now, a laser is a device that shoots a monochromatic light of high intensity, which can be dangerous if it's not handled properly. So some of the dangers included with the use of laser include explosion. We can have a fire outbreak. It can burn the skin. Now, if it is exposed directly to the eye, it can also cause eye damage. So whenever we are handling the laser, we should actually be careful. In this second question, we are told that a laser produces a beam of light of frequency 4.82 exponent 14 Hertz. We are to calculate the energy of a photon in the laser beam. We are given the Planck's constant H to be 6.6 multiplied by 10 raised to the power minus 4 joule seconds. Now, what we need to know before we can do this is what is the formula for the energy of a photon of light. Now, the formula E is given as FH. Now, it's interesting that in this particular question, we are just giving the frequency. We are not talking about the wavelength. We are not talking about the speed of light. So it's making our work easy. Okay. The energy of the photon in the laser beam is given as the frequency multiplied by the Planck's constant. So if you are to put in the values, that will be 4.82 exponent 14 multiplied by 6.6 exponent minus 34. So let's bring in our calculator to solve that. So 4.82 exponent 14 multiplied by 6.6 exponent minus 34. So that will be 3.18 exponent minus 19 as 3.18 exponent minus 19 joules. Okay, so that is the answer to our question here. In this question, we are told that an artificial satellite is placed in a geostationary orbit at a height of 9.6 exponent 6 meters above the surface of the Earth, and we are to calculate the speed of the satellite in the orbit. We are given the radius of the Earth to be 6.4 exponent 6 meters and pi to be 3.14. Now, if you are to depict this diagram pictorially, let's look at the diagram of the Earth. Africa is being shown in black. Then we have the body of water. Let's show that in blue, just some light blue. Okay. Now, this is the Earth. We're talking about a satellite that is placed 9.6 exponent 6 meters above the surface of the Earth. So let's say this is our satellite as being shown. So from the distance of the satellites, from the location of the satellite to the surface of the Earth, we have this to be 9.6 exponent 6 meters. So let's call that h. Let's say this is the distance h to be 9.6 exponent 6 meters. Okay. Now in the question, we are given that the radius of the Earth from the surface of the Earth to the Earth core. Okay. We are given the radius of the Earth to be the radius r. Earth's radius, capital R, was given as 6.4 exponent 6 meters. Now, what we need to note, if you are asked to find the speed, we know that this particular satellite is going through a geostationary orbit. So if we try to depict that, we can say the satellite is navigating its way across the path that is being shown in blue. So it will be revolving around the Earth. Okay. Now, the time for it to complete a revolution there is going to be 24 hours because it will make a complete revolution in 1 day, and 1 day is 24 hours. Now, we are looking at the distance covered. We are seeing that this orbit is having a radius of our small r, giving us the radius of the Earth plus the height of the satellite. So the radius of its revolution to the center of the Earth will now be, if we had 9.6 and 6.4, that would be 16 exponent 6 meters. So we know the orbit when we are asked to find the speed of the satellite. From our understanding of physics, speed is given as distance over time. Now, for this particular case, we are noticing that our distance is actually the circumference of the circle, okay? Circumference of the circle that's being denoted as the orbit of the satellite. So we have the circumference of orbit, and the formula for the circumference is nothing but 2 pi r, and our r has been gotten to be the sum of the radius of the Earth and the height of the satellite to the surface of the Earth. Now, the time is 24 hours. That's the period it will take to complete one revolution. And if we convert that to seconds, that will be 24 multiplied by 60 multiplied by 60 again. That's the conversion to seconds. So the speed of the satellite will be the distance, that's 2 times 3.14, then multiplied by the radius, that's 16 exponent 6, divided by the time, the period for one complete revolution, that's 24 times 60 times 60. If we bring in our calculator to solve that, we have 2 pi times 16 exponent 6 divided by 24 times 60 times 60. That is 1163.552835. And if we put that in standard notation, that will be 1.16 exponent 3 meters per second. So that is the speed of this artificial satellite. this question is asking us to state two differences between mass and weight. Now, to understand this, mass is the amount of matter in a body and is a scalar quantity that is measured in kilogram. That's what we get when we stand upon a weight measure, okay? Whereas the weight is actually a force. It's the force of gravity on a body, is a vector quantity. That is what will break a plate if you actually fall on a plate. So if you are to summarize this, it is just as shown on the board. The mass is having a constant value. It doesn't vary from place to place, but the weight, due to the shape of the heart, the altitude, it varies from place to place, is measured in newtons because its force is a vector quantity, and the mass is only a scalar quantity, is measured in kilograms. These are some of the differences between mass and weight of a body. All right? Okay. In this question, we're told that two forces F and 250 newtons act on a uniform rigid body of weight 50 newtons, and we're to find the clockwise moment about the pivot and the value of F. Now, in the first question, we are asked the clockwise moment, and that is the direction has been shown. Is the direction of the wall clock moving from our left to our right and navigating around just in a clockwise direction. So the pivot is being shown in red. Now, if you look at the 50 Newton force, that is a counterclockwise movement. It's going to be a counterclockwise moment. And then the force F is also going to be a counterclockwise moment. So the clockwise moment is the moment of the force that is 250 newtons. So that's what we are first asked to get. That's the clockwise moment. So the clockwise moment about the pivot in the first question, the clockwise moment about the pivot is the product of the force multiplied by the perpendicular distance to the point at which we are considering the moment. And in this particular case, is the distance, the perpendicular distance to the pivot as given in the diagram. So that means our work is we are multiplying the 250 Newton multiplied by 0.75 meters. So that clockwise moment about the pivot is giving us the force, that's 250 newtons, multiplied by the perpendicular distance, that's 0.75 meters. So if we bring in our calculator to evaluate that, we have 250 times 0.75. So that's 187.5 Newton meters. So the clockwise moment about the pivot is 187.5 Newton meters. Okay. In this second question, we have to find the value of the force F. Okay. In this particular case, that means for us to solve this, we can consider all the moments about the pivot. So we are looking for the value of the force F that will keep this body in equilibrium. Okay. So we can just evaluate the distance. Now, in the question, we are told that the body is uniform. That means the weight of that body will act at the center. So 50 newtons at the center. Already we are given that the length of the body is 3 meters. Then the center of that will be 1.5 meters. So to the left of the 50 Newton meters, this will be 1.5 meters. And already we have 0.75 meters to the right. So the remaining one will also be 0.75 meters. The addition of the 3 will give 3 meters as appropriate. So now, if you want to take moments about this particular body, we already know that the 250 newtons will be going through a clockwise moment. The 50 Newton force will be going through a counterclockwise moment, and the F that we are looking for will also be going through a counterclockwise moment. Okay. So for this particular rigid body to be kept in equilibrium, the sum of the counterclockwise moment and the sum of the clockwise moment must be equal. So if we are to take our counterclockwise moment, first we have the force F multiplied by the perpendicular distance, and that distance to the pivot will now be 1.5 plus 0.75 meters. Okay. And then multiplied by the other force, 50 newtons, multiplied by its distance to the pivot, the point where we are taking the moment. That will be 50 times 0.75 is going to be the sum of the clockwise moment. That's 250 times 0.75. Okay. We got this by taking moment about the pivots. So if we are to just open up our bracket and try and solve this. 1.5 plus 0.75, that will be 2.25 multiplied by f, okay, plus 50 times 0.75. Okay, we are going to move that to the right hand side. So we have 250 times 0.75. Okay, we got that initially to be 187.5. 187.5 minus 50 times 0.75. When they move to the right hand side, 50 times 0.75, that's 37.5. Okay, so if we are to evaluate that, 187.5 minus 37.5, that will be 150. So we are going to see that our force that we are looking for is 150 divided by 2.25. So using our calculator to solve that, 150 divided by 2.25, that's 66.67 newtons. Okay, so that's the value of the force F. The diagram above illustrates the positions P, Q, and R of the object moving clockwise. Okay, the object is moving clockwise in a circular path. So we can say this is the direction of movement, that's clockwise. Okay. So we are asked to copy the diagram and draw straight lines with arrows to indicate the net force at P, acceleration at P, velocity V at R. So let's do that. I'm copying this and I can just paste. Okay. So now the net force F at the point P, we'll try and locate that. Now, for this particular diagram that we are given, the net force F at P, okay, the force will be a centripetal force and is going to be directed towards the center of the circular path. So the centripetal force F will be directed from P to the center of the circular path, which is T. So this is our F shown in red. Okay. Then in the second case, we are asked to draw straight line with arrows to indicate the acceleration at P. The acceleration will also be directed towards the center, just like the force. So the acceleration at P is also towards the center of the radial part. So there it is, shown in blue. That's acceleration A. All right. Then we're also asked to find the velocity V at R. Now, unlike the centripetal force and the acceleration, the velocity will be directed tangential to the radius of this circular path. Okay. So if the acceleration is acting towards the center, the velocity will be acting at an angle 90 degrees to the acceleration. So now we're asked that we should take that at point R. It's going to be tangential to the center of the circular path and it's going to be directed in the clockwise direction. So this is going to be our V, okay, V at an angle of 90 to the center of the circle. And that's the solution to our problem. In this question, we are told that a man weighs 100 newtons on the surface of the moon. If the acceleration due to gravity on the moon is 1/6 the value on the surface of the earth, we are to find the mass of the man on earth. Now, we need to be quite careful with this type of question. Even though we are giving the weight of the man on the surface of the moon, we need to remember that actually the mass of an object, the mass of a body does not change. The mass is not affected by acceleration due to gravity. The mass is a constant. It does not vary from place to place. I'm laying emphasis on this so that we don't make the mistake of just trying to calculate the weight of the man and just the weight of the man. No, we are asked to find the mass of the man on earth. So the mass of the man on earth and the mass of the man on the moon is going to be the same. It's only the weight of the man that can change. So if you have the moon as shown in the diagram and we have the man, okay, standing on the moon, maybe he's an astronaut, and then the same man on the earth, okay. Now we are told that on the surface of the moon, the weight of the man on the surface of the moon, the weight of this man, let's call that W, is 100 newtons. Okay. Then the acceleration due to gravity on the moon is 1/6 the acceleration due to gravity on the surface of the earth. So GM is 1/6 GE. Now for the earth, we have been given GE to be 10 meters per second square. All right. The acceleration due to gravity on the moon is 1/6 that of the earth, and that of the earth we have been given as 10 meters per second square. So the acceleration due to gravity on the moon is 10/6 meters per second square. All right. So now since we are asked to find the mass of the man, okay, and I was making emphasis on it that whether on the earth or on the moon, the mass of the man is going to be the same. Now, from forces, mass times acceleration, the mass will be force over acceleration. But here in this case, we're talking about the weight and the acceleration due to gravity. So our M will be W divided by G on the moon, and that will be 100 divided by 10/6. And if we appropriately operate that, that will be 100 times 6/10, and that will be 60 kilograms. I don't need to bother myself with what is the mass of the man on earth or the mass of the man on the moon. The mass is going to be constant whether the man is on the moon or he is on the earth. It's only the weight that differs. That is as a function of the acceleration due to gravity per location. So the mass of the man is 60 kilograms. In this question, we're asked to define the specific latent heat of vaporization. When we're talking about the specific latent heat of vaporization, we're talking about a change of state from liquid to gas, okay? And it is defined as the amount of heat needed to change 1 kilogram per unit mass of a substance from its liquid state at its boiling point and at constant temperature to vapor. So, as shown in the diagram, let's say we have a particular substance, okay, in its liquid state as shown, and then these are substance in its liquid state and is 1 kilogram per unit mass, okay? So we are applying some heat. We're applying some heat to this particular substance, and then at its constant boiling point, at constant temperature, and at the boiling point of the liquid is being transition, is undergoing a change of state from that liquid state to gaseous state. This is the amount of heat that is needed to carry out this process is defined as the specific latent heat of vaporization, just as shown on the board. It is the quantity of heat needed to change 1 kilogram per unit mass of a substance from a liquid state at its boiling point and at constant temperature to vapor. This question is asking us, why is the freezing compartment containing the evaporator normally located at the top of a fridge? Now, looking at the diagram of a fridge, as requested in the question, the upper part here, that's the freezing compartment. That's where the evaporator is located. And normally, let's look at our transfer of heat in this particular scenario. Normally, since that is the freezing compartment, that's going to generate cold air, okay? Now, cold air is denser than warm air. So, by reason of its density, it's going to migrate downwards. So, the cold, dense air, they are going to actually migrate downwards. They will be, because they are denser than the warm air that will be in the surrounding, it's going to navigate downwards, okay? Now, conversely, at the base of the fridge, we are going to have less dense air, okay? It's not as cold as the top, so it is less dense. Now, that we normally want to migrate upwards. So, the warm, less dense air in the fridge, at the base of the fridge, that we want to migrate upwards. And now, as a reason of this migration of, okay, the denser air at the top, at the evaporator, and the less dense one, convection is going to actually occur. So the colder air will descend down, the warmer air will rise up, and with that, there will be convection taking place, so that everything that we are putting in the fridge will get to share some of the coolness of the refrigerator. So that is the explanation for this question. Yeah, we have to use the kinetic theory of matter to explain how addition of heat to a substance causes an increase in temperature. Now, for us to actually explain this, we need to understand what is going on when heat is added to a particular substance. So, what we're going to do is we're going to consider this scenario in which we have a substance that is observable, okay? And for that particular substance, there is a temperature at which we are observing everything that is taking place initially. So now, for the particular substance, the molecules are normally undergoing some movement, okay? But now, in this particular case, we asked that addition of heat is being introduced to this system. Now, if heat is being introduced to the system, what we are going to have is actually well explainable using the kinetic theory of matter. And that's what I'm going to attempt to do here. So if you have the scenario like this, normally what the heat energy that is introduced will do is that it's going to increase the internal energy within the system. And now, when the internal energy is increased, the average kinetic energy of the molecules increases so that they move about. The increase in average kinetic energy that will actually result in increase in temperature. Okay, so once the heat is introduced to the system, the average kinetic energy of the molecules increased. And since the average kinetic energy of the molecules increased, they move more around. And as they are moving more around, heat will be generated so that after the application of the heat, we have an increase in temperature. So that's how kinetic theory of matter can be used to explain the increase in temperature whenever we have addition of it. Now, this is going to be summarized below, okay? So we have the summary that the heat energy is used to increase the internal energy of the substance. This increases the average kinetic energy of the molecules, and it's the increase in the average kinetic energy that results in increase in temperature. In this particular question, we are given that the diagram above illustrates two capillary tubes of uniform cross-sectional area, and then is containing a trial by mercury. Boyle's law is obeyed, and we have to calculate the atmospheric pressure. Now, how do we go about solving this question? Normally, we can have three cases in which we can talk about the pressure of the mercury and the atmospheric pressure. Now, the first case is when the tube is being placed as shown. The open end is at the top. The other case is lying horizontally. And then the third case, the open end is inverted downward. So if you have trapped there by mercury, and the mercury is being shown in blue, okay, we can actually depict the effect of the pressure per stage for each of these three scenarios. So in the first case, now because of the orientation of the tube, normally we are going to have the atmospheric pressure and the mercury pressure. The mercury pressure will be pressing on the trap there downwards, okay. Atmospheric pressure will also be pressing downwards on the mercury pressure. So the total pressure in this case will be the sum of the mercury pressure and the atmospheric pressure. But in the case in which the tube is lying horizontally, now the mercury pressure will not be included because that will just be acting downwards. It's not pressing on the air. So the total pressure in this case is only the atmospheric pressure. Okay. Now in the third case, we are seeing that the tube is inverted. So atmospheric pressure will still be acting upward, but the mercury pressure will be acting downward, just as if it's responding to acceleration due to gravity. So the total pressure will be the atmospheric pressure minus the pressure of the mercury because they're in opposite direction. So any of these two cases, we have three cases here, any of the two can be used to actually solve this question with the application of Boyle's law. And what does Boyle's law state? Boyle's law is telling us that at constant temperature, the pressure is inversely proportional to the volume of an ideal gas. Okay, so now we have pressure is inversely proportional to the volume at constant temperature. And as you can see, we're not talking about temperature in this particular setup. So that means we've introduced a constant into the equation. We can have our pressure is K over V so that K is equal to PV. Now, constant is equal to the multiplication of the pressure and the volume, meaning that the first pressure and the first volume, if we multiply them, is going to give us the second pressure and the second volume. And the graph is just as shown, is going to be this curve when we plot the graph of pressure against volume. So we are going to be using this to solve this particular question. P1 V1 is equal to P2 V2. So here for our question, in trying to go ahead to solve this question, we see that it's quite noticeable that we are talking just about centimeters here. Okay, so since the tube in the first scenario is open at the top, the atmospheric pressure is going to be acting downwards. Okay, but for the horizontal case, in which the tube is lying horizontally, we are saying that we are not going to be using any pressure for the mercury. It's only going to be the atmospheric pressure acting inwards at the open end of the tube. Now, the length of the mercury and the length of the dry air is actually analogous to the pressure that we are talking about. So we have a scenario 1 and a scenario 2. And by Boyle's law, as we looked at initially, we know that P1 V1 is equal to P2 V2. So what is left for us to note is that now our pressure is actually analogous to the length that we have been given, and likewise our volume also. All right, the pressure we are using, the pressure of the mercury and the pressure of the atmosphere. The volume we are using, the length of the dry air in the tube. So now in the first case, what's going to be our P1? P1 is going to be the sum of the atmospheric pressure and the mercury pressure. So that will be PA plus 15 centimeter. 15 centimeter is what is analogous to the mercury pressure, okay? And then in the second case, we're only looking for the atmospheric pressure because the pressure of the mercury is not acting on the dry air. So using Boyle's law, we can go ahead to try and solve this particular question. So in the first case, we have the P1 is PA plus 15. Then the V1 will be 20 for the first case and 24 for the second case. So we have PA plus 15 multiplied by 20 is equal to PA multiplied by 24. So we can divide both sides by 20. So in the first case, the 20s will cut out. In the second case, you can say 4 in 20 is 5, 4 in 24 is 6. Okay. So if we move, okay, we want to just solve this, we can now say that we have 6 over 5 PA. Okay. When the other PA on the initial left-hand side moves to the right, that will be minus PA. Okay. That's equal to 15. So if we find out LCM, we have 5, we have 6 PA minus this over 1 minus 5 PA. So that will equal to 15. Okay? 15 over 1. So 6 PA minus 5 PA is PA. Then 5 will cross over to the other side so that we have our atmospheric pressure is 15 times 5. And that is 75 centimeter mercury. You know, we are working relative to mercury. So it's 75 centimeters mercury. In this question, we are told that red beans of mass 100 grams is capable of releasing 240 kilocalories of energy in a day. An adult requires 2,200 kilocalories to perform optimally. We have to calculate the mass of beans required to sustain 500 adults first. Okay, now this is looking more like a relational question. We are told that 240 kilocalories is obtained from 100 grams of beans. 100 grams is the same as 0.1 kilogram. Okay, so we have from 0.1 kilogram of beans. Okay. So now an adult is going to need 2,200 kilocalories to perform optimally. So an adult is going to be needing, just one adult in this case, note that an adult is going to be needing how many kilograms of beans? We can calculate that 2,200 kilograms can be gotten from X kilogram of beans. So in just relating these two statements proportionally, you can have 240 is equivalent to 0.1 kilogram. 2200 is equivalent to X. So if you cross multiply, just to find the value of beans that will be needed per adult, mind you, X is going to be 2200 times 0.1 divided by 240. So using our calculator to evaluate that, times 0.1 divided by 240, that's 0.9167. Okay, so we have 0.917 kilogram of beans will be needed for an adult. Okay, this will be the kilogram of beans needed per adult. But we asked for the mass of beans required to sustain 500 adults. All right, so in that case, 500 adults will require 0.917 multiplied by 500. So when I just say 500 adults will require 500 times 0.917 kilogram of beans. And if I had to bring in our calculator, that will be our answer multiplied by 500, and that will be 458.33 kilogram of beans. So the mass of beans required to sustain 500 adults will be 458.3 kilogram of beans. All right. Now, furthermore, we asked to find the mass of fuel that will be required if a nuclear reactor were to produce the same amount of energy as in our previous question. And we are told that 1 kilocalorie is 4,184 joules, and then C is 3 exponent 8 meters per second. Now, we have already established the fact that one adult needs 2,200 kilocalories of energy. Okay. But 1 kilocalorie of energy is the same as 4,184 joules. So to find the amount of energy that will be equivalent to what one adult needs, that will be 4,184 multiplied by 2,200, and that will be the energy that an adult needs to be sustained. Now, that's just for an adult. For 500 adults, we are going to be needing 500 multiplied by this value. So we have 4,184 times 2,200 times 500 joules of energy. That will be what will be required for 500 adults. That will be the amount of energy that 500 adults are going to need. Now, we should know that for a nuclear reactor, the energy from the nuclear reactor E, the energy E from a nuclear reactor is given as M multiplied by C raised to power 2. Okay? So now we are asked to find the mass M, and we have been given the value of C. So if you want to relate these two, that the energy from the nuclear reactor and the energy needed by 500 men, we can say MC raised to power 2 is equal to 4,184 times 2,200 times 500. Okay? And now we have been given C to be 3 times 10 raised to power 8 meters per second. So we can say our M is going to be 4184 times 2,200 times 500 divided by 3 times 10 raised to power 8 all raised to power 2. So we can use our calculator to evaluate that. So we have 4184 times 2,200 times 500 divided by 3 exponent 8 raised to power 2. Okay. So that's 5.1137 exponent minus 8. So we have 5.11 exponent minus 8 kilogram of fuel. So that's the solution to that question. We're asked to list the 3 secondary colors of light in this question. Now, there is a color wheel that is generally used to identify the secondary, the primary colors of light, and it is as shown on the board. So the primary colors are red, blue, and green, and the secondary colors are the mixture of all these three. So red and blue will give magenta, red and green will give yellow, and blue and green will give cyan. So the primary colors are noted to be red, blue, and green, and secondary colors are magenta, yellow, and cyan. We have this diagram here, and we're told that the diagram illustrates a defect of the human eye. We are to state the type of defect and the name of and the type of lens to be used in correcting that defect. Now, looking at this image, we are seeing that the image is being formed far behind the retina. So the defect is long-sightedness. It's not being formed on the retina. It's being formed far behind the retina. And another name for that is hypermetropia. That is the defect that's being shown in the diagram. Now, to correct this type of defect, looking at the rays of light coming from the object, we are seeing that they are going far beyond where they're supposed to go. So what we need is a converging lens to convert them on the retina where they are ideally supposed to be. So if we bring in a converging lens, normally a converging lens is going to converge rays of light that are passing through it. So rather than the original location of the rays of light, now the converging lens will converge those rays to the pupil, okay? And then the pupil can just have lesser work to do to converge the rays on the retina as shown. And so once a converging lens is brought in, the defect will be corrected. Here in this question, an object is placed between two mirrors inclined at right angles to each other, and we are to find the number of images formed, and then we are to copy the diagram and locate and label the position of the images formed by the mirrors. Now, there is a formula to get the number of images for mirrors inclined at an angle to one another, and that formula is given as the number of images n. So the n is 360 divided by theta minus 1, where theta is the angle of inclination of the two mirrors to one another. In this particular question, we are told that they are inclined at right angles to one another. Right angles, okay? So we are going to have 360 over 90, which is a right angle, minus 1. That will give us 4 minus 1. So the number of images that will be formed is 3. So we have 3 images are going to be formed. Good. Now, in this second question, we are told to copy the diagram. So I'm going to just copy that out and paste. So on the copy diagram, we are to locate and label all the positions of the images formed by the mirrors. Now, for mirror 1, the object distance and the image distance are going to be the same. So I'm showing that in blue. Okay, it's directly opposite. There's no enlargement. It's just like that. For mirror 2, the same distance, the same offset to the mirror is going to be on the other side of the mirror. So this is image 2 from mirror 2. Okay, so now what we are going to have is that the mirrors will be extended, and they're also going to reflect the image of one another. So here, mirror 1 is also going to reflect the image from mirror 2 at this location. Okay, and then mirror 2 is also going to reflect the image of mirror 1. So if mirror 2 is also extended up to that point, okay, it also reflects the image of image 1 at the same location in which his own previous image is located. So if you are to actually label them, we have this as image 1, the red as image 2. But since both are supposed to actually reflect, we have this is image 3 and also image 4. Okay, image 3 and image 4 are being located at the same position. So since they are both located at the same position, we are just going to see them as one. So we don't need to put them as 2 images. We can just say this is image 3. We can append it as image 3. So if you look at this, this is consistent with the formula that we just used to obtain the number of images that will be formed, and that is 360 divided by 90 minus 1. So that 1 is actually the image that we are subtracting from this case, and that's the solution to our problem. Okay, so in this question, we are told that a mirror of focal length 60 centimeters is used to produce a virtual image. So focal length is 60 centimeters. We have a virtual image that is 3 times larger than the object. Now we need to note this value that we are saying that is a virtual image. That's going to carry an implication that will reflect whenever we are working and trying to solve our question. So we have our focal length f is 60 centimeters. We have the magnification of the virtual image. We have m magnification m is 3, and normally the magnification is the image size over the object size. So that is v over u. The ratio of their proportion to one another is 3. So we have 3 is equal to v over u. And you can say v is 3u if you cross multiply. So if you want to use the length formula to try and solve this particular question, the length formula is stating that 1 over f is 1 over u plus 1 over v. But in this particular question, we have been told that we are talking about a virtual image. Now, not noticing that, we ensure that we are going to miss this question. But so what does it imply when we are saying the image is virtual? That means that the image is located at the same position as the object. So that image is negative because normally it will be located at the other side. So our v is going to be negative, so that our formula will now be 1 over f is equal to 1 over u minus 1 over v. Okay, but v is equal to 3u. So if we are to use that value, we have 1 over f. F is 60. 1 over 60 is equal to 1 over u minus 1 over 3u instead of v. Now we are saying 3u. We can find the LCM, and that will give us 1. Okay, we have 3 minus 1 over 3u. Okay, so we have that's 2 over 3u. So we have 1 over 60 is equal to 2 over 3u. We can cross multiply such that 3u will be 2 times 60 is 120. We can divide by 3. Okay, so that if we solve this, our u, the object distance, is going to be 2 times 20, which is 40. So 40 centimeters is the value of the object distance, but nobody asks us to find the object distance. We are asked to find the image distance from the mirror. So the image distance is v. All right. So image distance is v, and v have been given as 3u. So that will be 3 times 40, and that's going to be 120 centimeters. That's the solution to our problem. What we needed to note is that the image is virtual, so v is going to be negative, and with that, our question will be done and dusted. We have to state Lenz's law in this particular question. And Lenz's law states that in this current or EMF flows in such a way as to oppose the change in magnetic flux or any motion producing it. So, as shown in the diagram, if the motion causing the EMF is in a particular direction, the flux will flow in the other direction. And this is the Lenz's law that is used in electromagnetic induction and quite a whole lot of other applications. Okay, so that's Lenz's law. Okay, yeah, we're asked to state 2 applications of magnets. Magnet finds a lot of application in so many of our day-to-day activities. So some of them are being shown here. The magnet is being used in the magnetic compass for navigation. It's facilitating circuitry in headphones, and is used to generate rotational motion in electric motors. Is used in MRI to scan the human body. Can be used to separate mixtures, and these are just some few ways in which we make use of magnets in so many various fields. In this question, we are told that the diagram illustrates a step-down transformer to state the reason for using 2 coils, state the reason for using iron core and alternating supply. Now, the points are listed below. 2 coils were used to vary the input and the output voltage or current. An iron core is used for effective magnetic flux linkage. Iron can actually generate that a lot. Then the AC supply is used because if you use DC, that's going to provide a constant current, which will only be used in the primary winding and not the secondary winding, because the rate of change of magnetic flux in that case will be 0. So AC voltage is used and not DC. Alright. So here we're asked to find the secondary current of the transformer. Now looking at the diagram, the primary coil is to the left, the secondary to the right. And now we're asked to find, we're not given the number of turns in the secondary coil, we're given the number of turns in the primary. We're given the voltage in the secondary, we're asked to find the current, but for the primary we have the current and the voltage. Now, generally, for the transformer, the product of the current and the voltage in the primary coil is equal to the product of the current and the voltage in the secondary coil. So now the primary current is given as 5 amperes, okay, and the primary voltage is given as 220 volts. We can equate that to the secondary current that we are looking for multiplied by the secondary voltage, which is 110. So looking at this, our secondary current will be 5 times 220 divided by 110. And 110 can cut such that our secondary current is 10 amperes. Alright. In this question, we are told that a circuit is connected as shown and the resistance of the voltmeter, is 200 ohms. So locating the voltmeter, R is 200 ohms. Okay. So we have to calculate the voltmeter reading, the reading on the voltmeter. Now we need to actually analyze this circuit. Ideally, the same current will flow in series. So the current across the circuit, the current I, we can evaluate. But first, before we can evaluate the current, we need to find the total resistance of the circuit. So if you have that, we can use the Ohm's law. V is equal to I R total. R total now is the total resistance, so that I will now be voltage divided by the total resistance. So our first assignment is to find what's the value of the total resistance. We can call the 500 ohm R1 and the 400 ohms R2. But now R1 and the resistance of the voltmeter are in parallel. So we have R parallel, which we need to evaluate. And for us to find that, it is 1 over R parallel is 1 over R, the resistance of the voltmeter, plus 1 over R1, the 500 ohm resistance. So if we are to solve this, we can say we're going to have 1 over Rp is equal to 1 over 200 plus 1 over 500. So for this, we can easily find the LCM as 1000. Then 200 in 1000 is 5. 5 times 1 is 5 plus 400 in 1000 is 2. 2 times 1 is 2. So 1 over Rp is 7 over 1000, such that our Rp is 1000 over 7. If we find the inverse of both sides. Okay. But now that's not the total resistance. That's not the total of the value resistance. The total resistance will now be the resistance in parallel plus the resistance R2 in series. So we have 1000 over 7 plus 400 over 1. And if we find out LCM, that's 7 and 1000 plus 1 in 7 is 7. 7 times 4 is 2800. So that the total resistance is 3800 over 7. So now, since we know the total resistance, we can find the value of the current from I is equal to V over RT, and V is 6 volts, okay? So we have 6 over 1 divided by the R total is 3800 over 7. So evaluating that, we have 6 multiplied by 7 divided by 3800. So our calculator can help us to evaluate that. We will have this to be 6 times 7 divided by 3800. With that, let's put that in scientific notation. Okay. Now, 11 1.05 exponent minus 3 amperes. So that's the value of the current flowing in the circuit. Okay, but now we are asked to find the voltmeter reading. What the voltmeter is going to read is going to be affected by the 500 ohm resistance and the internal resistance of the voltmeter itself. Okay, so within these two nodes shown in red, the resistance there is the R parallel. So the voltmeter reading is going to be the current multiplied by the resistance in parallel. So that will be, voltmeter reading will be I multiplied by the R parallel. Okay, so that is going to be 11.05 exponent minus 3 multiplied by R parallel is 1000 over 7. So if we bring in our calculator, we just our initial answer multiplied by 1000 divided by 7. So that is 1.578 or 1.58 volts. So that's 1.58 volts, and that is the solution to our problem. In this question, we're asked to state two sources of background radiation. Now, background radiation is a measure of the level of ionizing radiation that is present in an environment at a particular location, which is not due to deliberate introduction of radiation sources. So, normally there are radiation that are coming in, but it's not deliberate. So, this is what is referred to as background radiation, and sometimes they can be gotten from medical X-rays, sometimes from cosmic rays, the one happening from outer space, sometimes from radioactive substance in the earth crust, sometimes from nuclear power stations and such like. So these are not deliberate release of radiation into the atmosphere. It's just regarded as background radiation. So some of the sources are mentioned already. We have X-rays, sometimes from cosmic rays, sometimes from the earth crust, and they are not deliberate. Okay. Now, the reason why the count rate of background radiation is not constant at a particular place is that normally radioactive decay is a random and continuous process. It's always changing dynamically, and since it's always changing, that means that it cannot be constant at a particular place. So with that, our question here had been handled. Okay, in this question, we're asked to name two materials that cannot be dated using carbon dating. Now, normally, when carbon dating is being used, it is used on objects that are containing organic material, and they're using the properties of radioactive material, carbon-14. So any material that does not contain carbon-14 cannot be carbon dated. So brick, rock, and metals are examples of such, and with this, we cannot actually use carbon dating to date them. Now, the type of nuclear reaction that can be used to detect leakage in an underground pipe is the gamma radiation. Why? Because gamma radiation can be detected through earth and metals. Okay, so if you are looking at an underground pipe and there is a leakage that is actually there on the underground pipe, what is done ideally to locate the location of the leakage is that a radioactive substance that can give gamma radiation, like say sodium 24, will be introduced into the underground pipe. Okay, so a gigamolar tube will be used to measure the amount of radiation that is detectable over the span of area that the pipe is going through. And normally a constant rate of radiation will be detected, but at the point at which there was a leakage, the radiation will be quite high. So an observer can easily read this off and say, okay, this is a point where the leakage is happening because I'm getting a high reading of radiation that is coming from gamma rays embedded in sodium 24. So it is gamma radiation that is used to detect leakage in underground pipe. In this question, we are told that two metal surfaces X and Y of work functions 2.9 and 4.82 electron volts are illuminated by light of wavelength 330 nanometers. So we want to get the surface that will emit photo electrons and calculate the kinetic energy of the photo electrons. Now, ideally, if you have a metal with electrons, okay, and then for the metal with these electrons, we have photons of light energy of some particular frequency that are incidents on them. Photoelectric emission will only take place when some conditions are being met, okay? So without those conditions being met, there's no means through which we can have photoelectric emission taking place. Now, for this particular scenario, each photon will actually carry a quantum energy that is given as E, and E is defined as H multiplied by F. H is the Planck's constant, F is the frequency of the photon, and now the frequency is also the speed of light divided by the wavelength. Alright. Now this is acting on a metal with work function, the metal with work function file. So now for electrons to be emitted from the metal, the quantum energy of the photon must of a necessity be greater than the work function of the metal. So if that is the case, then the electron that will be emitted will carry a kinetic energy that is going to actually be the difference between the quantum energy of the photon minus the work function of the metal. So if an electron will be emitted, the photon energy will be greater than the work function, and the kinetic energy of the electron that is released will be that quantum energy minus the work function. So using this principle, we can now go ahead to try and solve this question to actually get which of the surfaces, either surface X or surface Y, that will release electron in this particular question that we're given. We just need to know that for electron emission to occur, the photon energy must be greater than the work function. For the question 1, we have been given that the wavelength is 330 nanometers. But for us to calculate the photon energy E, we know that E is equals to the Planck's constant multiplied by the frequency. But now we are not given frequency, we are given the wavelength, and frequency is the speed of light divided by wavelength. So we have our H, Planck's constant, we have the speed of light C, and we have our lambda. Lambda was given as 330 nanometers. Now, what is the meaning of nanometers? Nanometers means 10 raised to power minus 9. So if you are to put in all these value, H is 6.6 exponent minus 34, C is 3 exponent 8, and then the lambda is 330 nanometers. And like I said, nanometers means times 10 raised to power minus 9. So we can use our calculator to solve that. 6.6 exponent minus 34 multiplied by 3 exponent 8 divided by 330 exponent minus 19. So this is 6 exponent minus 9. So the photon energy that is coming on the metal surface is 6 exponent minus 19 joules. Now, interestingly, we are given the work function of the metal in electron volts. So we know that we have been given that 1 electron volt is 1.6 exponent minus 19 joules. So for us to get the electron volt that will be equivalent to 6 times 10 raised to power minus 19 joules, we can say X electron volt is 6 times 10 raised to power minus 19 joules. We can cross multiply this so that we can have our X. It will now be 6 exponent minus 19 times 1 divided by 1.6 exponent minus 19. 6 divided by 1.6, and that is 3.75 electron volts. So it's 3.75 electron volt, that is the photon energy coming on the surface of the metal. And the two metals we have, one is 2.9 electron volts, the other is 4.8 electron volts. So 3.75 is greater than the 2.9 electron volts. So it is on the metal X in which the photon energy is greater than the work function of the metal that will emit electrons. So it is surface X that will emit electrons and not surface Y, because the photon energy is not up to the work function of the surface Y. All right. Last question, we are asked to calculate the kinetic energy of the photoelectrons. Now, already we have been saying that for the case of photoelectric emission, the photon energy is equal to the kinetic energy plus the work function, so that the kinetic energy will be the photon energy minus the work function. So we just calculated the photon energy to be 3.75 electron volts. We have been given the work function to be 2.9 electron volts. So if we are to subtract that, our kinetic energy will be 0.85 electron volts. But 1 electron volt is equal to 1.6 exponent minus 19 joules. So 1 electron volt is 1.6 exponent minus 19 joules. So 0.85 electron volts will be equal to 0.85 multiplied by 1.6 exponent minus 19 joules. So if we plug in that value in the calculator, this will be 0.85 times 1.6 exponent minus 19. And that's 1.36 exponent minus 19 joules. So that's the kinetic energy of the photoelectrons. And that is the solution to our problem.